So welcome to the day 2, and we are going to start the metamorphism session. Yesterday we had a very riveting magmatism, and we are into much more absorbing metamorphism session, and we are going to start with a talk, an informal type of talk by Professor Somnath Dasgupta. And I thought, he is of course well known to everyone, but for posterity's sake, a lot of youngsters are around. Briefly, I would like to introduce him. Professor Dasgupta, product of Jadavpur University, where he did bachelor's, master's and PhD. You would be interested to know, many people may not be aware, he started as a sulphide man. He did his PhD on sulphides of Rajasthan, Khetri area under Sanjeev Sarkar, and then he joined GSI, and later on he did a lot of work on manganese deposits, and he is well known internationally for his contributions on manganese deposits of Saussure belt and all that. Then he had the audacity to shift to Eastern Ghats, where he did equally monumental work. I mean, I am not aware of many people who made tremendous impact on 3 distinct fields: sulphides, economic geology, your metamorphism in the Gondite belt and all that, Saussure belt, and then coming back to Eastern Ghats, where he and his students have done monumental work. So, I mean, it's very fitting that he should deliver this introductory talk. And more importantly, Professor Dasgupta, in my opinion, his greatest contribution is creating very, very good students. You look at the students, Bulak Sen Gupta, Shantanu Bhomi, and so many, Shankar Bose and all, each of them have established their own sub-schools and all. I think that's what makes him very special, and we are happy that he is here. And sir, please, you can start your talk. Thank you.
Will you start after 2 minutes? I will.
Good morning. So, we thank you very much, Chalapati, for this very generous introduction, and Professor Talat Ahmed and friends, both young friends and not so young friends. So, we are here for 24 hours, more than 24 hours together, so I can call you friends, I believe. And so what I am going to talk about is not taking much of time, only 15 minutes, but about the history of metamorphic petrology in India a little bit. It's based on one idea that no nation or no subject has future unless they know the history. So the question is, I will start with a very brief introduction on metamorphism as it has been studied in India, and also I'm really happy for that Jalapati invited me here, of course, and I'm particularly happy to see that in today's session, all of today, 25% or more of the presenters are either my students or students' students. So actually, I'm covering 25% or 25 or 30. I did not actually count. It should be around that. Anyway, let's have it. The reason I did not project the slide because I don't have a cover slide. So it starts straight away with the subject. So as you know, I have just my name and my current affiliation. And so we start with the history that in metamorphic petrology in India, it started with excellent field observations and excellent petrography. The only drawback was that too much descriptive and the process was not highlighted very much in the early days. It changed dramatically when in 1980 the concept of carbonic metamorphism came, with Kapaldurga taking the peak, and the Geological Society of India organized a tremendous granulite conference in 1988, and which constituted who's who in metamorphic petrology. They all came together. But I do not believe that really contributed to the Indian metamorphic school, because it was a little bit of wasted, because we still know carbonic metamorphism in the name of Bob Newton. Although that is a big problem. So I believe that it was partially wasted opportunity. And keeping that in mind, we progressed to the middle age of metamorphism in India, when quantification started, process related started, and we used mostly geometrical analysis of phase equilibrium in the absence of instruments. So we did not have instruments at that time. I think it was a very clever step to take recourse. And I must say that one of the pioneers here is Professor Ravi Lal from Day2, who actually did excellent work on this phase equilibria geometrical analysis. So that way we studied, and then we did this theoretical formulation of 3D sensors. So we had a lot of new thermometers and barometers proposed by scientists from India, but also the field observations and petrography, it continued. Those things continued. In the modern period, from about 2000, there was a change because large-scale usage of analytical facilities started, availability of modeling softwares, quantification of processes on a global scale, and then we landed into the second important stage, the marriage of the different disciplines. So metamorphism, magmatism, geodynamics, everything came together with theoretical thermodynamics and kinetics. So things changed dramatically from 2000 onwards. So the major reason where Indian contributions to metamorphic literature is the first, I think, is the ultra-high temperature metamorphism. And these are the main aspects that we covered. New textures described, new assemblages described, new petrogenetic grids constructed, many new occurrences described. Eastern Ghats is just one of them. Then the second aspect was ultra-high pressure metamorphism. Starting from Somorari and to other places, we started looking at the journey of crustal material to great depth and then exhumation back onto the near surface condition. And then we started to look at how collisional orogenesis occurs and what time scale. The third contribution was, the Indian contribution was in the correlation of fast supercontinents using metamorphic petrology as a tool. So it was transcontinental correlation, which is based on many other aspects, not only metamorphic petrology, paleo-magmatism, magmatism, all other things, but metamorphic petrology started to contribute here in the global transcontinental correlation. So these are the three aspects that I think that the Indian scientists, they contributed quite a lot in the literature, which is very easily visible in the citations everywhere. Now, what should be the focus in the coming years? So, I read an article last year, Independence Day, Nature, which says in Nature, they say that the biggest puzzle is when did plate tectonics start? Yes, I believe that this is one of the most puzzling things. The second is, I looked at the proposals from the National Science Foundation document, which had all the big names in that contributing, and I just took 2 points from there which are relevant to today's talk. The first is when, why, and how did plate tectonics start? And the second one, how are critical elements distributed and cycled in the Earth? So these are the two topics that I think is our future in metamorphic petrology that we should look. And it's not my idea, but I think it is a globally accepted idea that this is what to be done. And then we must use-inspired basic science research. Now, these are the main things that I think that in the last 10-15 years we have looked into these particular problems: early Earth tectonics, crust mantle revolution, early atmosphere, climate, kinetic modeling of orogenic processes, etc., etc. I can name quite a lot, but I'm given only 15 minutes. So let's stop here. So these are the things that are mostly curiosity-driven research. But the question is that very important to understand what is to come. But biggest drawback is that it's not a work of 1 or 2 persons. So there should be multiple nucleation centers and multiple globes. So unless that thing happens, we are not in a very happy situation, in my opinion. And finally, can we ask ourselves that if we do some research on one more UHT or UHP or a Barrovian metamorphic occurrence, we calculate the PT condition, PT path of another area, because it was not investigated earlier. This is something that we often discuss, that since this was not investigated, I am doing that. The question is why it should be investigated. That's the question. Not that it was not done. Why we should look at it. And that is the point. And then we prepare 2 or 3 more pseudo sections. We do some uranium plate dating, but okay, we can do these things, we can write papers, but are these things going to excite people? That's the question. Will the subject advance in this way? Will the necessary impact will be created? I don't know. Some use-inspired basic research can help to draw funds in view of the fund crunch that we are having today. The question is that it's a common practice in engineering discipline and other places in the world to have 2 parallel projects. want to get the fund to do consultancy and other things and use that fund to sponsor PhD students and do basic research. So these things can be done easily. I know of my seniors in America that they draw fund from NASA to do some work supporting NASA's mission and then use that money to sponsor PhD students to do their basic science research. So it's possible if we marry these two ways. And then I think that one of the focus should be the critical minerals because we are the best person to use petrological principles to address the major concerns today, the water, energy, resource, and environment. Take the resource one here. That's the critical minerals. Now, the study of critical minerals involves mineralogy, geochemistry, and petrology to start with. Finding another deposit or exploration of the deposit is a different discipline, I know. But at least we can understand using these basic principles that how and where should we expect critical minerals to occur. So that way we can work on these things. So this is my 2 cents about what we should do. And this is not a church, so I'm not giving any sermon. So take it or throw it, doesn't matter, but this is my 2 cents about what we should do. Thank you very much. Do you have any queries? I don't think that I have raised any curiosity. My biggest rival.
Thank you very much for that, saying that. But the thing is, I just wanted an example of what you consider to be use-inspired.
Use-inspired means that it is useful for the 4 different things that we are bothered about: the environment, energy, resources. Energy means sedimentologists can work on the liquid energy, we can work on nuclear energy. So those things which are actually necessary for the society to move forward. So it is use-inspired basic, but it's not applied research. Applied research means that you have to use this basic information to find a new deposit and then you have to exploit that deposit. So those are applied research. So I have not talked about that. I think that tomorrow we will discuss. Are you satisfied? Thank you.
Thank you, sir, for such a good talk. And directly we are moving forward to our next session. That is session 7, will be chaired by Professor Somnath Dasgupta and Professor Shankar Bose. So, please take the floor.
Good morning, everybody. So I start playing a different role now, along with Professor Shankar Bose. So we have the papers. The most important thing is that we have to keep that time. Most important thing. And the first paper is for 20 minutes. The other 3 are for 15 minutes. So for the 20-minute paper, I will stop Professor Shantanu Bhumik after 16 minutes. And he must finish within 20. And for others, we will stop after 12 minutes, so that we can have some discussions. But please remember that we have to maintain the time schedule, otherwise it will be snowballing into a big delay at the later stage. And the Magmatism people did a very nice job by maintaining the schedule, and the Metamorphism group cannot lag behind. So, so with these words, I invite Professor Shantanu Bhumik to talk on pulse tectonism. I think he can talk a bit better than me. Thank you.
So your time starts now.
Thank you, and thanks to Chalapati for inviting me. I think I am audible now. So thanks to Chalapati for inviting me to present this work here. So my job has been made a little bit easier after Professor Dasgupta have introduced the basic issues that are attracting the geosciences in the coming decade years. So I will talk here about a type of tectonics called pulse tectonics, and I will show you how this kind of recognition in the natural rock record. So I will show you that the recognition of this special type of tectonics called pulse tectonics, how they help us in knowing how tectonics and plate tectonics has evolved over time in the geological time scale. Now, where are the records of tectonics very well recognized here? And these are essentially in the mountain belts here, which are formed during orogenic processes and convergent plate boundaries here. And I give here two examples here. One from Arunachal Himalaya, which is the Himalayan orogenic, the product of Himalayan orogenic, and the other is in the Indo-Burmese ranges. The example is Nagaland here. They are architectural examples of two fundamental types of convergent plate boundary processes, one involving continental collision and the other involving oceanic subduction here. And the locales of continental collisions and subduction tectonics in a modern plate boundary setting is shown in this geological map. And these two cartoon diagrams tell us about these two fundamental types of convergent plate boundary processes here. Now, one of the things that where we should see this record here of the different types of rock archives, metamorphic rocks are ideally suited in the sense that these are direct monitors of material transport inside the planet Earth. And if we track their transport and recognize the thermal and baric evolution in the process, we see that metamorphic PT paths, if these are reconstructed, they tell us about tectonics. And there are two ways that metamorphic PT paths can be recognized. One by forward modeling method, by thermal modeling, by solving an equation like this. And the second one, using natural rock examples, by seeing reaction textures, applications of conventional thermobarometry and feasibility of modeling, you can land up in recognizing metamorphic PT paths. I am showing you two fundamental types of PT paths from works by your students. One in the Nagaland area, the Nagaland eclogite. So this one here, and this is a Mesozoic age tectonics, and the second one is shown from the Central Indian tectonic zone. This is in granulite facies rocks here. Both shows clockwise PT paths here. And you see that their thermobaric ratios at metamorphic peak, they are different. They tell you about the subduction type, oceanic subduction type metamorphism here, and these are continental collisions here. Now, one of the things here is that this type of PT paths are generally recognized from the metamorphic rock record. They have a single cycle of heating cooling and single cycle of burial and exhumation. And we generally tell that these are the products of single orogenesis, single cycle orogenesis here. But if you see increasingly from the metamorphic rock record, we recognize the PT paths are non-linear. So these are examples from two belts here, one in the Bohemian Massif and on the other one is Siberian Massif, both in the Phanerozoic, one in the Paleozoic here and in the Mesozoic here. They shows the PT path have different types of history here. This is one cycle, burial, heating, and then exhumation. Then you see again in later orogenic heating in both cases. So the PT paths are not monocyclic. So what it tells us is that it has implication in tectonics, and I will show you shortly the implications of time scales of tectonics. So this one recognizes a tectonic transition from initial subduction to late orogenic heating here. And how to heat? You require some sort of mantle scale thermal perturbation. And there comes the importance of slab rollback and slab breakout scenarios. We do not pinpoint, the petrologists are unable to pinpoint which one is responsible. But these two fundamental scenarios tell us that you can have mantle scale perturbations that can affect a rock or setting like this. Now that is another important aspect. Apart from tectonics, the important thing here is that you have time scales. So if you have seen this particular part in red, this is a relatively long-lived orogenesis here. But if you have short-lived thermal pulses, then it is important that you can distinguish that there are several short-lived thermal pulses, and the important thing here is that the cooling and exhumation history becomes significantly different than what we assume in, say for example, in long-lived orogenesis. So this is the diagram that I have taken from Simon Howell's work in Element. So this tells you how temperature time pulse can be derived. Zircon is a mineral, all we know now, is an excellent geochronometer and also a thermometer here. And you can use zircon developed at different stages, and you can determine time as well as temperature to derive a temperature time pulse here. The problem here is that if you have an orogenesis which is multicyclic, pulsating, and it involves temperature in excess of 900 degrees Celsius, it has problem. One problem is that it is very difficult to regrow zircon in dry residual granulites. So for example, during this heating segment. Secondly, there are error in uranium length zircon dates, so 10 to 20 million years in generally, and it cannot resolve very short-lived metamorphic pulses here. And the average time integrated cooling rate essentially you will get, if you do uranium length zircon geochronology, you will have generally an average time integrated cooling rate. What is the solution then? So diffusion chronometry has emerged as a potential tool to discriminate between very short-lived thermal pulses. Why? The diffusion is a very widespread process, and the time scales can be directly related to the changes in pressure temperature evolution. It's a continuous process, and the resolution of time scales is independent of age. I give you an example with a garnet orthopyroxene exchange reaction like this, and you see here that, say for example, if the system is at equilibrium at 1000 degrees Celsius, the composition of garnet and orthopyroxene will be given by distribution component. And let us see, this is the composition at equilibrium, garnet orthopyroxene homogeneous. So if it is at 650 degrees Celsius, it is still at homogeneous composition of garnet and orthopyroxene here. But if there is a cooling history here, what will happen here, that there will be diffusion of MgFe between the two minerals, and will produce a diffusion profile like this. And if you solve these three equations here, and there are numerical codes that have been developed, and if you know measure this diffusion profile, if you know the diffusion coefficient and initial and boundary condition, it is possible for us to know the timescales over which the diffusion has occurred here. So what has happened here is that if you have a pulsating metamorphism, so it is possible theoretically that you can have three different profiles that have developed and that have different duration memory that is there. And if you can model these diffusion profiles, you can have theoretically possible the time scales along this entire scale here. So what I will do here is that I will try to give you examples from the Indian metamorphic rock record by our group. So two examples in some details, one from the Central Indian tectonic zone at around 1.6 GA, and the other, say for example, from the Phanerozoic one in the Nagaland ophiolite belt. So I will show in some details what here. And the third one, so I will just tell you about the results here from the Western Dharwar Craton. So this is from the 1.6 GA ultra high temperature granulate fishes, ultra hot horizon, at the southern margin of the central Indian tectonism called the Bhandara-Balagat granulite domain here. So what we have done here, we have found a sample with an exceptional memory of multi-stage metamorphic history and different generations of garnet and orthopyroxene growth. So from the scale of an entire thin section, it is possible to develop a metamorphic stratigraphy here involving different metamorphic cycles here. So this has been published in EPSL in 2017. I am not telling in details here. I tell you the end results of this is that you have a very non-linear, complicated pressure temperature path of evolution where there are 3 cycles of metamorphism, M1, M2, and M3, that we have been able to distinguish here. And what we have done here, we have taken profiles that have memory of different stages of these metamorphic cycles, and we have modeled this. So for different stages here, so you see these arrows tells you the time scales for the M3P to M3 retrograde, and this is the other part here. And this is the largest garnet here, which has a memory of from the M1 event to the M3 event here. And what we have done here is that we have been able to get timescales for this entire PT path here. So what are the major takeaways? The orogenic timescales is 50 million years, which has been commensurate with what we have found from uranium-lead zircon and monazite dating. Important thing here is the resolution of the timescales is of 1 to 2 million years duration in hot and old rocks, and there are multiple thermal pulses, and these are, the first thermal pulse is hottest and also longest here, and later thermal pulses are progressively cooler here. And you can relate it to tectonics here. The important thing here, you can have pulsating slab rollback and advanced models that can tell us about the tectonics at 1.6G origin here. Now I give you another example from the Manipur ophiolite belt here. These are another type of rocks. These are metamorphic soil rocks here, which has a memory of the initial stages of subduction here. So I have taken a sample from the northern part of the Manipur ophiolite belt, and these are mantle periodites and metamorphic soil rocks. They are in contact. So we have taken a sample which is just at contact with mantle periodite, and these are the 3 representative textural domains here. So these are peak assemblage here, coarse granoblastic assemblage. Then you see that titaniferous hornblende that has produced here. And finally here, you have hornblende plagioclase symplectites that are produced due to reaction between this titaniferous hornblende here and garnet. So what you have here is that if you connect the temperature conditions of peak and 2 generations of hornblende growth, you have a very simple cycle of retrograde cooling and exhumation. But important thing here is that if you have carefully looked, that then there are records of this hornblende that is produced here. This hornblende is rimmed by a symplectic corona of 2nd generation clinopyroxene, ilmenite, and plagioclase, and that tell us a second post-grade heating event here. And when you take into consideration, then this path, and this path is intervening by a second post-grade heating event. So you have again a pulsating metamorphism here. And what you can do here, you can model the diffusion that has been developed here, and you can get time scales here. And these are the time scales that have been developed for different types of different stages of evolutionary history that is recorded here. And this is the temperature time path that has been developed here. So interesting to note here that the cooling rate is absolutely high, it's exceptionally high, not recognized in the metamorphic rock record here. And you can also use this you can use this memory here to tell you about the different stages of subduction history here. I am not going into details, I can discuss if time is there. So in nutshell then, that if you have the time scale that you see here, this is the temperature time path that has been developed here. In both cases, 1.6 and the Mesozoic here, you have a pattern of decreasing temperature here. But if you see here, in the 2.5 Ga Archean Proterozoic boundary here, so we have also been able to develop tectonic transition across Archean Proterozoic boundary, and we are able to find out pulsating metamorphism here. I have used this diagram from Priyodoshi's work here, where he has shown that the cooling rate, when plotted against the geological time scale, or the time here, there is an indication of with time that cooling rate has increased with time, and that is related to tectonics here. So we have here given time scales from cooling rate data from, say, for example, from Shampriti's work here at 3.1 Ga Kur granulite massive, our work in the high grade and low grade domain of the Sarguts and the Central Indian tectonic zone, and say, for example, from the Manipur ophiolite belt. So these data will further improve our understanding of how cooling rate data has evolved over time here. Now the question is that where do we recognize pulsating tectonics? One of the things here is that in oceanic subduction setting, where you have this particular the particle path that you see here in the footwall side, you can have pulsating metamorphism that can be recognized here. And the more importantly, that, say for example here, you can have a particle path which can change from footwall side to the hanging wall side here. And what you can have here, you have a post-grade barrier heating path here, and you have an exhumation and cooling followed by reheating here. One of the important thing here for us metamorphic petrologists, tectonic modelers here, those who are working in Precambrian orogenic belts in granulite facies terrain, remember that with the results of thermomechanical modeling, we should be very careful to interpret the PT conditions with geodynamics. There is large possibility that many of these pressure temperature, high temperature, ultra high temperature metamorphism can, the final stages were in the hanging wall side, but it has a memory in the footwall side here at some stage. So I acknowledge my PhD students over the years, my collaborators, and generous funding from different funding agencies in the country. Thank you very much.
Thank you very much, Shantanu Bhumik. So we have two questions. We can have two questions. Rest over coffee. Yeah, please.
Thanks, Professor Bhumik. It's an excellent work and a good presentation. I would actually, I would like to know any particular evidence we can give for exhumation, mineralogically otherwise.
So exhumation is where you have mineral transformations, you have symplectite textures. Those minerals which are formed due to breakdown of garnet, they are stable, they have higher volume, molar volume, and they form at lower pressure. So that's tell you directly about the exhumation here, that they have once, if you calculate the peak pressure temperature condition, if you calculate the pressure conditions during garnet breakdown, and if you see there is a difference in pressure, you can tell that these are products of exhumation.
For example, suppose we have some kind of, we deal with fluid inclusion, so that is the reason I asked this question, that can we get some pure CO2 inclusions, which probably could be an indicator for such exhumation?
I have not worked in fluid inclusion, I will not be able to tell about, but
pure CO2 conditions could
what you can do here is that you can relate certain textures which formed along fractures, which can be related to garnet breakdown textures. So along fractures, if you can track certain new fluid inclusions that have been developed here, you can directly relate it to exhumation phenomena here. Okay.
Right. Okay. Thank you.
Thank you very much. And so, rest of the questions, please, over tea, because we are running short of time. And I hand over to Professor Shankar Bose to conduct the rest of the session.
Thank you. We have a second speaker here, Dr. Tapobroto Sarkar. He will be talking about the petrogenesis of mid-Neoproterozoic Charnockites from Madurai block. Over to you, Dr. Sarkar. Yeah, Dr. Sarkar, you have 15 minutes time. We will stop you around 12 minutes.
So you don't see the time. Okay. Good morning, all of you. So I'll be talking today on the petrogenesis of some Charnockites from the Madurai block in southern granulite terrain. We have done from geochemistry, geochronology, and some geodynamic modeling. So this is a work at the interface between metamorphism and magmatism, where I'll take you through. So let's, as I'll talk about the Charnockites, so first thought that let's be all on the same page on what is Charnockites. So as you all, or many of you know, Charnockites were first described by Holland in 1990 to describe the Madras hyperstearine bearing granitic rocks for the Madras Charnockites. Later, over the next decades, it has been used for various to describe a much wider variety of rocks. And then Frost in 2008 gave a definition after a review, which is an OPX-bearing granitic rock that is clearly of igneous origin, or that is present as an orthogneiss with a granulite terrain where the origin of OPX is uncertain, which essentially means that the orthopyroxene in the granitoid rock can be crystallized directly from the magma, which occurs at high temperatures at low water activity, or by the dehydration melting of biotite and or hornblende, which occurs during granulite facies metamorphism and partial melting. Charnockites, of course, make up only a tiny fraction of the world rocks which are worldwide, but they are still interested in the Charnockite because they are commonly found in high pressure temperature regimes, and therefore they provide us a window directly into the process that occur into the deep crust, and they provide valuable information regarding the evolution of the granulite terrains. Now, in this work, we have used Charnockite in a sensolato way, where we have used OPX-bearing granitoids as Charnockites, not restricting to only granites. So Charnockites obviously are found in all granulite terrains, and southern granulite terrain out here is no exception. And we are fortunate, we are working in the southern granulite terrain out here. If you look at the map on the right, you will see that the majority of the rocks in the southern granulite terrain are either Charnockite or the retrogressed equivalents. Yet, the focus of the research in southern granulite terrain was mainly focused on ultra-high temperature rocks, which occurs only sporadically. So what we thought is that we also look, along with those classic metamorphic work, we also looked at the Charnockite and the formation, which would give us an idea how this terrain evolved. So we went into the Madurai block. There are three different blocks out there. The Madurai block, which is the largest block in the southern granulite terrain, it preserves a variety of rocks, dominantly Charnockites, and the age ranges from 2.5 billion years to 0.5. And it also reports very ultra-high temperature conditions. So the Charnockites out there, there has been some studies on the Charnockites or how they were formed, but the interpretations are very contrasting. For example, Santosh and his group envisaged a continuous and multiple phases of magmas that were in place throughout the early to mid Neoproterozoic in an arc type of setting. On the other hand, Brandt et al. In 2024 said that extension-related origin for this voluminous mid-Proterozoic A-type Charnockites. Therefore, what you see is the contrasting interpretations. However, none of these interpretations were established through any forward modeling. Okay? So what we have tried to do is, through a forward modeling, try to understand how these could have formed. So there are two major outstanding questions which I'll talk about today. That what is the age of the dominant granitoid magmatism in this region, because there are several pulses. and what is the tectonic setting for these granitoid magma generation. So with this, sorry. So with this motto, we went to the field. We looked around, did a lot of field trips and field studies, looked around this region, and what we dominantly found that there are different generations of Charnockite what we see. The most volumetrically, the maximum ones are these massive or relatively massive looking Charnockites, which are volumetrically much more. They are medium grain sized, and in most of the places they are intruded by this pegmatoidal variety, which has much larger grain size compared to the former. And in other places there is a pink granite, clearly pink in color, which is intruding in definitely the massive ones and sometimes the pegmatitic ones as well. If we have a closer look, you can clearly distinguish the difference in the grain sizes as well. So the crystallization, for the crystallization and the metamorphic ages, we looked into the zircons of these. Clearly there are elongated oscillatory zone magmatic zircons, which are resorption places developed after developing metamorphic rims. So the spot edges from the magmatic regions define discordia with upper intercept age of around 826 million years and the lower intercept of 537, which also matches, the lower intercept matches with the spot edges, concordant edges from the metamorphic rims. So what we interpreted is that the age of the emplacement of this is around 800 and the metamorphism is around 530 million years. And if we look at the pegmatoidal Charnockite, they are definitely younger. They show concordant ages of around 580 million years and the same metamorphic ages in both the cases. If we look under another sample, the same thing, the same results that we see, and the pink granite, they also shows concordant age, which is the age of the emplacement, and the rate of recrystallization, which has the same age of metamorphism. So what we take away from the chronology study is that there's been extensive magmatism around 830 million years. There's another episode of felsic magmatism and a high-grade metamorphism around 530 million years. So then we did a basic geochemical study of these. So we have divided these Charnockites into basically intermediate and felsic just for the sake of visual display. So we have our around 30 samples we analyzed, and also what we did is that we compiled all the data of the previous published data and estimated or plotted this in a Garnet density estimate to visualize the previously published data. So what we take away from here is that these rocks are dominantly granite to tonalite, and they are both ferroan and magnesian in character. And they are dominantly meta-aluminous to extending to some paraluminous, dominantly calcic to calcalcalic, and this also shows meta to paraluminous character. If we look at the trace element, the trace and the rare earth element behavior, so they show an enriched LRE, a flat HRE pattern, negative Neoarchean anomaly, and they plot in the fields of volcanic arc granites in the tectonic discrimination diagram. So till this point, it is a routine geochronological and geochemical work, but what we have done additionally is the modeling, which I'm come in the next slide. So what we see is that modeling can shed some extra additional information, and what helped us in the modeling is the data from Thompson and Dave, which shows that these neoproterozoic granites show a negative epsilon hafnium value, which indicates reworking. So what we did, is a petrological modeling and a geochemical modeling in an open system using the program called Crust. So let me first explain what we are doing. So we took a source rock and started increasing the temperature at constant pressures till the rock starts melting. Now when the melt reaches around 10%, this melt is extracted out of the system. We retain 1% of the melt in the system, which mimics the natural scenario. Then again the restite is again melted, and again when this condition of 10% melting comes, the melt is extracted, and this continued till around 1050 degrees centigrade. Now we have taken two source rocks, one is a mafic, one is an intermediate from the composition of the lower crust by the review of Hacker et al. 2025, and we are showing two pressures 9 and 11 kilobar, which are actually marked in different colors, and the sources are marked in different symbols. So additionally, what we have done is that another experimental thing is the restite assemblage entrainment, which essentially means that when the melt is extracted out of the system, some small percentage of the restite gets entrained into the melt as suspended particles. Okay? So we have taken a nominal value of around 5 wet%, and this concept is in line with many experimental studies which shows that restite entrainment is common in felsic magmatism. So let's see, and then what we have done, we have used the composition of the melt extracted, the composition on the mineral assemblage in the restite, and calculated what would be the trace element concentration of the melt as well as the with the entrained one. So now we plotted the results on the same geochemical plots along with our original data, and what we see is that if we do a pure melt loss, which is the case 1 in our, so the data is only in a restricted space and does not do not explain the entire part of the data. So what we did is that we tried with some, for example, what you see, it's dominantly ferro1, and it does not explain the magnesium character. So what we did, we tried with the restite entrainment, and now what you see out here is that the stretch of the data is much more, and it's much better explain the natural data, our data, as well as the compiled data, what we have so far. So what we take away message is the restite assemblage entrainment is essential to explain the magnesium character of the Charnockites. And this goes for the other plots as well. We can discuss, we can see or discuss it later, and it can explain everything, as well as the trace element, the trace and the rare earth element plot, where you can see the prominent patterns can be explained through the restite entrainment and the modeling approach that we have taken. And the same thing out here as well in the tectonic discrimination diagrams. We can, the modeled melt composition lie in the field of volcanic granites in these diagrams. So what the major conclusions is that extensive felsic magmatism occurred around 830 million years. The Charnockites show a wide range of composition from ferro1 to magnesium, alkali calcic to calcic, and meta-aluminous to slightly aluminous. Pure melting of the mafic to intermediate lower crust at pressures 9 to 11 kilobar could not produce the entire range of the composition. However, minor amount of restite assemblage entrainment in the extracted melt could produce the composition variability. So the takeaway message is that melting of the Proterozoic lower crust occurred at a relatively dry conditions at pressures 9 to 11 kilobar. Juvenile Neoproterozoic arc type magmatism in an arc setting is not essential to explain the Charnockite composition, which is in line with the zircon-hafnium isotopic signatures. The melting of the lower crust most likely occurred due to asthenospheric upwelling in an extensional setting. And the present work is the first comprehensive forward modeling to explain the petrogenesis of the mid-Neoproterozoic Charnockites of the Madurai block. With this, I thank all the stakeholders, especially the students, and thank you all for your kind attention.
Thank you, Dr. Sarkar. We have time for one or two quick questions, if anybody wants to.
Nice presentation, Tababrado. So I just wanted to know, what is that extensional setting you point out?
Sorry?
What is that extensional setting you pointed out?
We have kind of correlated with the breakup of rhodinia.
Excellent.
Because there are also alkaline rocks, which I did not put it directly out here, of that age.
Though you have pointed, though your work now presently you have concentrated only on the northern part, But I should say that we have got this 800 extensively
Yeah,
everywhere.
we have, we have done entire
Till-
Madurai.
In Madurai, you have got this 800. You have got, other than Charnockite, pegmatite, Charnockites, you have got a lot of granites
Right,
as
yeah.
well. So it's a huge,
Huge
normally
one. And
it was
that's
a
why
huge
we
one.
wanted to put it through the modeling, because
yes.
the archetype signatures can be generated through remelting as well. It doesn't always require an arc setting.
Excellent work. Thank you.
One.
Did you use the trace element KD values for typical of paraluminous granitic melts?
We used for metaluminous melts as well.
Okay.
The KD values we also actually changed as well, depend on
Yeah,
the
because there is a
for
large
the
variation
silica
in the
content,
available data set.
We have used changed it with the basic of the silica contents as well.
Just one.
What is the UHT signature in your Charnockite?
These Charnockites? Yeah. So this the UHT signature of the Charnockite is the formation of the garnet and orthopyroxene. So the orthopyroxene we have seen that in
Alumina content.
alumina content in these the orthopyroxenes which we think later. I don't remember exactly, but around not high as the pellite, but around 4% or something like that. Yeah.
Okay, we can discuss it later. So thank you again. Our next speaker is Dr. Aliba Ao, and he will be talking about the Neoarchean Gadwal Greenstone belts of Eastern Dharwar Craton.
Okay.
Dr. Aliba, you have 15 minutes time. We will stop you around 12 minutes.
Thank you, sir, for the time. Good morning, everyone. Before starting, I would like to acknowledge University of Hyderabad Institute of Eminence project that has supported and funded this project. And the title of my presentation here is Metamorphic History of the Gadwal Greenstone Belt, Eastern Tower Craton, and its tectonic implications. Okay. So this is the geological map of the Tharwar Craton. We have seen all yesterday, but just to give a perspective of my study area, I will explain in some detail. And these are the some rock types and the edges. I have not given the references here for the sake of the clarity. I have given at the end of the slide the references that I've some selected references that I've referred. And if you see the Tharwar Craton, it is divided into 3 blocks, the western block, central block, and the eastern block, based on tectonic fabrics data, geochronology, metamorphism, and isotopic data. And this is the western Tharwar Craton, and they are dominated by DDGs and greenstone belts, the older Sargur group, and the younger Tharwar Subur group. And the eastern margin of the Chitradurga shear zone marks the boundary between the western block and the central block. And if you see the metamorphism, the oldest metamorphism that has been recorded from the greenstone belts of the western Tharwar Craton is at 3.1 billion years by Dasgupta et al., 2019-22. And they have recorded some form of horizontal plate motion that is formed, that is metamorphosed this greenstone belts. And further subsequently, as previous speaker, Professor Pomik, has highlighted out, we have bared metamorphic belts that are developed from this western block during the Archean to Neo-Proterozoic boundary. So coming to the central block, we see still DDGs, but we also see transitional DDGs. And then we see the greenstone belts, which are much linear, almost trending north-south direction. And we also see bimodal edge volcanics, mafic and felsic volcanics as well. And if you see the metamorphism, the paleolithic rocks have been recorded, which is metamorphosed from granulite to UHT metamorphism by Jananda et al. And Kempf et al. Jananda et al. 2011 and Kempf et al. 2024. So they have recorded granulite to UHT metamorphism at around 2.6 billion years. And the greenstone belts, the eastern margin of the Kadri greenstone belts and the Hungun Gustagi greenstone belt marks the boundary between the central block and the eastern block. And in the central block, here we see more younger gneissic tonalite to granodioritic rocks and diadexitic gneiss to alkaline granite rocks also. And here also we see bimodal edge volcanics, both felsic and mafic volcanic rocks as well. But here the metamorphism is Scandi, the edge of metamorphism is Scandi. Some people have recorded from Hatti and some from the southern Golar greenstone belts. So through monazite edges and through zircon edges of the gneissic rocks, they have dated the age of metamorphism at 2.5 billion years ago. So that is the history. And this is the study area from where I have reported this work. So this is a detailed map of the Katwal greenstone belt. And if you see here, we see a lot of association of the volcanic rocks, ranging from metabasalt, meta-andesite, meta-dacite, meta-rhyolite, meta-dufs, agglomerate, and so on. And also adagites, rhyolites, adagites and poninites have also been reported from this Katwal greenstone belt. So, and based on geochemistry, and this Katwal greenstone belt has been inferred to have formed in an intra-subduction zone setting by different authors. So my curiosity was whether there's any imprint of metamorphism preserved in this greenstone belt, and what can it tell about the tectonic evolution history of this particular terrain. So that was the aim. So these are some of the field photographs here, and in the field they range from darkish brown to blackish in color, and they show very steep foliation. We can see here, and this is an interpretative geological cross-section across this area here, XY line here, and then they showing the steep foliation nature of the greenstone belts surrounded by the granitoids here. And this is the story of the metavolcanic rocks. They are mostly dominated by hornblende and plagioclase with some minor quartz, as well as some ilmenite, some apatite, and even relic clanopyroxene as well. Some are strongly foliated, and some are mildly foliated. And this is the chemistry, mineral chemistry of the amphiboles. So compositionally, they are calcic amphiboles, and they range from ferrohornblende to magnetiohornblende to ferroactinolite to actinolite to tremolite in composition. And if you look at the feldspars, mostly they have a wide range from albite to pythonite. And one basalt has also some microcline as well. So this is the X-ray element map of a hornblende. So this is the aluminum map, and this is the titanium map. And the aluminum as per formula unit is shown by these points here. So this is taken from core to rim. And if you see the aluminum content, it increases from core to mantle, and then from mantle, it shows slight decrease in aluminum content. And similarly, if you see the titanium content, it shows it increases from core to mantle, And then from the mantle to rim, it shows some slight decrease. So some kind of a mineral zoning is preserved in this hornblende composition. The next one is also an X-ray element map of calcium map of a plagioclase. So this is the backscattered electron image showing you the boundary of the plagioclase grain. So this is the boundary. And then we also see some zoning present in the plagioclase grain as well. So from core to mantle, it shows increase, so reverse zoning. And then from mantle to rim, it shows some slight decrease in anorthite content in the plagioclase. So I've used these mineral zoning patterns in amphibole and plagioclase to constrain the big or the metamorphic conditions of this cut-wall greenstone belt. So to do that, I've used pseudo-section modeling techniques. I've used Purple X in the system NCKF Mastio system. And the composition is shown here. And this is the BD pseudo-section that is calculated for this rock. And we see the big metamorphic assemblage present in this field. And this is the isoblate lines of anorthite content in plagioclase and titanium content in amphibole. So I've used the core mantle rim variation in the plagioclase grain, and I've used this isoblate intersection of these points to construct a prograde PD bud and a retrograde PD bud here. And the metamorphic conditions for this prograde metamorphism is recorded at around 5.2 kilobars and around 635 degrees centigrade. Big metamorphism in subsolidus condition at suprasolidus condition at around 5 kilobars and 750 degrees centigrade, and retrograde metamorphism down to 4.3 kilobars and 690 degrees centigrade. So overall, it shows a near isobaric heating prograde bud, and if you connect all the prograde peak and retrograde metamorphism, we get a nice clockwise PD bud of metamorphism from this metabasalt. So, so this is BD facies diagram showing you the field of this metabasalt, the BD bud of this metabasalt, and it shows that this shows high thermobaric ratios at around 1,500 degrees centigrade, which is very common in Neoarchean terrains. So I did some rock chemistry to understand the magmatic evolution of the rocks. So briefly, I'll go through this. So mostly they are basaltic, tholeidic basalt, and we see some. So we see some spread here in silica content. So when we plotted in the immobile elements, so they mostly plot in the basaltic field. And we also used trace element chemistry of the metabasalt. So two trends it shows. So most of the basalts, they show flat trend, which resembles a morph basalt. And some of the basalts shows enriched LRE content, and which may be due to enrichment, which is very similar to E-morph type basalt. And then this is the trace element chemistry or spider diagram, which shows depletion in high field strength elements such as niobium, zirconium, titanium, and so on, and slight enrichment in large iron lithophile elements like rubidium, barium, and strontium. So, yeah, sure. So these are routine diagrams to decipher the tectonic history or the tectonic setting in which those rocks are formed. And this diagram shows you that they are formed in a plate margin basalt. And this diagram shows you that they are part of the N-morph type and volcanic arc basalt. So what type of basalt? We try to decipher it through this diagram. It shows arc type. and mostly in island arc basalti. And here in this morph, most of the samples plot away from the morph array, indicating that much of this has been affected by some form of subduction process, as we have seen in the LRE enrichment and large iron lithophile element enrichment. So in summary, these edges are not mine, so I have adopted from the published literature. So it's around 2,740 to 2,640 million years, the Cutwell Greenstone belt formed by intraoceanic subduction system, which was followed by transitional tonalite, tronzomite, diorite. And slightly following this, there was a slab break-off at around 2,640 million years. And because of this slab break-off, there's Mendel upwelling. And that Mendel upwelling generated the heat for the metamorphism, which is shown by this almost isobaric heating of these metabasalt rocks here. So overall, this inference is consistent with the evolution of greenstone belts in a hot origin, which is subdued topography and then near isobaric heating of the volcanic rocks. Yes, thank you.
Thank you. Very nice work. If you have some queries, please. Sure.
Thank you, Dr. Aliba, for your lucid presentation. I have only one small question. In the plagioclase classification diagram, you have shown your plots have fallen from this end to that end, Pythonite to albite even.
Yes.
What is the reason for that? Thank you.
So one of the reasons is because of the mineral zonation. So as you know that as temperature increases, your anorthite content in plagioclase increases. So if you see a plagioclase grain, you will see the imprint of those high temperature metamorphism in the plagioclase grain. So that is one of the reasons. And another reason is also this plagioclase plots are from different samples. So some have been metamorphosed at low temperature as well, and some are part of the high temperature metamorphic rocks also.
So, yeah.
Dr. Aliba, I missed first part of your lecture. I was away.
Okay.
Just I recall in the Gadwal Greenstone belt, Dr. Manikyamba et al. Nakvi, they reported boninatic magmatism.
Yes.
And they inferred very shallow suprasubduction type of setting.
Right.
So your PTs, do they reconcile with that? Because they seem to be of much deeper type of setting. Huh?
No, actually, what metamorphic PT condensation tells us, it is a very shallow crust at around 5 kilobars, and then after subduction there was a slab break-off, and that Mendel upwelling that provided the heat for the metamorphism of the. So we also agree with their conclusions that it was an intraoceanic subduction system initially. So yes.
So you have. You can. It's better to discuss. Yeah. Any query from the students? Just one. Yeah.
Thank you, Dr. Aliba. It was a wonderful presentation. I have one question from the PT pseudo section. You have modeled an isobaric heating path, and that also you have you have an explanation. You have a tectonic explanation for that. My question is, when you are isobarically heating the rock, any specific reason why you didn't consider melt loss?
Melt loss.
Yeah.
Yeah. So if you've seen properly, the pseudo section, it falls in the liquidous, it has crossed the liquid line. So melt is also generated. So when I calculated the amount of melt, it was not substantial. And if you see the texture also, we see a slight reaction rim around the hornblende grain. So embayments of hornblende. So that is most likely the textural evidence of some form of melt. But based on our pseudo section calculation, the amount of melt is not significant. So that's why we have not considered that one.
Well, the rest of the questions can be asked during the tea break or lunch break. So, thank you.
Thank you, sir.
We conclude this session.
Thank you, sir. Now I will request our directors to hand over memento to Professor Shankar Bush. So now it's time for tea. And after tea, we will start our next session by 11 a.m. And tea is arranged in the outside. Thank you.
Next session, Chairman is Shaibal Gupta. One person is missing. We'll have somebody else. You can think of
So that's it.
Nasipur. You keep.
You are the hardcore, or your parents. Yes, AC chapter, he says is the old. Here the body with college. Your parents will realize.
a dusty plain in northern Argentina, some of the work to shift to a green energy future is taking place. These black tubes fill a massive tank with salty brine sucked deep from the ground below as part of an 870 project in the province of Salta. The brine contains this white metal.
But the Epidote Mineralization, no, we want to
So now we are going to start our next session. That session 8 will be chaired by Dr. Nasipuri and Professor Shoibal Gupta. So please take the charge.
Okay. So we begin the post-tea session. The first talk will be by Professor Shankar Bosch of Presidency University. So Shankar is all set. So you have 20 minutes, 18 of which you're allowed to speak.
Okay. So very good morning to all of you. I'm very grateful to Professor Chalapati Rao for the invitation to come here. And the paper I will present here, it is about fluids, late stage fluids, and how it affects the textures and modified the chemistry also of a rock which has undergone very high temperature metamorphism. Actually, this is a work which was done by my master's student Shubhodip and Shayantika. Both of are now not in presidency. Shubhodip is in abroad doing PhD, and Shayantika is in ONGC. So on their behalf, I am presenting this work. As the title shows, I'm talking about fluid. So the key question that I will be asking and try to answer during this presentation, one is that what happens to a lower crust after it undergoes anomalous thermal conditions, what we term as UHT metamorphism, because as Professor Dasgupta showed in the morning that there is an immense contribution from the Indian geoscientists on this topic, UHT metamorphism, and one particular area where UHT metamorphism was described from India is Eastern Ghats belt. So I will touch upon that part. And the second issue that I want to emphasize here, the whole role of metamorphic fluids in such a scenario, and what kind of fluid we are talking about, and what kind of changes that we witness, which fluid actually, the compositions of what kind of fluids, and what channel ways, how these fluids actually invade the rocks. So these are the key questions that I want to address here. And then the question is, were these fluids related to the orogenic processes? Because we have in these places in India, we have very strong imprints of large-scale orogenic processes, and those processes are somewhat related to the amalgamation of different blocks and assembly of supercontinents. So whether these are actually spatially or temporally related or not. And finally, do we have a case study? Because all these questions can be answered if only we have some areas where this can be found. So let me just first talk about something about the fluid changes that occur in deep crustal. There's a fantastic paper came in 2018 by Craig Manning, where they show that this metamorphic fluid can be perceived in a tetrahedron where the components like H2O with some mixed solids and carbon dioxide and the brines, and the fourth dimension is the rock forming mineral. So these fluids actually play a role in deep crustal rocks, and you have this H2O is always there in the mix, and H2O rich fluids along with other components like CO2 and salts, they provide all necessary changes during metamorphic processes. And we focus on, in that case, we focus on mainly H2O carbon dioxide and hypersaline brine, and also some alkali solutions, because nowadays it has been found that these are alkali solutions are very important fluid components which changes different textures in rocks. And each of these species has own source, like say H2O, like from a granitic magma, basaltic magma, CO2 produce CO2, and this alkaline magma produce alkali solution, etc., etc. And these fluids, they bring about myriad changes in rocks which are often difficult to assess, and they pose ambiguity in constraining metamorphic evolution of a terrain. So let's focus on our study area. This is the broad geological map of this Eastern Ghats belt, where you have different crustal domains apart from different provinces. I am not describing it further. This is Visakhapatnam domain. This is Kharia, Rampur, Fulbani. This is mostly from the early work of Dobmeyer and Wright, and later works from our group and other people also found that these domains, they have some limitations. All of these domains do not have actual terrain boundaries, but for this work, I am just focusing on this Visakhapatnam domains. This is the broad geological history of the Eastern Ghats belt. We have several provinces. We have crustal scale shear zones, and this province was juxtaposed against two cratons, one in the Shinghum in the north and the Dharwar in the west. And this juxtaposition occurred during around 950 to 900 million years. Recent papers by Tavobroto's group also proved that. And we have both Greenvillian age and Pan-African age imprints in these rocks. And when you talk about the Greenvillian age, people used to talk about that Eastern Ghats and Rainer province of Eastern Antarctica, they evolved together as a single belt, like Rainer Eastern Ghats belt, REG, and they were part of the supercontinent Rodinia, but later studies proved that they actually were placed far away from the mainland Rodinia. That is a different story, and this Rainer Eastern Ghats origin is a collage of 900 million years age, and we see beautiful fitting of two terrains with similar pressure temperature history, and this is the possible, our recent work showed that this is the possible Greenvillian age suture that is found through the Mahanadi shear zone from our recent work or from our students. Having said that, we have Pan-African age in the Rainer Eastern Ghats belt, and just focus on the central part. This is from Ben Goscombe's 2020 paper, and they have shown that this 550 million year events occurred in the this Antarctica and Eastern Ghats South India region, and they call it basically a broad framework of Kunga origin. And in recent paper by Nathan Dasco, and they showed that this the Australian, Indian, and Antarctic regions, we have more evidence of events in the Meso-Proterozoic age in the Australian Antarctic region, and the more Meso to Neo-Proterozoic ages near the Indian part. So this is the region where you have 500 to 550 million years events. So it has been found that the evidence of this Kunga orogeny is present in the India-Antarctic sector with a strong metamorphic imprints on the Antarctic region. So the question is, what is happening in India? This is the two regions. One is the study area. One is the Salur area of the central part of the Visakhapatnam domain, and another is the Vijayanagaram area, also close to around 60 kilometers apart. And these two areas we have targeted. Actually, two students work in two different places. So we found different rocks here, and I am not talking about all the rocks. I am talking about the aluminous granulites. In Vijayanagaram area, this is a beautiful outcrop of this aluminous granulite, spinel cordierite bearing rocks. These occurs as a large enclave in quartzofeldspathik gneiss, what we popularly call leptinite. It's strongly foliated, and it shows characteristic blue hue due to presence of cordierite. And we have two occurrences in the Vijayanagaram area, and this is, I mean, quite well understood. And you can have very strong fabric here by alternate dark and yellow, white colored bands. The dark bands are composed mainly of garnet pyroxene, and the white bands are composed mainly of quartz and feldspar. In the Salur area, this granulite facies rocks, and this aluminous granulite rock over a 10 kilometers long stretch from along the east-west direction. And these rocks are both massive and coarse-grained, but Also, they show foliated magmatic characters, often diatic-citic, and this structure of melt migration and crystallizations are quite common. You can see at places this foliation looks like a protomyelonitic rock. So you have in these white portions you have evidence of melt migration and crystallization. When you talk about the microstructures and textures, the Salur Vijayanagaram rocks show beautiful textures typical of ultra high temperature metamorphism, where the spinel, ilmenite, these grains are surrounded by triple layer or double layer corona of orthopyroxene, sillimanite, and garnet, and this gives this ultra high temperature conditions, peak metamorphism with greater than 10% aluminium in OPX, and these reactions where this explaining this texture shows the near isobaric cooling, and followed by this sillimanite and the garnet somewhere here. These two minerals reacted to form this delicate intergrowth of spinel and cordierite. This reactions is a product of near isothermal decompression, and we found some evidence of later reworking in the quartzo-feldspathic portions, where you have delicate intergrowth of quartz, potash feldspar and quartz, which we think as the product of reworking and a second metamorphic event. Also here we have reported occurrences of carbon dioxide rich fluid at the early metamorphic stage, that is M1 by Sarkar et al. In the Salur area, the textures are very complex. What we found that you have hematite, ilmenite minerals surrounded by garnet, magnetite intergrowth. What has been produced by magnetite-rich component in garnet, what we call skiagite, that broke down during the peak metamorphism. And here also you have the peak assemblage spinel, quartz, and similar orthopyroxene, cordierite, potash feldspar, and they also have high aluminium in orthopyroxene, where the similar kind of near isobaric cooling textures are produced. And you also have similar isothermal decompression textures, where sillimanite and garnet produce this spinel cordierite intergrowth. But an interesting thing is that we have another feature where you see these large cordierite grains here in the leucosome layers. They are breaking down into an intergrowth of orthopyroxene, sillimanite, quartz. The reaction has a flat TPDT slope, so this reaction can be crossed if you increase pressure along with temperature. So this is a heating and loading type reaction, what we term as the M2 event. And all these reactions were modeled using pseudo-section using the Perplex system, and it's a natural system. So sodium, manganese, all these components were considered, and using this proper oxygen conditions and H2O conditions, we found that this area is the peak metamorphic conditions, where you have all these minerals, spinel, orthopyroxene, all these things are common here. And using the isoplate diagrams from garnet magnesium number, OPX magnesium number, and modal volumes all concentrate along this region. So this is the peak conditions, and our interpretation from textures show that this is possibly the pressure temperature evolution. This is the peak. We don't know about the pre-peak condition, but either there is a cooling followed by a decompression or a decompressive cooling, and there is a possible reworking here, but we got only news about the retrograde part of this one. And this is the similar for the Salur one, and we have similar conditions, similar pressure temperature history, where the M2 event is very strong. Now the question is, after these UHT things, what happened? We found evidence of fluid movement in this region. This is the albitite veins and quartz regions, and we found these veins are intersecting somewhere, like say pseudotrachelite veins. These are definitely fluid enriched, and in Salur area we found this kind of patchy occurrences in the aluminous granulite. So these all are telltale features of fluid-induced metasomatic process. And to understand that, we made a thin section map, sodium mapping of this entire thin section, we found the patches of sodium feldspar here in different areas. And under petrography, you see that these albite veins in the grain margin in alkali feldspar grains, you have albite patches and calcite and chlorite, alkali feldspar breaking down to pyrophyllite and chlorite assemblages, and you have calcite and chlorite in the surrounding garnet. All these events suggest fluids were there. So let's look at the zircons. So we separated zircons, and all these analyses were carried out in ESSO-NCESS. And thank you for that. These are zircons from the VZM sample, only representative ones, mostly detrital in character, but we have some overgrowth around 1,000. And one spot only gives 500 MA events. And these red ones are the titanium in zircon thermometer, results of the titanium in zircon thermometer. For solid samples, we have a very strong domination of 950 to 900 million years event. And these are the plots. And you can see this is the Vijayanagar and this is the Salur area. But none of these data show much evidence of history later than 900 million years. Monazites, on the other hand, are very much proactive, and we carried out many sample analysis, and we found that the chemical mapping of monazite shows patches of different zones, low yttrium, high thorium, low thorium patches, and just plotting the different spot data, we found that the patchy interior and convolute margins, which indicate transformation of this 1,000 to 900 million years monazite by something 600 to 500 million monazite. And this kind of patches developed due to process called coupled dissolution and reprecipitation. And these are the monazite from the brain samples showing similar textures. And these are the results of the text from our textural data. We found that this can be result from metasomatic fluid that was charged with water along with all these species. These are the monazite sampleages. We got somewhat 9,000 million years, 950 to 900 million years. Interestingly, we have something here. So these are the three different age groups that we found from the Vijayanagaram sample, and somewhat similar in the Salur sample. Yes, just. So these are the zircon RE signatures. We have typical cerium anomaly and negative europium anomaly, somewhat similar for crustal zircons. And the monazite REs are somewhat slightly different. We have elevated LREs and depleted HREs, and something happened in for the 500 million years monazite. We found there are some aberrations. So what happens that the RE distribution becomes more irregular for the younger monazite grains. And these are the age probability diagrams. So you can see that these are the M1 and M2 events here, and this is the possibly M3 fluid event. It's a very strong peak here. So this first part, M1, M2 part, is no different from our published work from the Eastern Ghats, but this second event matches with the amphibolite facies metamorphism of EGP reported by Axelson et al, along with the boundary shear zone, some events. So this is somewhat coincidental. So this coincides with the timing of Kunga orogeny, that is around 570 to 530 million years. And whenever we talk about Kunga orogeny, we have several models of Kunga orogeny. The right one is from Stephen Boger, and this one is from Mulder. And they have different locations for the migration of the Kunga orogens. And in all these cases, none of these reconstructions shows that the Kunga orogen or its similar age events caused high temperature metamorphism in the Eastern Ghats. So Eastern Ghats was far away from the mainland Kunga orogen, and possibly the far field stress that caused this low temperature metamorphism, reactivation of the shear zones, and fluid flow. So these are the conclusions so far we have derived from this work. The first part is similar to what has been reported from Eastern Ghats belt, and the peak metamorphism regime was carbon dioxide that dominated, that is dry kind of thing. And the post 900 million year events are not prominent on granulates except along the veins and patches where we found metasomatic fluids. These are the fluid species we have identified, and these fluids have caused extensive textural modifications, and these fluids in the fluid event in the EGP coincides with Congo orogeny, but the terrain was far away from the mainland loci of the origin. The fluid movement with low temperature overprinting due to far field stresses. So our work also shows that there is no actually not much different of the two locales we have described, Salur and Vijayanagaram, which are earlier interpreted as separated by a some kind of shear zone or thrust zone. I think it's not the case. It's a continuous terrain. Thank you.
You have been told that students are not getting the opportunity to ask. Well, want to have a lot of questions, but please, I encourage the students also to ask questions. I think the hands are not visible sometimes.
Yes. Yeah, please.
Yes. Thank you very much for both.
Yes.
What I am trying to see that the albutite, what albite alteration that you have,
Yeah.
is the later hydrothermal fluid.
I mean, if we don't know the actual temperature of it, but it suggests the temperature reported from the amphibolite facies metamorphism should be around 500 to 600 degrees centigrade. So a kind of possibility is that these are.
I'm seeing calcite, I'm seeing chloride.
Yes, yes. See, because the composition of fluid is a mixed one, so it contained this calcium sulfate, the sulfate salts, and some kind of brine because we have evidence of fluids, fluorine in it. Calcite was also formed. So it's a mixed fluid dominated by water. That is, it's not about only carbon dioxide. And also you have this time, you have a lot of pegmatite events in Eastern Ghats. Yes, possibly.
Another quick question, very quick, from the students. The other room is today active or no? No. Today? No.
Myself, Dr. K. Bangak Naidu, IAPE, Shakpatnam. Sir, any difference of rock monazite and beach monazites?
Beach monazites?
Yeah.
It should be same. I don't know what there will be any difference. The beach monazites are the eroded withered product of the rock, so that should not be different. But they will come from different sources. That is possible. Because in Eastern Ghats you have, rocks from 1.6 billion years also in the central part somewhere inside, because we have zircon dates from interior part. So you may have some monazites from older ages, some more younger ages, but they will look same under.
But the outside form will be completely eroded.
Yes, that will be detrital, yeah, transported.
You will not get all the pictures.
Yes. Okay. So you know these places.
He's thinking of commercial opportunities, I think.
Okay, these are the sources, I think, one of the sources, yeah.
Okay, I think we'll move on and thank you.
Thank you.
The next speaker is Dr. Amal Dev. So he'll be talking on the exhumation and cooling of Gondwanan terrains. So he has 15 minutes. So I will give you a warning after 3 minutes, or let's say 12, right?
Okay, I hope everybody can hear me. Thank you for the opportunity, and it's really privileged to speak in front of a couple of good people who work on multiple aspects of petrology. So I'm just a minuscule part of this research. This is kind of an interface between petrology, kind of geochronology. I don't know whether this is really metamorphic petrology, but still comes into the Hello? Hello. So I don't know if this is really the part of metamorphic petrology, but it deals with some kind of metamorphic rocks. So possibly see that as it comes. So I'm going to talk about the exhumation and cooling of orogens, basically collisional orogens, how collisional orogens evolved over the time, and how they cool and exhume to the surface. So the talk basically focuses on the SGT, the Southern Granular Terrain, but I'll try to explain and expand this idea to the other Gondwana terrains and see how this correlation is going to work in a general aspect. So pardon me the figures, they are not really good because I couldn't find something very similar to this, so I did a bit of Photoshop here, that's why you could see these patches. So these are two kind of orogens in a very general sense. So you have one kind of orogens, basically collisional orogens, where you got two continents colliding each other, and the one continent gets slipped or the other one due to fault assistance. So then people call this tectonic upliftments. So you have the pulling of the subducting slab. Some people believe that there could be some paleo-oceans or ocean basins closure. So this is kind of a tectonic upliftment where the rocks at the shallow surface get exposed to the surface. So when the exhumation or the upliftment happens under the influence of tectonic upliftment, tectonic processes, the movement will be pretty fast in this case. So the rocks from the shallower depth reaches the surface pretty fast because it slips and goes up. On the other hand, what happens in certain cases where you have two continents, but in between you will have a small intercratonic basin, and the collision will be kind of soft, not in the tectonic perspective of hard and soft collision. The collision is kind of soft, so there won't be, the component of subduction is very less. So this is kind of a buckling kind of phenomena. So collides, goes up and forms the orogen. So in this case, although there are certain involvement of these tectonics, but dominantly the exposure of the lower crustal rocks are mostly done by the erosional assisted, the erosion and unloading, so the cores slowly get exposed. So in this case, the process is pretty slow. Erosion and associated exhumation, the process is very slow. This happens in a very slow manner and all. So we have a talk of Professor Baumik regarding how you could predict the process of cooling and exhumation over the time. Of course, how to trace this is a very big question, how to trace this. So we have two conditions, that's the slow exhumation and the rapid exhumation, two different tectonic settings. So how to track cooling rates or how they cool, exhume, this has been a question. So the simple answer is geospeedometry. I'm quite sure that geospeedometry is a very superior technique in this aspect. There are people like Professor Dasgupta, Professor Baumik, Professor Bose, Dr. Priyadarshi, my own colleague Dr. Sorkar, who are good in this geospeedometry stuff. But to be frank, I'm not a physicist. I'm not good in physics and mathematics. So I thought of taking in a different way, how to track cooling in a different way. So there is the concept of this one, this is called the accessory minerals. So any petrological systems will be composed of multiple kind of accessory minerals. You've got zircons, monazites, apatites, and different minerals. So these different minerals has different closure temperature. So closure temperature in the sense that a specific temperature that is designated for the mineral for a specific system that records the age that corresponds to the process. So in a very simple example is zircon that has a closure temperature close to 900 degrees Celsius. So what does it mean is that all the age that you recover from zircon correspond to a process that operates close to 900 degrees Celsius. So many people basically overlook to this process the understanding the relation between closure temperature and ages. So I'm going to take you a very good simple example how the behavior of closure temperature that has to be looked into the actual age context. So this is a pseudo section which we published pretty long back. This is from a sapphire granulite. So this is the place where you see the actual rutile in the sample stabilizes and forms the assemblage. This is the part. But if you see the PT, the temperature of this rutile assemblage, this is close to 1000 degrees Celsius. And this is whether being confirmed from the zirconium and rutile temperatures. But the crucial temperature of rutile is around 570 degrees Celsius. So although the rutile forms at 1000 degrees Celsius, the age that is recorded in the rutile corresponds to something at 570 degrees Celsius. So you should not overlook and say that the age of rutile corresponds to the 1000 degrees Celsius process. In the same way, there's another example is apatite, has a lower closure temperature of 450 degrees Celsius. But if you see the assemblage stabilizes in between 800 and 700 degrees Celsius, but the closure temperature is 450. So if we combine both these aspects, we could see that how accessory minerals can be used in a petrological perspective, irrespective of the PT evolution of the sample, in a different outlook. So this idea, and if you get the age of this region, you got the difference in the closure temperature and difference in the age from the accessory. You just age the difference in temperature by age, then you get the cooling rate. So there are certain general assumptions on this technique, which will be a topic of discussion in the other times, but this is how this technique is going to work. So this idea we could apply on the granulites of the South India. We call it the southern granulite terrain. Pretty classic terrain, has got a lot of trussel blocks, shear zones, a very large history from Precambrian history of early Neoarchean to period to Neoproterozoic, long, very big history. So we could serve, I did my PhD in part of that, and NCSS has a very long history in working on the granulites of South India, all the way starting from 80s and 70s. So we could continue some kind of these things and to look into the problem in a detailed aspect with the new analytical facilities what we have here. So we could derive something like this. This, I would like to call it just a TT path, where the temperature and as well as the age comes into axes. So we could get some age plates. So if in a certain chart, you should think that these age plates are of single minerals. No. These age bracket is basically derived from hundreds of analysis from multiple rocks. So we could basically define a plateau of age in different levels. So combining the available uranium-lead ages and uranium-lead monazite and zircon ages, we could constrain that the peak metamorphism in the Madurai block was lasting around 50 to 60 millennia, all the way between 593 to 532 millennia. And subsequent, the most prominent age peak, what we could find is rutile ages, which has a 20 millennia small growth differences, but still concentrating around 440 millennia. So we could calculate the cooling rate between these two periods. What we could find is that the cooling rates are pretty slow, 2 to 6 degrees Celsius per millennia. Again, we got some good apatite plates from multiple analysis of hundreds of samples. We could define a age plate between 392 to 410 millennia. And we could see that the cooling rates even goes down more slower. So we have a very long-lived UST origin that was slow cooled, then it again got ultra slow cooled. So this is the pattern of age versus age-based cooling rates what we could recover from the South Indian granulites. But there are certain things that to be taken in caution when you deal with this kind of rocks. So the one good example is this titanate age, what we got from a metamorphic rock, close to a metamorphic rock. So this titanate age was mimicking 555 millennia, which is close to the ultra high temperature metamorphic rock. So if you treat this as a different metamorphic pulse, what happens? You're going to calculate it as a fast cooling rate, because 560 to 550 you're going to calculate as a fast cooling rate. But we did neodymium isotopes in this titanites along with trace elements, which is kind of a first time in India. What we could find is that these are not product of metamorphism, rather the involvement of a slab-derived fluid injection. So the primary target is to characterize the mineral by age, make sure that the mineral was evolved or produced during the process of metamorphism, make sure that then you can draw the exact TT path, and we could calculate the cooling rates. So what these cooling rates really mean in this context is that, as I was referring to the previous sections, these cooling rates are pretty slow. So such slow cooling rates can be possibly associated with exhumation by erosion-assisted process, not more than the involvement of structurally or tectonically uplift process. So we found this could be really interesting. So we looked to see into the other Gondwanan terrains, how this kind of patterns, how this is going to replicate. So we got data from South India as we did. We collected, not directly, the available literatures from Eastern Ghats. Of course, we also did some analysis for our collaborators, which was also in the good line. We could get some from Madagascar, Africa, and Antarctica. Also, we did some analysis for ourselves as well as for our collaborators. What we could find is that the cooling rates are pretty slow, very slow for the post-Gondwanan period. So this all means that all these terrains were amalgamated as a single unit at some point of time. It's a different discussion of time. That got slow cooled all over the time and possibly exhumed to the surface, believing this number to be erosion assisted more rather than a structurally controlled or tectonic upliftment. So what this has to do with the whole East Gondwanan assembly, that's the next question. So there are two contrasting models to how East Gondwana has evolved over the time. So one group of people says that this is all Neoproterozoic. You got an ocean all the way running all around here. We call it as the Mozambique Ocean. And there was Pacific type subduction. All these microcontinents got collided and joined together. if you stress on that concept, and there is a different school of thought also that we on the NCESS and some group of people vouch that's the Paleoproterozoic assembly model. So the Paleoproterozoic assembly model says that all these continental blocks got amalgamated as a single unit by 1.9 GA, and subsequently there was no rifting of these basins, only the formation of internal basins, small rift basins, intracratonic basins in the other sense, like these orange lines, and you got sediments deposited in these intracratonic basins that got later converted to ultra high temperature or high temperature rocks. So if you compare the scenario of cooling rates, what we recovered with the two models, what we could find is that this Neoproterozoic subduction model has certain problems. Because why? Because if there was a specific type of subduction, it could be kind of a very hard collision, and we could expect the involvement of tectonic upliftment more prominent to that of the erosional exhumation, and then obviously we should get pretty high rates of cooling. But on the other hand, here we have the closure of internal rift basins, which means that the collision is kind of soft. So the rates, what we can expect in such a tectonic setting is to be very, very slow, and the exhumation should be erosion assisted. So this is what I would like to say that. So basically the gist is that mostly this terrains could have been a single terrain all the way by 1.9 and got exhumed very slowly after the post-Gondwana time, very slowly. So this a long-lived, a classic example for a long-lived, slow-cooled, ultra-high temperature or high-temperature origin. Thank you.
Presentation. So I'm sure there would be questions on this. Quite interesting suggestions he has. Yes.
So Amal, nice talk. So there are a lot of evidence of rapid decompression in the Madurai block and southern granulite terrain. So how do you reconcile that with slow cooling rate and exhumation with erosion assisted?
It is true that we have pristine evidences for rapid decompression, but the exact timing of how long the decompression path has been long, has been still not constrained. So that's one problem with you assuming this kind of chronometry-based cooling rates. So what happens is that between two tie points, that's the epitite point and the rutile point, we assume that this is kind of a linear cooling rate, which is not actual in the real sense. So in the whole path, what it can happen is that it can cool rapidly, then it can slow cool. So that's why we call it as the average cooling rate, not the real cooling rate. So this is that linear assumption, that problem is always there in the system.
Okay, so then it may not be always completely through erosion.
Yes. At certain instances, you could have a combination of both things.
Okay.
In the other setting also, we cannot completely exclude the component of crusting or tectonic upliftment. What I meant to say is that there should be that component, but the dominant component should be most probably the erosional assisted exhumation.
Okay.
That too for the post-Gondwana and post-metamorphic.
Post-metamorphic. Thank you.
Amal, very nice presentation, and also the topic that you have touched upon, the application of thermochronology to calculate the cooling rate. So can you go through to your temperature type path here? So particularly what Tabobroto is also telling, that you have two segments here. I think the rock record tells you about very steep isothermal decompression at possibly at ultra high temperature conditions here. So it is very difficult. If you see your peak UHT metamorphism at 1100 degrees Celsius, how robust is your time constraint with monazite there? Because why I am telling you is that if you have very steep decompression, you do not calculate that cooling rate using this kind of thermochronometers here. The later part of cooling, which is slower, that is no problem. So that's why, because you do your, say, monazite and zircon, they have closure temperature of lead diffusion up to 900. So how you are sure that this monazite is recording time information at 1100 degrees Celsius?
Okay, sir. That's the question actually I'm expecting, to be frank. So I personally don't believe that this is the actual time of metamorphism. Why? Because all the ages what we have in the SGT for the peak metamorphism comes from monazites and zircons. And the temperature always close to 950 plus, 1000, 1100. And I don't believe that there is no accessories going to record the actual temperature, actual timing of metamorphism. So I would like to call it just the best time of metamorphism, the best time what we can get. And all these calculations were not based on the thermobarometry, although I have shown that the metamorphism has gone up to this levels, but this calculation was basically done based on the closure temperature effect. So the boundary was exactly chosen as 900 because that seems to be more reliable for me. So this estimate is based on the 900 to 550, which I think more robust considering this 130 degrees Celsius. This is the highest temperature. So I don't believe that this is the actual age, although I publish based on monocytes and zircons. You too maybe join with me in this aspect.
I think we can work together to use diffusion chronometry to get some time constraint along the
Yes,
heat decompression.
but I have one point to add. Actually, when we did this thing, so
We can get the data.
yes.
Just one point I want to add that if you follow the Simon Hurley's diagram, 2007 elements paper, zircon and particularly zircon actually doesn't grow during the peak metamorphism. It actually grows during cooling, most of the cases. So I mean there are always uncertainties about the peak metamorphic event
That's
from
what
zircon.
Yes, that I was referring. Especially in the case of semi-pelites or pelites, this is very difficult to grow zircons because of the elemental problem.
Yes.
The availability of the element also.
Yes.
You could recognize the temperature, but not the actual age.
I think we'll probably go down to the next lecture. Thank you, Aman. For the next couple of talks, I would request my co-chair, Dr. Preetham Nasipuri, Faisal Bhopal. He'll be guiding the speakers.
Yeah, thank you, sir. To move on, may I request Dr. Srina Raichaudhuri to present her talk on formation of aluminous clinopyroxene ilmenite spinel symplectite assemblages in a regionally metamorphosed clay silicate granulites from the Chotanagpur gneissic complex, East Indian Shield. Yes, miss. You will have 15 minutes, and after 12 minutes, try to complete.
Good morning, everyone. Today I would be talking about formation of aluminous clinopyroxene ilmenite and spinel symplectites in a calc-silicate rock from CGEC, Chotanagpur Granite Gneissic Complex. Now, before I move on to my study area, I would like to discuss first about the occurrences of this assemblage in different rocks. So mostly these assemblages has been reported from intrusive mafic and ultramafic igneous rocks, but these are less common in metamorphosed rocks. Now within metamorphosed rocks, these have been recorded in mafic granulites and retrogress eclogites. And these are even more uncommon in calcareous rocks. So few reports are from skarns, and extremely rare reports are from regionally metamorphosed calcareous granulites. So in this backdrop, in our study we have tried to understand how this unusual assemblage formed in our rock and what is the probable protolith of the rock. So moving on to my study area. My study area lies in the northeastern part of the Chotanagpur Granite Gneissic Complex, East Indian Shield, and that's near Devghar. And the studied rocks are located in the foothills of Trikut, and these occur as enclaves within Mesoproterozoic country rock, which is a magmatic amphibolite biotite gneiss with local Charnockite patches. Now this country rock also contains some meta-igneous enclaves of organ gneiss and mafic granulites, while the metasedimentary enclaves include some pellitic granulites, calc-silicates, and some quartzites. Now, the studied rock shows alternate melanocratic and leucocratic bandings, which are very similar to the other calc-silicates of the area, as shown in this figure. Now, the leucocratic rock bands, these are dominated by plagioclase, as you can see, and other minerals like garnet, clinopyroxene, and amphiboles occur in lesser amount. On the other hand, The melanocratic rocks, the melanocratic bands, these are dominated by amphibole and clinopyroxene, and garnet occurs as relic grains like here. And in this band there are rare magnetite and some calcite also. And at the interface or boundaries of the melanocratic and leucocratic bands, a garnet-rich band forms, which are dominated by around 70 to 80% phosphoroblastic garnets and less amount of amphibole and plagioclase. Now, detailed petrographic study reveals that in all the three bands, similar mineral evolutionary history has occurred. So I will describe them together. The garnets, these occur as medium-sized subiodioblastic grains, and these brown minerals, these are actually clinopyroxenes. These are pleochroic in the shades of brown, and they contain a very high proportion of aluminium, extending up to around 11.58% Al2O3. Now these clinopyroxenes, they have straight equilibrium boundaries with garnet, plagioclase and amphibole, and together these four minerals define a granoblastic mosaic, and titanite occurs rarely within this granoblastic mosaic. So the peak assemblage, the peak metamorphic assemblage was determined to be amphibole, plagioclase, garnet, clinopyroxene and titanite. And interestingly, plagioclases are extremely anorthotic in nature. It's around nearly pure anorthite. And garnet is grossular rich with a little proportion of andradite. However, clinopyroxene also occurs in a second textural variety. It occurs in intergrowth, or it occurs in an intergrowth texture along with vermicular blebs of ilmenite and some spinel. And these symplectites, they form at high angles to garnet, to the boundaries of garnet and amphibole, and sometimes these symplectites, they engulf partially or fully these garnet grains, and inclusions of amphibole and titanite are also common within this symplectite. So we inferred that the symplectic assemblage was formed at the expense of garnet, amphibole and amphibole and titanite. And a second generation of amphibole was also observed, which replaced the symplectic assemblage and garnet. Now, pseudosection modeling reveals that constrains the pressure temperature conditions of peak metamorphism to about, it has been covered. So it shows a high pressure around 80.5 to 9.5 kilobars and moderate to high temperatures, which is followed by a steep isothermal, near isothermal decompression up to 5 kilobars, where the post-peak symplectic assemblage stabilized. So now interestingly, this rock contained abundant detrital zircon, and showing the age range of 1790 to 486. Now, based on this, the presence of abundant detrital zircons. It shows or it indicates that a pterogenous sedimentary protolith of the rock, and additionally, as I already mentioned, the presence of grossular rich garnets and high calcic plagioclases, high calcic clinopyroxenes, and all these reveal or indicate a calcareous protolith of the studded rocks. And also the peak metamorphic assemblage which stabilized in this rock is also similar to the peak metamorphic assemblage observed in other calc-silicates of the study area. So, but the only difference was that in this rock, the bulk was richer in aluminium and some amount of iron, and lower in calcium content relative to the other calc-silicates. So, an argillaceous or marley limestone or an intercalation of basic volcanic calcareous sediments was inferred to be a probable protolith, or a mixture of both this was inferred to be the probable protolith of these rocks. Additionally, lower oxygen isotope values indicated that possibly the protolith of the protolith or the sediments, they interacted with meteorite water, which decreased the oxygen isotope values to 4 around, and which was also responsible for the aluminum enrichment and the calcium depletion in the rock. And later, this altered bulk metamorphosed to this unique assemblage. Now the oldest metamorphic zircon or the spot age 1486 and the youngest electrical age constrains timing of sedimentation between this. Additionally, the age of peak metamorphism and symplectite formation was constrained from metamorphic zircons to be around 1060 and 970 million years. So this high pressure peak metamorphism followed by a decompression, followed by a near isothermal decompression. This all indicates a clockwise PT path, and also this 28 degrees Celsius per kilometer geothermal gradient, these are indicative of a continental collision setting. Now similar similar clockwise PT paths have been reported from other litho units of the study area, and this early Neo-Proterozoic event has been related to the second major tectonothermal event of in the CGGC and has been correlated with the final amalgamation of Rodinia supercontinent. So these are some of the references, and I would like to thank Professor Rao and ESSO-NCESS for giving me this opportunity to present my work, and also Professor Pulak Singh Gupta and Shubrata Karmukar and Chandra Sarna for guiding me always.
Yeah, thank you for completing before the time so that we have some time for question and answer session. So from students. Huh? Yeah. So, or yes.
Now, what kind of garnet composition you have in your rock?
These are grossular rich, but a solid solution of grossular and unwinding, and also has around up to 7 molar percentage andradite.
So how much grossular?
Approximately 60 to 70.
60 to 70. Okay. Now the other thing here, you have 2 metamorphic ages from your zircon. One is around 1478 or something.
1486, we have only one spottage.
Now what you consider, and because your main dominant population is 1000 or 950.
Yes.
So theoretically, if you consider some metamorphism at 14 plus, 1400
yes.
plus, so then that evidence should be there in your rock record. Do you have any evidence of the...
Actually, not in my rock, but we have the country rock which I talked about, the Celsic Knight. It has an emplacement age around 1450. So these are all these enclaves are all older. So possibly there may be a thermal imprint, but which is not recorded in my rock at least. We got only this one spottage which gave this older.
So is it a possibility that the 2 metamorphism you have peak assemblage
yes.
and you have symplectic assemblage?
Yes.
Is it possible they formed at 2 different time frames? Because you are now
right.
joining this as part of
yes.
one continuous PT path.
Right.
They may reflect 2 products or 2 different
right.
metamorphism, the signature of which is incompletely preserved in your. Is
right.
it that possible as well?
Well, we thought about that first, but then we opted for this option because the zircons texturally, they are overall distributed in a matrix, as well as we got a few inclusion within the zircon inclusions within the symplectic assemblage. So these all actually, the inclusions as well as the matrix grains, so they gave this age within this 1000 to 70 cluster. That's why we thought that that may be a better solution to this.
Okay. Thank you.
Just continuing with what he was saying, you actually have a long span of metamorphic ages during this 1030 or 40 to 970. So if the symplectite actually formed during this retrogression, you should not expect that long time. I mean, it should be immediately after this peak assemblage. So just think over it.
Yes, of course, sir.
Okay, so remaining questions can be discussed during the lunch. So thank you, Srina. Yeah. So next speaker is Dr. Ajay Kumar Singh from ACSI GRI Hyderabad, and he is going to talk on tectonic settings and depositional age of beta sedimentary rocks from Simlipal complex, Singhbhum Craton, Eastern India, constraint from UPV geochronology. Yeah, Dr. Singh, you will have 15 minutes with
Okay.
12 minutes and 3 minutes.
I will finish it before that.
Okay, that's great.
Am I audible? Okay. So, good morning, good afternoon, sir. Everyone. So this is today I will talk about the tectonic setting and depositional age of meta-sedimentary rocks from Simlipal complex, Singhbhum Craton, Eastern India. Constraints from UPV zircon geochronology. So the Simlipal complex is lie along the eastern margin of Singhbhum Craton. So this is a circular or semicircular complex which having the three alternative rings of meta-sedimentary rocks in the splitic lava volcanic. So this cover the area around the 9,000 square kilometer, and the basement of this complex is Archean rocks, and it is these bands are dipping inward the center of this complex, and the central part of this complex is comprises by the ultramafic rocks like pickrite, gabbro, basalt, and some undifferentiated rocks are like quartz, diorites also in the central part of this rock of this complex. So I will only concentrate on that on these meta-sedimentary rings in this complex. So geological map of that Simlipal complex. So and with the location of the samples. So these are the locations, and we have the rocks like quartzite, phyllite, shale, and some sandstone also is there. So some primary sedimentary structures are also preserved on some parts of this basin, and the petrography is revealed that some phyllite is showing the sharp contact with the sandstone, and sometimes showing the gradational contact with the quartzites or sandstone. And these are the two images from the quartzite which are showing the recrystallization and ondulose extinction of these grains. So these are showing the deformation of these rocks. So these rocks are basically deformed, and because tectonic fabric is developed in that phyllites, so these rocks are undergone to the green schist facies condition. So we have separated the zircon from the quartzite, phyllites, and schist. So these are dead title zircons basically. So we took and we dated for the uranium lead dating, and these are the probability density plots, and these are the Concordia plots. So we have only considered the concordant ages which have 95% of degree of concordance. So this is the overall spread in different parts of the basin. So basically I have grouped these rocks into the three regions. One is central domain, northwestern domain, and northeastern domain. and one is the Kuleana. Kuleana is lie outside the basin. So here, so this is the overall summary of these populations, which are spread from 2.5 to 3.9 GA. So mainly these sediments mainly is derived from the Paleoarchean to Mesoarchean TTG, which are present in the in the Singhbum Craton. So one thing is that for defining the age of deposition, we need some metamorphically formed some grains, means zircons. So this is one of the grain which is showing the 2.5 GA age from this rim part, and the core part is showing the age of 2.9 GA. Because I am interpreting this is the metamorphic age, and because of this is a very desiccated part of this grain, so this cannot be survived during the transportation. So we are interpreting this is formed during the low grade metamorphism, and that fluid was released from the metapolitic rocks, and that is mainly responsible for this formation. So 2.5 age is mainly in situ metamorphic age. So on the basis of the minimum age of crystallization and maximum age of metamorphism, we constrain that that sediment was deposited between 2.8 GA to 2.5 GA. So for the for tectonic setting, we can utilize that detrital zircons to understand what kind of the tectonic setting in which that basin was developed. So these are the one paper which is published in 2012 by Coward et al. In geology. So they suggest that three types of the tectonic setting: convergent, collisional, and extensional. So based on that overall population of the zircon and the age of the deposition. So these red arrow is showing the age of the deposition and different tectonic settings. So they considered and they define one diagram, discrimination diagram, based on the difference between the crystallization age and depositional age, and the cumulative frequency of that individual grain. So based on that, they define the three tectonic setting: convergent, collisional, and extensional. So in our case, our samples are mainly is lying in that collisional tectonic setting. If we will plot the difference between the crystallization and depositional age versus the cumulative frequency of these individual zircon grains. So around the 60% of the detrital zircon grains is showing the difference between the crystallization or depositional age is less than 500 million year. So these all are indicating that that Similipal basin is formed due to that collisional kind of tectonic scenario. So based on that study, we can conclude most of the detritus was derived from the existing Paleoarchean TTG crust, as well as from the Mesoarchean potassium granite and potash granite and granophyre from the craton. And the sediments were deposited between 2.5 to 2.8 GA based on that age of the oldest metamorphic and youngest detrital zircons. The sediments were deposited in the collisional related tectonic environment or that fold-end kind of basin. Thank you. Thank you very much.
Yeah, thank you, Dr. Ajay, for your talk. So it's time for questions. Yes.
So you, in your conclusion sections, you have shown that the basin opening around 2.5 to 2.8 this period, sediment deposition.
Deposition, sir, not basin opening. That is the depositional age.
Okay,
So basin was open before that.
Okay, so how do you fix this 2.5 billion years? This 2.5, is there any metamorphic event during this time?
So 2.5, because that terrain means that similipal terrain is undergoes that metamorphic conditions like up to the green cyst species. So that times we are expecting that achieve means low temperature pressure of that fluid was released from the metaplatic rocks, and that is interact with that tidal zircons, and then altered that part and giving that age of 2.5 GA. So because the frequency of 2.5 GA population is very less, so we cannot expect that are derived from the somewhere else. As
yes. In Shingbhum area, we have very little evidence of 2.5.
Yeah, so there are no availability. That's why, so we are considering that lowest age means minimum depositional age that can be.
Yeah, Ajay, very good work indeed. Okay, you have generated a lot of data. So when we are talking about the tectonic setting of sandstones, okay, there are classical works like Dickinson and Sujet, okay, where the framework composition gives us a lot of information regarding the tectonic setting. But Shimlipal Basin, these sandstones are actually super mature quartz granites.
Yes.
So how do you think that in a collisional setting that kind of super mature quartz granites will form? Because modern day Poland basins, if you go to the Indo-Gangetic alluvial plains, these we expect mostly lithic granites. You cannot expect quartz granites. So how do you reconcile with that? Because framework grains will give you the first-hand information regarding the tectonic setting.
So sir, here we are using that dead title zircon. So basically that dead title zircons are derived from the magmatic rocks, and we are taking the difference between the crystallization age and depositional age. So so that giving the information about in which kind of the basin able to preserve of that types of the zircons, or that population, that much population of that particular age of the zircons relative to the depositional age. So using that concept that Cowwood et al. They have published one paper in 2012. So on that basis we are saying.
I would urge you to, I request you to please look into the framework composition of the sandstone also. That will give you a lot of information.
Okay, sir.
But very good work indeed.
Okay, thank you, sir. Thank you very much.
Hello. Actually, whether you have taken sample from that quartz granite, or because in the Simlipal area in the lower places, we have a lot of sandstone which is not quartz granite.
So, sir, we have collected all the samples, all kind of the samples.
No. Is there any, because those are different. Lower part, those are not quartz granite. In the upper part, there is quartz granite.
So, in the lower part, I think there are some flight or sails are there. So that kind of the samples we have collected. So, sir, 3.9 GA is belongs to the Kuliana region, and from 2.5 to 3.6 or these ages from the central or north western or northeastern part of that basin.
Yeah, I have a comment regarding here. So in the lower sandstone is also quartz granite. I differ with him because we have published most of our data is from lower sandstone. That is, most of them, almost all of them, contains 99 to 98% silica. So they are quartz granite.
Okay, thank you, Dr. Ajay.
Thank you.
Now I request Professor Gupta to take over.
So I'm taking over for just one talk. So I'd like to welcome Dr. Lopamudra Shah for the next talk. She's from IIT Roorkee. She will be talking on the tectonothermal evolution of the Proterozoic Mahakoshal belt around Jabalpur along the northern margin of the CIT side. So please adjust the timer. So Lopa, I will let you know at 12.
Good afternoon, everyone. The title of my today's talk is Tectonothermal Evolution of the Proterozoic Mahakoshal Belt around the Jabalpur area along the northern margin of the Central Indian Tectonic Zone. This is part of my PhD students' work and which I am presenting here, and this is all we have published, all the work. So first, just a brief introduction about the Central Indian Tectonic Zone. The term itself was first highlighted by Professor Bhomik, who is my PhD supervisor and is present among us today. And first in 2000, and then also it is known by the other names like Satpura Mobile Belt and Saucer Mobile Belt. Bhomik et al. In 2012 first corroborated that this Central Indian Tectonic Zone, which is located here, is in continuity with the Aravalli-Delhi fold belt in the northwestern part of India, which is wrapping around the northwestern part of the North Indian bloc, and it is continuing in the east to the Chotanagpur Gneissic complex and further east into the Shillong Plateau Gneissic complex. And this idea was further elaborated by Banerjee et al. In 2022, and this is they have named it as the Greater India Proterozoic Fold Belt, and CITZ is located in the central part. Now this is this map shows the tectonic dispositions of special dispositions of the tectonic units of different tectonic units in Central Indian Tectonic Zone. And what you see in the southern part is the RKG domain and the BBG domain. Sorry, RKG domain is in the central part, BBG domain in the southern part, which is separated from the Bastar Craton by the Central Indian Shear Zone. And in the northern part, we have the Mahakoshal belt, and here is the location of the Jabalpur. Jabalpur forms the northern crustal segment of the Central Indian Tectonic Zone. Now, as per the data from about Mesoproterozoic tectonics from the Central Indian Zone is concerned, a lot of data are available from the southern part along the BBG domain, where emplacement of the Tirodi biotite gneiss occurred at about 1.6 billion years, and then there was a series of accretionary events characterized by granulite facies metamorphism as reported by Professor Bhomik in 2014. And in 1.4 gigaannum, Professor Bhomik et al., there has been a metamorphic monazite growth, which has also been reported by Bhomik et al. In 2011. Now, in contrast, if we move to the Mahakoshal belt, we find that Professor Talat Ahmed's group has recorded 1.75 gigaannum A-type granite intrusion around CZ area and 1.6 gigaannum post-collisional A-type granite along the Jabalpur area. So as per the metamorphic records from the Mahakoshal belt or the northern part of the Central Indian Tectonic Zone are concerned, so the only data available was for Deshmukh et al. 2017, who constrained continuous metamorphic event from 1.9 to 1.5 gigaannum and along a clockwise PT path. Now, this is the area of our studies of the samples that we have studied in this for this presentation, and this is the map that we have prepared, the lithological map with the foliation. And what you see here, there are different rock types among the metasedimentary units here. We notice garnet micacyst, staurolite micacyst, andalusite, staurolite, garnet micacyst, and micacyst. Now, when you looked at the texture, so this is the field photograph of the Andalusite bearing cyst, and you can see that the pervasive foliation here is the S2 foliation, and also here we see the prominent Andalusite porphyroblasts and in another mica cyst here, and then there are this garnet mica cyst. This is the garnet mica cyst. And then we have storlite mica cyst, and we'll come to the petrography of each of these samples. Before coming to the petrography, just a brief idea about the geochemistry of these rocks. Now, when we plotted the major element data of these samples, we found that mostly their protoliths were shale or wacke, and looking at the contribution of the from the trace element components of these metasedimentary rocks, looking at the contribution of the source rocks, we found that both TTT and UCC upper continental crust and the mafic or ultramafic sources were involved. And in the tectonic discrimination diagram, we find that these rocks plot in the collisional tectonic domains. So we came to the conclusion, what we can state here is that the sediments were, the protoliths of these metasediments were deposited in a collisional setting. Now here we have the textural images, the BSC images and other extra element maps. So what you see here is that these are the Andalusite porphyroblasts in the Andalusite bearing rocks along with garnet, and here is the S2 foliation. Similarly, this S2 foliation has been traced in all the, could be identified in all the other samples, and in one of the microdomains we have seen that around this garnet Andalusite bearing rock, we have seen that sillimanite, staurolite, quartz and biotite bearing assemblage has formed. And next, when we studied the other samples, we also find the same S2 foliation which is warping around the garnet and staurolite bearing porphyroblasts. Somewhere S2 foliation which is defined by muscovite as warped around the staurolite porphyroblast, and somewhere the garnet, only garnet. Now here we see within the Andalusite bearing mica cyst, we see formation of Andalusite, second generation of Andalusite by the breakdown of the garnet porphyroblast along its margins. So as I discussed in the textural part, the rock has all the rocks. If you look at the textures details of all the rocks, we can see that there has been multiple domains of mineral assemblages, microdomainal, in the microdomainal scale, those mineral assemblages has developed. And in first we have chosen the microdomainal bulk compositions from these domains to construct the pseudosection analysis. And here we find this is the one part of the prograde part has been constrained from this pseudosection analysis, and the where we can find a sort of low pressure heating, and then for the next texture like this where we have found staurolite sillimanite assemblage, we find the stability of staurolite sillimanite along this along this area here, and finally we constrained from the mineral compositional isoplate the peak PT of staurolite sillimanite bearing assemblage at here at this point, which is marked by the star here. Then we have another rock where we have staurolite, second generation of Andalusite, and here we find the stability of the assemblage at this part, and continuing with the staurolite absent garnet bearing assemblage, we find the evolution or stability of the assemblage in the pseudosection analysis at this part, and the peak PT is constrained at this point. And again, this is another rock which is having both staurolite and garnet within it, and so here we have found the peak PT here. So finally compiling all the pressure temperature conditions from different microdomains that have developed around the Andalusite porphyroblasts or around in the different mica schist layers. So this is our PT path for the main metamorphic event, which is recorded here, and which is, we can see that this is a clockwise PT path, but in marked contrast to what has been recorded by Deshmukh et al. From the CT area. And then we identified monazites, which are mostly located within the S2 foliation domain. And when we found out the ages of these monazites, we found age peaks at about 1.469 million years, and another age peak which is older at 1879 million years. And then we plotted the isochrones, and these are the two isochrones that we have derived from this monazite data. And so we conclude this as the age of the main metamorphic event, which has been produced all these textural domains that we have discussed. And this older age probably represents an older metamorphic event, because which probably led to the formation of the S1 foliation. Now, why we concluded that these ages of these monazites as metamorphic monazites is from the trace element patterns you can find. They are highly depleted in their heavy rare earth components, and so if we compare the PT paths, if we compare the PT paths of these from this monocoastal belt what we derived with that recorded by Bhomik et al. From the granulite facies domains of the southern margin of the CITZ, we find a marked contrast. And the PT path that we derived here is in completely analogous to that what has been recorded by Spear et al. In 1990 from the southwest of New Hampshire. And based on this analogous PT path and its topology, so and its characteristic, what we have concluded that this may be these argillaceous metamorphic rocks represent the lower plate in a nappe which is formed during continent-continent collision. Now just few concluding slides. So now we have already looked at the Jabalpur area here. So we like to compile this data and analyze it and explain it with respect to what we have found in other parts of the North Indian block from around the margins of this Bundelkhand craton, these marginal basins. So these are the rocks that we have studied in another, published in another paper. And these are the sandstone from the Gwalior basin. These are the sandstones from the Bhopal basins. And what we did, we actually determined the detrital zircon ages from these two basins, and we find that they are, this is one peak we can see of these detrital zircons which correspond with the breakup of the wood, of the extended wood supercontinent, and the remaining ages 1.6 and 1.4 are coinciding with the formation and breakup of the Columbia supercontinent. Now, as per the Columbia supercontinent connection of the CITZ is concerned, Professor Bhomik, he reported that probably this early to late Paleoproterozoic to early Mesoproterozoic orogenesis recorded from the southern part of the CITZ indicate that this formed as a separate landmass as compared to the main Columbia supercontinent assembly, the landmass which was involved in the Columbia supercontinent assembly. And the two other opinions involved, Mohanty from 2010 and 2012 concluded that this is in continuation, this CITZ is in continuation, was in continuation with the Capricorn orogenic belt. And Lee et al. 2015 and Zhang et al. 2012, they found, proposed a continuity of the CITZ with the trans-North China origin. Now, looking at whatever the data which are available from the monocoastal belt, can you really find out a conclusion about the or linkage of the monocoastal belt with the Columbia supercontinent? Okay, this this proposal is supported by research groups who are who are working on the granites from the monocoastal belt. And this has been questioned by metamorphic petrologists who have derived the metamorphic PT conditions and the timing from the Monocoastal belt. And in my opinion, the answer lies in the detailed study of the Betul belt, from which we can study the tectonometamorphic evolution of the belt, and then we can come to a conclusion about the Columbia connection of the northern part of the Central Indian tectonic zone. Thank you for your kind attention, and I would like to specially thank Professor Chalpati Rao to provide me the platform to present the talk. Thank you.
Thank you, Lupa. We have time for one very quick question if somebody would like to go through with it. Yes.
It's a very nice one. Just out of curiosity, because I don't have much information about this Monocoastal group of rocks. The Andalusite you have shown, these are large size grains. So, and what is your opinion? It is formed during decompression, this large Andalusite grains?
No, that was formed during heating.
Heating. So that heating is related to some kind of magmatic event here?
Sir, actually we didn't find any evidence of contact metamorphism here, but definitely the what Professor Talat Ahmed and his group reported a granite which is from the Monocoastal belt near around Jabalpur. So that intrusion age of that granite is 1.8 to 1.9.
Is it about the Madan Mohol?
Madan Mohol granite, yeah. So we are working on it, but I think that after we can, already the paper is under review, so after we publish it and we can establish what is the tectonometamorphic evolution from the Betul belt, we have a much more clearer picture about a supercontinent connection of this belt.
Okay, thank you.
Thank you, sir.
Thank you, Lopa.
Thank
once again. I'll just hand it back to my co-chair again for the next talk.
Thank you, sir. So we have the last talk of this session by Dr. K. Bangagunaidu.
Yes, sir.
From from IIP Visakhapatnam, and he's going to talk on geochemistry and geochronology of monazites from coastal sands of South India and its implication for the evolution of mobile belts.
Yeah.
So I welcome you. You have 15 minutes and 12 plus 3 minutes.
Thank you, sir.
Oh.
Within before 15.
Okay.
Yes, sir.
Get in.
Good morning to everyone. Myself, Dr. K. Bangak Naidu, IIP. So, lighter. This is lighter. This one lighter. This back and front. Okay. So, my topic is geochemistry and geochronology of monazite from coastal sands from southern India. The implications of the mobile belts. Like taken one mobile belt is the EGMB. So already discussing about everything is before lecture, Bose and Sarkar, and discussions about the times and special discussions about EGMB. Right now taking my EGMB monazite data and the beach sediments. This is a different topic, just thinking difference. So these are sample collections, like this is a beach sediments. This is a foreshore, backshore, barren zone. This is a four environment in the collection of the beach sediments. So what is the foreshore, what is the backshore, what is the barren, what is the zone? This is the, basically this is the divided to the to tidal effect. So higher tide is the foreshore, like some backshore. In between low tide in the backshore. In between foreshore and backshore is the barren and the ridge-like structure. Then is the last one is the zone. I have taken sample in the all these 121 samples using for the PVC pipe. So 3 feet PVC pipe taken from 1 feet of the sample, put in the 1 feet of the samples. The collection of all these samples using for the different so methodology used. This is the mice usually in the study area. This is the what is the methodology. First is the taken field work, then use the different sample collection in the foreshore, backshore, barren zone. This is the sample processing. This is the first sample processing is the structural analysis using for the sieve shakers, Then the sieve sets in the 10 sieve sets is there. All the sieve sets, the coming to the data is there. The data is the geostart software using different energy levels is there. This is the one part is the different. The another part is the main objective is reached to the implications of mobile belt. So heavy mineral analysis. So heavy mineral analysis simplified the 3 fractions is there. For 60 fractions, 120 fractions, like all these ASTM size maintained by ASTM size. American Standard Thieves materials. So ASTM size maintained by fraction 60, 120, 230. So coarse, medium and fine sediments. So then after taking all the samples, so separation of the bromoform separation. Then bromoform separation is a grain counting like using for the slide. This counting of the using for optical property of the every mineral is a different optical property is there. So monazite is a different optical property. Monazite, rutile, zircon, monazite and beach sand is a heavy, whose heavy minerals in there. Each heavy mineral is a individual optical property is there. So individual as per optical property, optical base, this section of the grain picking of 85 grains in the pick in the study area. Okay. This is the trend and average. Actually, this is a energy levels condition. So beach sediments, like some of the effect of the river effect is there. Some of the effect of the tidal effect is there. Some dominant of some energy levels is different. So, okay. This is the fraction wise distributions. The foreshore and backshore barren dune. So measure in so medium size. This is the coarse. This is the medium. This is the fine segments. The measure in beach segments is a 12.95 weight percentage. Like this is the higher in medium size. So very beautiful fixtures. All the heavy minerals, different sizes is there. Elongated, rounded, sub-rounded. Each one every mineral. This is a major mineral in ilmenite, rutile, garnet. This is the rutile. This is the blooded color is the rutiles. Some of the monazite and some of the zircons, sillimanite, kyanates, like all the pyroboles. So different shapes of the beach monazites, so rounded, elongated, some different shapes is there. Okay. So then you taken a monazite grain using for the EPMA analysis. So the EPMA analysis using in Chemac SX100 in GSI, Hyderabad. So some monazite alternative voltage and kept some of the features. This is the thorium and uranium, like two differentiations there. Thorium and uranium ratio below 100, so 0 to 100, like 10 to 100. This is the some of the classifications is there. Carbonate, hydrothermal, low temperature, high temperature monazite is there. So European positive anomaly, like one of the squandolites and Charnockite rocks steroids. This is the substitutions. One of the signatures of the European is a positive anomaly, like UE is a positive anomaly. So this is the calcium versus thorium oxides. So calcium weight percentage using for the after G et al. So this is the above. This is the high concentration of the CO is 1 to 3%, and thorium is a 3%. Almost this is the field of magmatic and high temperature metamorphic zones. So remaining is the low concentration of the CO and 3HO2. This is the based on hydrothermal and low temperature and magmatics. Okay, this is the trilinear diagrams of thorium oxide, CaO and ReO. So in case THO2 and CO is a high concentration, this is the magmatic and high temperature metamorphic zone. There is a low concentration of the CaO and thorium. This is in the field of hydrothermal regions. This is the one Liu et al. The ratio thorium weight percentage, then thorium by CO ratio. This is the discriminations of the field of igneous and metamorphic all the my beach sediment samples. So this is the one trilinear diagrams. This is the only igneous and metamorphic origins. So ReO versus CaO weight percentage in all the beach sediments, the field of magmatic high temperature metamorphic zones. Okay. This is the most important for the, what is the difference between EGMB and beach sediment monocytes. So all the collection of data in the CEMET Enright 2008 Sayak et al. EGMB monocyte data, and this is the my study area data. This compared to both the data is been measured in magmatic and high temperature metamorphic zone in the EGMB data, and almost in my study area of all the monocytes in magmatic and high temperature metamorphic zone. So based on and EGMB monocyte dating and in my study area of monocyte data, so almost similar age of this one. This is the conclusions. EGMB monocytes are enriched in the rare earth elements, thorium rearrangement due to high grade metamorphic zone, and beach sediments also inherit from the granulitic and Charnockite rock EGMB wise erosion, transportation and deposition process is there, and beach sediments display thorium high rich thorium uranium ratio 2.2 to 61.6. This is the in between 10 to 100. This is the magmatic high temperature metamorphic zone. Above 1000 is the carbonates, and below above 0.01 is the thorium and high uranium ratio. Very less. This is the carbonates. So this is the condylite and Charnockite and granitites. Beach sediments monazite uranium thorium is and monazite and a beach sediment monazite is equal to EGMB and my study area of the samples. Okay. So very special thank to NCS Director N.V. Chalpatrao and convener and co-convener Thompson and Amal and prompt and respond. Then acknowledge to Survey of India analysis of EPM analysis, and finally so my postdoctoral Department of Science and Technology in PDF. So the special thank to financial support to ANR. Okay, thank you to all.
Thank you, Dr. Naidu, for your nice talk. Now time for questions.
Naidu, can you go to your rare earth element pattern? It's a good presentation, but in not only him in this case, but also a lot of others, people are telling, particularly with regard to the rare element patterns, LRE high, HRE low, or europium positive, cerium negative, holmium, but not that is only observation.
Yeah.
What is the inference? Yes. Nobody is telling.
Yeah.
Can you please tell that you have observed some anomalies in the RE patterns? Can you explain?
This measure in taken europium is positive anomaly, sir, in this field.
Europium you don't really see much.
Sir.
But the prominent anomalous things
so
are
no one are not discussing for the thulium, sir. Like thulium. I don't know exactly.
That's what you
yes,
should
sir.
Try to understand.
Yes, sir. Sure. So some of the publication europium is a discussion, but measure.
You are an youngster, so sure. You should understand
sure,
why all that, why it's not straight, why. And then try to explain in this kind of presentations. Okay.
Sure. Thank you.
It's a good presentation.
Okay. Thank you, sir.
Sir.
Do this analysis because Ramji is here. I don't want to comment, but I think there is problem with your analysis for this holmium and
EPM, GSA, sir.
EPMA?
GSA, Survey of India, Hyderabad. Geological Survey. Okay. Thank you, sir. Sir.
An interesting work indeed. So when we are talking about the source of this detrital monazite grains, have you done some drainage pattern analysis where from those sediments are coming? Because why only Eastern Ghats? Because monazites can be derived from the your adjacent Harvard metamorphism. So I want to see the age. Just can you go to the age?
Sir, actually, nearest in the EGMB, that's the reason compared to EGMB and beach monazite, sir. That's the reason. Yes, sir. Draining, yeah. The Gostani river is there, na? Just only for EGMB, sir. Nagavali river is there, na? Just only for.
You just go to the edge.
Yes. Yes.
2200 after 2200. So I see that no, if, whenever it's present, okay,
It's a-
I urge you to keep a drainage pattern analysis.
Sure.
What kind of rivers are transporting and where they are originating. So they are cutting through all the terrain, okay. So
So
that
I will-
will be more, instructive.
Thank you, sir.
You cannot just say all these are magmatic and metamorphic ages as I have shown. There are events like low temperature fluid activity. So,
So actually, one problem also is there. How to deviation of magmatic
no, it's not
and
that
metamorphic.
simple. Just
Magmatic and
monazites.
metamorphics.
No. I mean, monazites can undergo a lot of changes during later part, and if it is undergoing changes with a solution of alkali rich or halogen rich, they can change the lead can move around, and you will get later younger ages.
Okay. So thank you, sir.
Yeah, questions. Wait, I have one more question.
Like Sukanto sir said that you should have incorporated the drainage patterns as well. I would just like ask you one thing, that you have only compared it with the EGMBs, right?
Yeah.
That's why you're finding similarities with the EGMBs. You should have also compared with the other regions to discriminate which affinity it is having towards, like more to the EGMBs, or which part of the EGMBs to be specific.
Yeah, sure, sir.
Yeah.
Next, okay,
So-
elaborate to all the some cratons and taken samples also.
Yeah, so this-
compared to beach sands and remaining cratons.
Yeah, so this might lead to a data bias.
Actually, this is a drainage patterns. All the drainage patterns in like rivers in the EGMB in there, Nagavali and Vamsadhara, Gostani, and every rivers in the EGMB. Like taken the samples and then differentiation of EGMB and beach segments.
Okay, so any more questions?
Any more?
Especially from the students? Okay, then we are at the end
Thank
of
you,
this
thank you.
session.
Thank you so much.
Thank you, Dr. Venkat. And thank
So, okay, I think both myself and Pritam would like to thank all the speakers. So, a round of applause to all of them again. So, sorry? Well, since I'll be speaking after lunch, I would hate not to do that. So, anyway, so.
Thank you, sir. And again, I will request our director, sir, to hand over the memento to Dr. Nasipuri and Professor Shoibal Dashko. Shoibal.
I've been waiting for my vote.
One thing, some of the delegates expressed their desire to visit our labs. So we have actually sufficient time after lunch, not in between. I mean, if somebody is interested, you contact Sneha, she will coordinate. Because we have ICPMS lab, IRMS lab, we have wet chemical lab. You just express your interest, she will take you, I mean, she will arrange at least, okay? Thank you.
So now it's a time for lunch. Lunch is already arranged. So again, we will come here by 1:55 so that we can start our next session by 2. Thank you. Good afternoon, everyone. So now we are going to start our session 9 that will be chaired by Professor S.K. Bhomik and Dr. Thompson J.K. So please take the chair and continue.
Thank you, Sneha. So in the post-lunch session, we have 5 talks scheduled. I think one of the participants is not there. Essentially, we will have 4 talks here. So I will be assisted by Dr. Thompson. So let's start with the first speaker. So I have the pleasure of inviting Shaival to deliver the first talk on fluids during metamorphism of the lower crust, the interplay with deformation. Shaival, it's yours.
Yeah, I teach with this every year. Right, very good afternoon. I've always noticed that somehow, no matter where I am in the world when I'm giving a talk, it's always the first one after lunch. I don't know why, but that is the case. Anyway, before I begin, quickly, I'll just tell you that while coming here on 15th morning in Kolkata airport, I met Professor Dasgupta, and as one would expect from a person of his stature, he asked me the most fundamental question possible, and it made me think. The question was, what are you talking on? And I could not remember what I was talking on. So the good thing was at least that when I came back, reached Trivandrum, so the night I had decided to look up my abstract, and I saw that I possibly wrote one of the best abstracts I ever wrote. One can talk about anything really, so it says nothing at all. So this is the sort of thing that I was able to put together from 15th evening. The title I couldn't change because Chalpati had commanded me to give the title many days back. So that's what it is, and we'll just roll through, and Shantanu can shut me up as soon as it's time.
So we have some time to
As usual.
Your time has not started.
No, chula I've already lost a minute. Okay, so we talk about fluids, and I hope you can all recognize that this is fluid here. And what's coming out of here is
something that our next speaker will probably be talking about, continents emerging from the sea. But this is actually a continent going back into the sea, right? So it's an extending zone. So this is the place where this is subsiding. Now, a photograph from the Archean to show, that I've actually seen this happen. So this is me about 20, how many, I can't remember, 30 something years back, 32. Right, so believe it or not, I had hair. The place that the sea we are looking at, right, is somewhere between these two continents. Little bit of the Tethys Sea that is entrapped between the two colliding continents, that is Europe and Asia with Africa. This is the Mediterranean Sea, right? And the part I'm going to talk about is a small fragment of the Mediterranean Sea, something called the Aegean Sea, right? So this is Greece, this is Italy, right? And this is Greece's great friend Turkey. So we are out here, and I'm going to be talking now about one specific little place. It's a group of islands called the Cyclades, or Cyclades is how they pronounce it. I'll call it the Cyclades, just to be a little clearer. The most famous one of these is the one which is just experiencing earthquakes right now. So this is on the part of a volcanic arc. It's called the Hellenic Arc, okay? And this is the island of Santorini. Now, this is probably one of the most beautiful places I've ever visited. The whole area, as you can see, it's a summary of the geology there. So you have a sequence of blue schist facies rocks, blue schist / eclogite facies rocks, overprinted by green schist. In places there's been a recovery. During retrogression, some parts of the terrain, there was partial melting. It became hot enough to melt under the amphibolite facies. In amphibolite facies conditions, that's in Naxos, in Mykonos and Paros. These are one of the few places where it's recorded. But I'd call your attention to this 3 red parts. So little bits on this island and one here. Now, this is a part which is actually old Hercynian basement. Now, Hercynian is about 360 to 230 or something like that. I'm bad at ages. I remembered things at the time of my MSc exam. I've promptly forgotten. But this is a part of an old belt, and it's all granite and granodiorite, essentially continental crust. On top of this, you have this blue schist sequence deposited. All of these are alpine in age. So you have blue schist facies metamorphism around 45 MA, overprinted by green schist metamorphism at 33 MA. So that's roughly the picture. So we're looking at this part here. What is most important is this red part is underlain structurally by the blue schists. Now the blue schists formed because of subduction. So because they formed by subduction and then by different processes came up and are currently exposed to the surface of the earth, it is important to understand, because the continental crust is lying below it, was the continental crust in the Cyclades subducted? Because continental crust, as far as we know, is too light to be subducted. That's why continental crust is 4 billion years old and the oceans are much younger. So it's a fundamental question that if the continental crust is underlying the blue schists, and the blue schists have definitely gone down, did the continental crust go down or not? So what I did was to study this little island that was demarcated in the last diagram. It's called the island of Sikinos. And here those little red parts, I've shown them in different colors. They've got 2 components. So you have some old metaphyletic rocks, which are metasedimentaries, right? And you have an intrusive, this is a granodiorite, this is the pinkish part, which is intruded the metasedimentaries. All above it is a sequence which comprises glaucophyne schists, green schists, and chlorite schists with a lot of marbles. So you have both calcitic and dolomitic marbles in the cover sequence. Now the blue schist sequence I will refer to as the cover, and the old continental basement is what I will call, I will just call it the basement here for the purposes of this talk. Now, continental crust is believed to be too light to be subducted. So in the Cyclades, because you see the continental crust lying below, was it subducted? That was actually my PhD problem. So what I had to do, among other things, is actually do mapping. And I mapped out this. This is doesn't appear to be a big area, but believe me, I mean, this is just a part of the area I mapped. And not just that, this is all topography. So it is not flat ground. So it was hard work, and I've mapped fairly every inch of this with nothing to go on. So it was triangulation that I had to do, and with a Silver's compass. That's about all that was used. But what is important here to note what the lithologies were. So we have
marble, we have graphitic mica schists, and you've got these pods of glaucophane bearing rocks. And inside the basement, you have these metaphyletic gneisses, and the gneisses were intruded by a granodiorite, of which a few xenoliths of the gneisses are still there, distributed within the granodiorite. But as you move along the contact, if you move perpendicular to the contact from this basement into the gneisses, you come across rocks which are extreme. There are signs of increasing strain, as I will show, and it becomes schistose. So essentially the gneiss becomes a schist. So it's sheared out at the contact. I call this the schistose carapace. Now, the rocks that you're looking at, just for fun, these are the marbles, right? And these are the glaucophane schists. These are glaucophanes, and the parts which are truly glaucophane are the light blue parts. The parts which are darker blue are crustites, which have more ferric iron in them. So there's a substitution which actually replaces this, and these can be correlated with changes in PT conditions. But I'm not going to talk about that, and I apologize for the fact that it's out of focus, but these are actually restored from old Kodachrome images. Now just take a look at the basement. So the basement rocks have metaphyletic gneisses. So now they have a lot of mica and alternating with quartzo-feldspathic layers, and you can see that they are isoclinally folded. Now this is all gneissic still, you can see the gneissic fabric, but these are then intruded by the granodiorites, and at the time the granodiorite intruded, it was associated with apletic dikes, and there are drag folds related to that within the gneisses. But all of this, as you go towards the carapace, right, these are cut across by a foliation which actually cuts both across the gneisses and the aplites. So what you're seeing is a new fabric in the carapace. So when you compare the structural orientations, foliations and lineations in the carapace, you can't do much with the basement, but if you compare the structures in the carapace with what you see in the cover sequence, they are exactly concomitant. So the structures, whatever the cover has experienced, the basement cover carapace has undergone that. Now, what do you see in the mineralogical transformations? As you go from the core to the carapace, you go from what looks like a granite with a few sericites, increasing signs of strain, and ultimately, we see that the granodiorite turns into what's a microcline schist. So you've got large clasts, porphyroclasts of microcline surrounded by a fabric which was essentially phengitic white mica. And here, in the granodiorite, within the metaphyletic gneiss, you find these completely randomly oriented flakes of phengite. And within the phengite, occasionally you'll see these garnets which contain very, very rare inclusions of glaucophane and chloritoid. So these are archetypal high pressure assemblages. When the same rock moves towards the carapace, right, the micas which are completely random here become aligned, become schistose. Again, this is a part of the schistose carapace, right? But here also the garnets, occasionally you can actually detect glaucophanes there. So you can see the high pressure assemblages. Now, the transformation in the basement metaphylites, essentially it has biotites. It's not got a very exciting assemblage, but the biotites are actually transforming into white mica, which is phengitic. So the reaction of transformation of biotite, right, to phengite, it actually requires water. So that's what is important here. The same thing that you see here is that when you get these pertites which are formed here, again the reaction requires the presence of water to produce zoisite, which is a part of the assemblage that's produced here. So if you summarize the basement and cover relationships, right, so you can see I did a lot of work in my PhD, drawing at least. So this is the metaphyletic gneisses, intruded by aplites. They're all cut across by these granodiorites. The granodiorites may or may not be linked to the aplites. It contains a few xenoliths like this, right? But as you move towards the carapace, this becomes a schistose, this becomes schistose. This part and this part are completely structurally equivalent. So the question is now, we know that water moved from in this area, that the blue schist sequence was saturated with water. Now, the blue schist, if it was saturated with water, when thrusting took place, what we see inside the basement are fractures, faults. And along this was cold, it got fractured initially. Water then migrated. What I believe is that water migrated from the basement cover, the cover sequence above, it migrated into the top of the basement. However, as shearing went on, as the top of the basement became ductile, it prevented any more water from going down. So therefore, the bulk of the rocks that were present inside the basement They never developed glaucophen. They never converted phengite as you move a certain distance away because water simply didn't percolate through. So now, since water was required to stabilize high pressure minerals like glaucophen and phengite, you did not get typical high pressure assemblages inside the cover, but you can see this in the part that is forming the carapace. So we now know that the continental crust must have been subducted. But this is just what I had to do for a PhD. Thereafter, I began thinking about the bigger question. Ductile, as what I had noticed but could not explain then, was that as long as you had fractures, water moved down. But as soon as that particular rock became sheared and became ductile, it would not allow water to percolate down. The upthrust then was upwards, so the water started moving up. So how does water then move in a crust that is granodioritic or granitic? How does it move in continental crust? Because this is a part which is when it becomes ductile, we see evidence of fluid flow. How do the fluids move there? So I'm just taking a random example, but it's not very uncommon. So this is a Charnockite. I'm taking this because it can be representative of a lower crustal rock. And in this, you can see this mafic dike. Now this mafic dike is an amphibolite. When you look at the Charnockites, you see the orthopyroxenes only very slightly marginally altered to amphibole. But when you look at this mafic dike, you see that it's completely amphibole and plagioclase. There's nothing else there. Okay. So all the water, there is a lot of water inside the dike and apparently no water surrounding it. So the part is that if the host rock remains dry, how did the dikes get retrogressed? How did water get in? So I felt then that there was something that was happening inside granitic rocks that actually inhibits fluid percolation deeper down. There must be some character to it. And this must have something to do with how water moves when the crust becomes ductile. So grain boundaries, where places where you have ephemeral fractures, where fractures heal, then fluids will most efficiently move along grain boundary domains. And therefore, because quartz makes up a significant part of these areas, so it's important to know how aggregates of quartz would behave if metamorphic conditions were different. So then, if you look at grain boundaries, we can classify them into two parts. Some which have misorientations of their crystal lattices at angles less than 15 degrees, you call them low angle grain boundaries. And if they're greater than 15 degrees, then you discriminate between the two parts as separate grains. So that is what a high angle grain boundary would be. Now they can be random, so they can be, whenever they're random, there is significant mismatch of crystal lattices across two grain contacts, so that has a higher energy. But occasionally, these boundaries can move into orientations in which there is a coherence, a periodic coherence, and because of which it's got a special boundary status, which means that it has a lower energy than normal high angle grain boundaries. Okay? So this is an old concept in metallurgy. Now, to see what we were interested in, we wanted to see how aggregates of quartz might affect water percolation. So we looked at a rock called quartzite, which contains a lot of quartz, and we did all these things to try and see what happened to quartzites deeper inside the earth. So we collected quartzites from different metamorphic grades. Now how do we know that these are different metamorphic grades? Because we looked at the rocks around them. So these are from lower green schist facies conditions, upper green schist, amphibolite and granulite. Just take my word for it, I did not make a mistake as to the grade of metamorphism here. So when you look at it then, what we did then was atomic force microscopy. After a lot of EBSD work, I'm just showing you the net effects, we applied a technique called force distance spectroscopy. What you do is to use the atomic force microscope, which looks upon things, images it at the nanometer scale, and what it does then is indents the top surface to find out what the strength is across that surface. Now what we noticed is that if the amount of surface deformation in quartzites which had been metamorphosed under the granulite facies was significantly greater than those quartzites which were metamorphosed in the green schist facies, which means then that the contacts, across the contacts, the bonding in granulites appears to be stronger. So quartz-quartz grain boundaries apparently become stronger at higher temperatures, and this is counterintuitive. Why should this happen at all? Now, another student of mine looked at this and from a high-grade terrain in which you had quartz along with a number of other minerals. When you look at the quartz phases, right, this is the gray part, you see these blue parts, red parts, and the yellow parts. Now, the blue and the yellow are high-angle boundaries, and the red parts are low-angle boundaries. So the low-angle boundaries actually create undulose extinction. But the high-angle grain boundaries, these separate grains, and these have misorientations which are much larger. So I've already had a warning. So if you now, using the EBSD detector, try to see what the misorientation is between two quartz grains, in this particular part, statistically speaking, you can see the peak that a predominant number of grain boundaries have misorientations of exactly 60 degrees about the C-axis in quartz. So two neighboring grains of quartz, their lattices are misoriented by 60 degrees. And this is characteristic of a type of twinning inside quartz called the Dauphin twin, something that you cannot detect optically. Okay. So now these grain boundary in high-grade metamorphic rocks, they appear to have a higher amount of Dauphin twin boundaries. And these Dauphin twin boundaries are oriented at 60 degrees around the C-axis. These Dauphin twin boundaries are actually CSL boundaries. These are high-angle grain boundaries. But if you look at their misorientations, they actually have a much greater periodicity along their lattices, which is why they are much lower energy than other parts of the lattice. Now, metallurgists, what they do is when they want to improve the quality of a material, they use coincidence site lattice theory. Now, what this does, they do it to enhance resistance to corrosion. And corrosion is related to percolation. So what happens is that they take the material, deform it, anneal it, deform it, anneal it, and they optimize till the material acquires the highest proportion of CSL boundaries. At that particular point, the material becomes most resistant to corrosion. So this process, it's called grain boundary engineering. When you do this annealing, the material actually can withstand it. So our interest was, can this happen in rocks? They've seen this in metals. Now, what we saw is that definitely something's happening. A much larger proportion of Dauphin twin boundaries are actually developing, right, in these high-grade rocks, where these Dauphin twin boundaries, which are the yellow boundaries, when they intersect these normal grain boundaries, you see that it turns red. These are other parts of the boundaries which begin to follow other twin laws of quartz. Now, whenever something follows another twin law, it means the lattices have a twin relationship. But it also means that when you actually compare the orientations of particular faces, you notice that between neighboring grains, some faces are coincident. This follows the Japan law and the Sardinian law in quartz. So it means then, whenever you have some amount of coincidence and it turns into a symmetry relationship, then the amount of energy associated with that particular boundary is less than what you would have in normal grain boundaries. So what we think is that when you have quartz at very high temperatures, as indeed we have when it experiences extreme metamorphism, and then when it cools below the alpha to beta transition, then it actually switches from beta quartz to alpha quartz. And during that transition, the wrong faces can develop in two different symmetries. This cannot be identified optically. You have to do it by electron backscatter diffraction. When this happens, you get these two parts of grains which used to be the same, just become twinned. And then you have these Dauphin twin boundaries which then intersect the normal grain boundary, converting them into other kinds of twin boundaries. Now, what does it mean? What effect would this have on the overall part here? It would effectively reduce the grain boundary free energy. So once it does that, you can actually test this again against the atomic force microscope. So when we look at it in granulite facies rocks and you look at it in other kinds of rocks, you see that across grain boundaries, the structure is different. So here you have bridges, the other places you don't have bridges. The distance between the two particular lattices becomes more indented after thin section polishing. So the indent that you create during polishing is proportional to the strength of the grain boundary. So sorry, I've almost overrun, but it's also stuck. Because the timing is over, I think. It's almost done, actually. It's good. Okay, never mind. So it's actually the second last slide. There was a conclusion and there was a thank you. But anyway, so the conclusions are effectively, we still don't know what actually stops this percolation. But we think that something is happening, texturally, definitely something is happening. Whether this has an effect in metals, the question is, would it have an effect in rocks? Because if it does, it might give us some explanation as to why granulite facies rocks are dry. They're in the lower crust. If they undergo this transition, then this is the reason. It might make granulitic facies rocks which have quartz more resistant to percolation. And in that way, it might actually help keeping the rock dry even as it comes up to the surface, even after inversion. So sorry for overrunning and thank you very much.
we have some time, so.
So my greatest rival.
Please.
Hey, you did that.
Excellent talk, but this is not really a question related to your talk, but I was wondering why the Greeks write the stratigraphy upside down.
Why the?
Greeks write the stratigraphy upside
But
down.
I wrote it, and I wasn't really Greek. I mean, I was a student, so that if there are answers.
Any other query? Excellent,
Please,
Dr.
please,
Val.
please.
Of course, as usual, Saibal, I enjoyed your talk. English was so good, so nice. One small,
entertaining, you mean?
excellent. Yeah, I always appreciate you. Only one small query is, you're talking about that heating of all those grains, mostly continental crust or what are the continental rocks, mostly silicate rocks. But you are comparing with the metals. Metallurgy is what they do, but the rheology of metals and the silicate minerals may be different.
It's funny you asked this question. This was one of the major problems which we faced when this is being reviewed, actually, is that there are a lot of people who think that this doesn't happen in silicates. Geometrically, there is no reason why it should not happen. Because lattices, when they rotate into particular orientations, you will get CSL relationships. Whether that will make it more impermeable or not, it makes it stronger. That is what we've been able to demonstrate. It will affect rheology. And it might make an apparently higher temperature rock stronger. But whether it will make it more impermeable or not, that is something that has to be demonstrated. We haven't done that yet.
Thank you. Thank you very much, Saibal.
Sorry? Barely. I don't know now after I finished, but the thing is, of course, I'm using up time, but the thing is, the first time I went there is in October or November 1991. And I carried 4 apples from Athens. And when I went there, I didn't know where it was. So I just asked, and they told me there's a ferry at night. So I reached there. I landed at 2 in the morning, and the guy who was at the quay, when the ship came in, they told me that I have a room, you can stay here, and I stayed there. But I mean, thereafter, I never saw any people for 3 days. What was more tragic was that I had no food for 3 days except for those bag of apples. So the first 3 days of my field work, I had an apple in the morning, apple in the afternoon, and apple at night. The last day I couldn't withstand. The 4th day I went up to the village, and there were a few more villages.
Shrival, we can.
They said, that was it.
So our next speaker is. Our next speaker is Dr. Priyadoshi Chaudhary from Niger, Bhubaneswar. He will talk on emergence of continental crust on early Earth. Priyadoshi.
Am I audible? Hello, am I audible? Yeah, yes. Thank you, Professor Bhumi, for this. Sorry. Yeah, so one thing I just realized, so my topic won't be that hard for petrology. But what I'm going to tell you is basically draws an inspiration from petrology and then tries to answer something which is, I think, is far more fundamental. So it's basically the emergence of continents. And when I say emergence, it's basically subaerial emergence. Now, why do we care about it? Because this emergence creates what Earth has its very unique thing, is that the oceans and land. And this forms a fundamental geochemical cycling between these reservoirs, that you have atmosphere, oceans, and the solid Earth. And once you have land, you can affect through weathering its ocean chemistry, atmospheric chemistry, and through that also climate regulation, because you can suck up carbon dioxide from the atmosphere and water. Also, there are other nitty-gritty processes. I'm not going to that. But this thing is therefore fundamental in understanding the long-term evolution and the impact of solid processes on the surface. Now, this is just a diagram, which on the left-hand side, if you see, this is basically 0 is the MSL, mean sea level, and this 5 is towards the mountains, and the 7 is ocean floor. This is just the depth. Now, this distribution shows present-day topography of Earth's surface, taken the data from the NOAA. So, most of the continental shields lie just above the MSL, as we know. And then you have mountains like Himalayas, Andes, Alps, which falls in this region, and then you have the ocean basins. So this dichotomy in this topography or bathymetry is what we call the bimodal hypsometry of Earth. But the question is, when did it arrive? So the Earth did not possibly have this thing right from the beginning, or it had, so we don't know this. So the question therefore is, when and how did it all start? Because then it will kickstart all these cyclings between these reservoirs. So there are 2 aspects to it, when and then how. So And each of these are highly debated questions. I cannot go into the detail of all of them. So for the initial, I will just briefly describe about the when part. So if you look at it, so the same diagram I've kept here, this is the present day. But here we have put in between, this is a schematic, but schematic diagram based on the evidences that are preserved in the modern day rock record. So you can get the data from the sedimentary weathering paleosol horizons, and then there are plastic sedimentary rocks, as well as geochemical tracers, which tell you that perhaps if you combine all of these evidences together, you may have land, stable continental crust, emerging somewhere between 3.2 billion years ago. And that timeline is, of course, not like hard nailed in the rock record. There is plus minus, of course. But then you start emerging this land, and then you progressively increase the areal extent of this land, at least until 2.5 GA. Now, this comes from all this record, and I'm not going to detail of it right now, but I'm happy to do that if you want. And so therefore, you can consider this as prior to that, you may not have as much land as one would wish for. So that is what we called water world situation. Then you created first land around 3.2, 3.3, and then it increased progressively between Neoarchean and Paleoproterozoic. So then the question is, this first land formation in this time, what contributed to it? What drove this land emergence? Because on modern Earth, plate tectonics control the topography. But as we now know, the plate tectonics may or may not was present in the Archean. The tectonic connotation, the entire framework is debated. Therefore, its control on this topography and all those things are also debated. So how do we know these things? So here I kind of looked back into the magmatic rock record and the metamorphic rock record. So it's basically the same thing for me. It's petrological rock record. So if you look this diagram, so I have blocked my own diagram, it seems. Anyways, so this is the age of the Earth at 4.5 and 2.5. The y-axis is zircon hafnium, initial hafnium. And if you just look, the main takeaway point from this is that you have a lot of magmatism that is happening between 3.5 to 3, at least for Shingbum. For Kapwal, it is even beyond. And a major chunk of this magmatism contains is from the juvenile nature, that is from the depleted mantle curve. So what it fundamentally means that you have been creating new mass, adding to the lithosphere. Now there are also reworked signature in this hafnium. That means the mass that you are adding, not only are being the new mass, they are also undergoing crustal differentiation. So therefore you have created a new mass, and that is continuously evolving in nature. So over that time period, you added mass and evolved it. So that is basically the making of the continental crust in these cratons. But if you add mass and make it less dense, chemically evolve it, it will have some impact on the isostatic balance of it. So the question would be then, how thick was the crust and what was the density of it? As a proxy for the density, if you look, this is again taken from the Shinghun data. So if you plot it in the modal abundance of the plagioclase components, you can look that the early ones were rich in 200 electron zermite, that was more sodic, more primitive in the sense. And if you go along with the time, it becomes more and more potassic, that is more evolved. So with that, the question is, how can we trap this thickness data? So there comes this idea that if you have a crust, the TTGs generally form in the deeper crustal levels. That's what we have understood so far from the Archean geology and understanding the melting and metamorphic paradigms. If that is so, then, and if I get a TTG whose chemistry has not been modified post this formation, then the melting conditions of the TTGs can give you a first order approximation of the pressure, and that pressure can be converted into depth. Again, I am saying a first order approximations because this cannot be an accurate pressure or depth value, but an idea of it. And if there is significant increase in the depth, it correlates kind of with the crustal thickness. Again, this can be a minimum crustal thickness, as we don't know exactly it should be at bottom, it could have happened here also. But how to get that? So we do that, we can do forward modeling. We can take a basalt, which is generally considered to be the precursor of these TTGs. Then you melt it, melt it not physically, but to model it along different geotherms that we know may have existed in the Archean. Get the melt compositions, do tracer and partitioning, and then compare this model melt compositions with the one that you actually found in the rock record. And then see if there has been a change over time. So to do that, we first took this, the data. So basically you can divide the basalts in the Archean into general category, into one called enriched, one is called depleted. Enriched means enriched in the incompatible elements, and the depleted means depleted in the incompatible elements. So if you take that, and generally just thought also that enriched basalts are the major precursors or source of Archean TTGs. So if we did that, we take the average composition of the Archean basalts, Neoarchean basalts, which is this one. We then modeled its suprasolidus conditions, melting, which is here, saturated with a kind of water which may saturate the rock at 12 kilobar with an approximate ratio of oxygen. And then we consider melting happening along these three different geotherms. The idea of geotherm is that, modeling at a geotherm is that then it kind of reciprocates the tectonic setting rather than modeling it at a constant isobaric conditions. So the idea is if we take the melt along any one geotherm and see how the melt is changing in terms of its volume and composition and the residuum that it is interacting with, we can trace back the composition. So as first order thing, I'm just plotting one thing to show what is more important for me is that if you look at this is the temperature axis and this is the proportion of the different phases in the residue with the melt, which is the L here. From the first order thing, we can see that the hornblende is decreasing in both the cases along both the geotherms as the melting progresses. At the same time, garnet is increasing here also, here also. But the extent to which garnet increases is much more when the melting happens along a relatively colder geotherm as compared to a hotter geotherm. So therefore, if your melting happens along greater depth at a lower temperature, you would expect more and more garnet to be there. And if that is true, then the equilibrating melt would have certain characteristics through which we can capture this. Excuse me. So that's exactly what we try to do. Since again the data set which we took from the Shinghung Craton, which includes a lot of data sets that others have published, including Shukan's data there. So these are the data set from 3.4, and we modeled it and we figured out the melts that is forming around 1000 degrees centigrade are the best fit. The melt fraction you cannot see there, but between 16 to 30% of the melt. But if you look here, as the younger ones go, we can see that these fits are not a good fit for this darker shade. For that, we need a melting along a colder geotherm. So therefore, if we convert this melt fractions, the bracket ones of the pressures, we get a pressure difference of around 3 to 3.5 kilobar. And give it this pressure conversion to a depth that changes to around 12 to 14 kilobar. So as you know, the ages of these melts also. So what we can get here is another way of measuring this thickness, but from a more empirical standpoint, that you have a lanthanum-meter-BM ratio and the age. And if you see that, we have around 12 kilobar change between 3.45 to 3.25, which is symmetrical or analogous to what we get in here. So if we have this amount of thickness incorporated during this time, with the fact that your crust is becoming more and more felsic, it certainly will have an impact on the isostasy. So here we did isostatic modeling. I just put the basic equation, but there are a lot of assumptions went in. The key point is that the various parameters have been changing with time. So here is the time, here is the area of the continental crust, and there are a lot of models because many parameters could have varied. The fundamental thing is most of the models show that you can start forming the land or the subaerial crust between 3 to 2.5. There's a major rise in the aerial fraction of land above the oceans between this time, which is kind of what we also see from the rock record. So based on this, we kind of propose that the two-stage model, the first stage is the first appearance of the stable cratons, and they kind of peaked above the ocean water because of this process where you can form most likely in a non-plate tectonic setting, that you create a plateau type of basin, plateau of setting through which the mantle upwelling can provide some sort of heat and mass, and that mass then continuously differentiate and form a thick felsic stabilized craton, and that can then emerge above the oceans. But soon after these cratons form, you may end up in having something called convergent tectonics. I am not going into the details of whether it's a plate tectonics or not, but you start forming some sort of compression orogenesis, and that then kicked further the topography, the aerial land extension. So therefore, you have a continuous rise of the land once this phenomena kicked in towards the perhaps across the Archean Proterozoic boundary. Now, having said that, once you have land, it will have an impact on the ocean and surface dynamics, as I was saying. So this is the diagram of strontium in seawater. Again, is the time. The blue curve shows the strontium isotope evolution in the seawater, but this is in the mantle. So seawater generally mimics the mantle, but the point of departure is generally considered to be the point where detritus from the weathered felsic crust in the form of apatite weathering is coming up basically. So this is the dashed line is an older curve. But recently people have compiled the more and more data that is coming out of it. And we see a departure between 3.5 and 3. And then it starts picking up by 2.5, and then there is a more complexity there. So this data is also kind of correlating that you may have started land and weathering of it sometime during the later stage of Paleoarchean and then throughout until the Neoarchean. What it also does is that if you have land formation in small ponds, small areas, it will start creating local silicate weathering. And that can affect the local climate. When I'm saying climatic cooling, I'm not saying the interplanet cool down, by the way. Because when we see that the presence of glacial diamectites in the Pongola supergroup. Pongola supergroup is likely the first largest intertectonic sedimentary succession that has been studied extensively. And I think the Shinghum also has that, which is, I think we should study that more, and a bit older than the Pongola. But what is striking in Pongola is that Pongola has a glacial diamectite horizons, which certainly thinks that you have a climatic cooling. Now, these are all temporal links, and much needs to be studied in terms of the actual dynamics, how this can affect in terms of quantifying it. So if I just put everything together, so these are the proxies, this is time axis. These are the proxies of this emergence. You have sedimentary rocks, subaerial volcanism, Aeolian sedimentation, etc. And these are the features that kind of affects it. So I cannot see, sorry for that. There is a dashed line between 3 to 2.5 GA here, where you can start creating all the emergence proxies. At the same time, you have glaciation, photosynthesis, and a change in the oxygen-isotope systematics. So with that, yeah, thank you.
Thank you. Such an excellent talk. So we have some time for discussion.
Yeah. Yeah. 3.5 to 2.5 mostly, yeah. Sorry.
That's the time boundary where this controversy still runs, whether the static lid or the mobile lid operates for the arcane Crayon.
Yeah, kind of, yes.
Okay, but you use the TTG compositions to predict the older crustal composition, but you have a very stable platform with high silicate weathering. So definitely you will have an input of continental sediments going into the TTGs.
Yeah.
So how do you account for the involvement of sediments?
Wait. If you have a high input of sedimentary, then you would not have TTGs, first of all, because you will create a potassic melt.
Yes, true.
End of it.
Yeah.
You have to have something which has a very low supracrustal input.
Yes.
What you're talking about is the transitional TTG.
Yes.
And that's why I said you cannot have those melts which have been hybridized later on or have undergone huge fractionation. These melts have to be primitive. Primitive in the sense that you're creating from the basalts. That you have to ensure first, of course.
Yes. So that's such why epsilon hafnium versus age, you have both evidence for juvenile magmatism as well as crustal reworking.
Yeah, but I just use the TTG fraction.
Yes. Okay. Fine. Thank you.
Just the idea of the changing composition to potassic granitoids, right? That from Taylor and McLennan has got that from the sedimentary record in Greywa case.
Yeah.
I was just wondering, say, the issue of supracrustals, right? So you have sediment fraction there also. Did we not have a freeboard then?
So I did not touch upon that. I think we did have, but that's not a mature stable land, because if you look at the entire package of the sediments, that's still a greenstone belt. You have a clear volcanism before and after that. So we did have a freeboard, but that freeboard was a stable land. Do we like the concept of land that we know now, for how long it was stable and how much did it contribute? We certainly have an amount of land, but I think those lands were kind of confined in the sense that its areal extent and the timing of for the duration of its emergence. So those that we see there are perhaps, well, you can always challenge that, is a cryptic emergence as we call it. And it may have resulted from plateau formation or kind of an extensive period of volcanism in a short period of time. Because soon after the formation, this entire this topography collapsed, and that we have evidence for.
Okay, just one thing on the, we do see even within, say, Barberton in the Swaziland supergroup also, I don't know what it's called now, but within that group also you have unconformities.
Yes.
So how do you explain unconformities?
So those are exactly the same thing. That's the period when the crust was in the making, right? So the Carpwall crust was in the making, and during that time it kind of wobbled in and out of the sea level. Absolutely it did, no questions asked. But that is a land, for example, you can still have a seamount. That's what the first slide is. You can still have seamounts sticking out of the water, but that's not the stable land that you will have it for a long time. It will kind of vanish out after a certain time. So therefore, the emergence of land has also a connotation about how we define land. Do we consider continental crust when it is in the formation during the period, or when we consider when you have kind of stabilized into a stable lithosphere? And that distinction is very important into kind of when you are trying to answer the questions when. And much of the ambiguity that we see in Archean, I think, is personally because we cannot delineate that. And yeah, that would be my answer.
So, okay, this is the last one. Ramon, please. Implications of this preservation potential of these rocks.
Of preservation of what?
These means either old TTG or these things transition.
Yes, yes, that we have to live with, unfortunately. If you do not have a TTG record preserved, that we can see. But now what we're trying to see is the zircons, because the detrital zircons could have a much better potential. But the problem is, what I always try to do is that not to go for the empirical proxies, as I was saying, lanthanum, ytterbium, but rather to go for full-scale thermodynamics. So if we can figure out one way of doing that is to take the zircon trace elements and model that and to see whether this theory applies or not. Of course, that's the one thing that rocks cannot do, but detrital mineral record are better suitors for that.
Thank you. Okay, so with this, we now go to the next stage. I request, thanks, Priyadarshi. I now request Dr. Thompson to conduct the last two presentations here. Please.
Thank you, Professor Bhaumik. Moving forward, now we will have the third presentation in the session by Dr. Mahmuda Talukdar from IIST Shivpur. So I request Dr. Mahmuda to present her talk on giant epidote formation in parts of anorthosite layers of Sitamundi, Tamil Nadu. So Mahmuda, please.
Okay, good afternoon, and my talk is much more simpler now after such an enlightening talk of Priyadarshi. So as you can see, today I will be talking about the giant epidote formation, and from the picture only you can identify that this is so beautiful, and I cannot resist myself to go into the making process of how it was formed and what is the story behind and so on. Okay. So this is part of the Sithampundi layer complex. This is where, this is where you get the Sithampundi layer complex within the southern granulite terrain. And this is the lithological map of the Sithampundi layer complex. And still we are following Subramaniam's map, which is so very good. So today also we modify it and present it. It's rather detailed mapping. And here in this Sithampundi layer complex, this is the position where mostly we get all the data, all the work is done, most of the literatures come from this area where we get this kind of mineralogy. That is, we have anorthosites within which we get so beautiful corundum bearing mineralogy. We have chromatites, and within that we have the clinojoicite over here, which is a first order, means first generation clinojoicite. We have a second generation of clinojoicite as well, but that is what we get from the epidote group of rock in that area. Rather than it is more well renowned because of the almost n-member composition of anorthite content. And here the clinojoicite what we get is only around 4 to 6 pistosite mole percentage. So before going into epidote, just for the students I have kept this composition over here, that what is the difference between the clinojoicite and epidote, that we have the Al content more in clinojoicite, whereas we get more Fe3 content in the epidotes. Okay, so moving on. In this part of the location, we have rather this weird mineralization. It is not a weird, but the appearance is very beautiful rather. So we have this epidote formation over here, and this is how it looks like. The first picture shows, you can identify the the giant formation, the beautiful epidote formation over here, which is haphazard in orientation. Here you can see rather more oriented. So we have deduced that some of it were haphazard. In some plane it is rather oriented. And we had some patches of amphibole and epidote bearing mineralization present over there. So what did we deduce? We have deduced that this mineralization had overlasted the deformation. We have more, rather we should call it a syn to post syn tectonic mineralization over here. Next we went to the microscopic textures. What we have seen that this epidote formation is zoned, means the epidotes are rather zoned from core to rim. When we look into the other mineralogy, we have seen there were presence of clinopyroxene within the plagioclase grains. We have amphibole development rather from the grain boundary. We can see from here, though it looks like it is in the core, but it is actually moving from the grain boundary of this clinopyroxene, and this clinopyroxene is also not as we see in the prograde type clinopyroxene, but this is more grain boundary or intergranular growth of the clinopyroxene over here. Here we have found that there is an equilibrium texture rather not interacting with clinopyroxene much. The amphiboles grow most of the time, the amphiboles replacing clinopyroxene. We have a rim of different plagioclase formation near the rim. The amphiboles has replaced epidote also we have seen here, and here also we have some evidences. Now looking into the mineral chemistry, what we have seen that these different epidotes from different position from the grains, we have seen that the core were more of aluminum content, the rim was more of Fe3 content, and the smaller grains were rather more of Fe3 content enriched, and only the cores preserve this aluminum content more in the core. Okay. So we moved on to the reaction modeling. So we, through C-space, we have just modeled the reaction, how it is formed. This is rather the general reaction which we followed. What we have seen that during the rim and the core formation, there were good amount of water required, Na, potassium, and iron is also required during the process of making. This indicates the fluid induced mineralization. And when we look into the amphiboles, where I forgot to mention before that in the, yes, so in this hand specimen scale, we have tried to, these signatures that there are two layers of amphiboles. One which defines the fabric, and ones which are these kinds of amphiboles which does not define the fabric and is more patchy in appearance. But in the composition wise, we do not get anything in the any difference, rather most of them are similar in the composition. Whatever texture you take, they become more or less similar in composition. The anorthite content is rather what we have expected. The cores are more anorthitic. We produce more albedic nature of plagioclase after the reaction, and that's what we have seen in the composition as well. The reaction modeling also tells the same. So we have thought of taking one with epidote and amphibole formation. Can it be synchronous or it is different position, because some signatures were there where we thought that amphibole were replacing the epidotes, and there were some signatures where the patchy appearance is there. We feel that they are synchronous. So we thought of modeling two processes as well. So we found that it is as well fluid oriented, means fluid induced metamorphism or metasomatism rather. So the most important thing what we have seen is the change in the composition of the epidote. This change in the composition from 12 pistacite mole fraction to the 22%, not mole fraction, percentage, it's 22 pistacite, which according to the authors that they are the proxies for the high pressure temperature, pressure by temperature, they are the proxies for the high pressure conditions, and they are the proxies for the redox conditions as well. So here we are getting 12, which is high aluminum. So the pressure by temperature condition was rather high over here, whereas here the pressure by temperature was rather low. Next assumption or next interpretation is that the redox condition has changed. So within a growth system, a mineral is growing and the fluid which was coming in was having a different redox condition, and it is changing within the same mineralization event. So that was what actually we have to look in, that in what pressure temperature we have to get this kind of mineralization. So we try to look into the present pressure temperature condition, which is already published by me and Priyadarshi and also by Shreya from the center core of the Sitampandi layer complex, that we have got a clinozoisite bearing peak assemblage, which gives rather pressure and temperature more near the 11 to 12 kilobar pressure and 750 degrees centigrade, or rather here it is more likely to be 800 degrees centigrade. It goes on to the retrogression where we have lower temperature pressure conditions to the second variety of clinozoisite. But can we compare this with our epidote formation? What the difference we got in those regions, the central part of this Sitampandi layer complex, we have different variety of anorthite, we have different variety of clinopyroxene, we have which is rather more of aluminum content. Here we have very less amount of aluminum content. Here corundum develops and clinozoisite develops. We know that the general bulk composition have more of Al. Now we can interpret that. Here the general bulk composition is more of less of aluminum content. That we can understand only. Now, one thing we know very clearly, that to form this kind of a giant mineral great size, we need to have a slow cooling. We got that information that it has to be cooling or decompression, which rather decreasing pressure by temperature ratios. So that has to be a retrogression process, not a prograde process. Next we have another information, that is it is syn to post tectonic. So it has to be after the main peak metamorphism. Then we have to keep it here for rather long time so that we can have this giant mineralization. So with this note, we deduce that it has to be a slow cooling process in this area. Other than that, we cannot develop such a giant epidote mineralization. So this was our conclusions only, that the epidote amphibole formation overlasted the deformation. More specifically, they are syn to post deformation. Indication of epidote amphibolite phases or slow cooling enhancing the grain size. The fluid redox condition changed considerably with a single mineral formation from core to rim. And from the other compilation of age data, the peak assemblage or the peak metamorphism took place near about 2.47 GA, so it was after that. We don't have the rather discrete or specific age data for the cooling, and we can do it with some other proxies. But you can understand that this is not a very vigorous work, as we have reached not a very conclusive result. So we prefer more, okay, this is for the cooling rate, slow cooling. So we actually, I am here to get more of advices rather giving my own conclusion over here. We have got this, we have to see the different generation of amphiboles. We could not deduce what is the peak pressure temperature condition and the lower pressure temperature condition because we did not get two varieties of amphibole. But texturally, there are two different, but compositionally we cannot deduce. This may happen that the fluid induced have homogenized all the compositions of amphibole, but we never know, we don't have that data. Then what process have gone through that the Sitambundi layer complex in the main zone, we have that corundum formation, aluminum increased, metasomatic alterations, but here we don't have that. And in a very localized zone, we are having this kind of mineralization with such giant epidote formation. So we have to look into this, and it is open for good advices. Thank you.
So the questions, suggestions, please.
Of course, I am happy to listen to your another site. I happened to visit another site last year, 2023, Chittamundi. And how far you are these epidote mineralized rocks from that, what is that place called as Karangalpatti?
Sir, actually the local names I am also not
The Karangalpatti is the place where you have extensive chromatites.
Okay, so it is
Where all
rather
this
in the
GSI
central zone. So it is not very far, but when you go round way through the main road, it is near about 20 kilometers.
Okay.
So through the villages and all, it may be short.
Maybe next time when I go, I will try to see.
Yeah.
I am quite excited to see these giant epidotes.
yes.
Thank you so much.
Just a comment, since you wanted advice, or I can tell you that exactly the corresponding thing I have seen in the blue schist I told you. So you saw the amphiboles with an Fe3 plus zoning. They coexist with epidotes who show corresponding zoning exactly of that form. So maybe in the amphiboles it's homogenized because of the higher temperature here. There the temperature was below 450, but the pressures were 10 to 11 kilobars at least. So maybe, I mean, I don't know if the pressure has an effect.
Has an effect, but I could not deduce, since I'm not getting different generation, I cannot deduce the...
Yes, but the only thing is, you're saying the giant epidotes, enormous epidotes I had in that same case, temperatures were very low. So so it may not be the temperature which is responsible.
It is the pressure.
Pressure plus fluid maybe,
Fluid
I think I said.
is because here you get 9.9 anorthite content, and that is also told that you have a good fluid partial pressure over here. So fluid content was high initially, and full here amphibole formation has happened. Though the next layer only you have garnet and pyroxene and these phases, but in this anorthosite layer you don't have any garnet, you don't have any pyroxene. Very rarely you get pyroxene. So here in this layer it is very fluid enriched. That is for sure. So
Okay, one last question.
Momita, do you find any oxide or sulfide minerals in your rock?
sir, in this particular area, no.
Because I have read Daniel Harlop's paper 2005, they expressed this sulfide and oxide minerals to produce high photo condition like this. So you asked about this
But
redox
we did
stage.
not get, sir, if you have seen the texture, we did not get any complex mineralogy, no accessory minerals. It is rather simple clinopyroxene, epidote, and amphibole. That's all. But we have to see, if you see the clinopyroxene, it's also not normal prograde varieties, like rather skeletal growth through the grain boundary. It's not porphyroblastic also. So I don't know.
Momita, one observation that I have here, you have two clinopyroxene, one from Sitampundi and the other one where you have shown the giant. if you see that XMG of the two pyroxenes are different.
Different, yes.
And also the epidote that is formed, in these two cases, the ferric is different.
Yes, sir.
The magnesian clinopyroxene in that domain, the epidote has lower ferric, whereas your more ferron clinopyroxene has yielded in that it has more pistacite component. Have you tried to see the ferric content in your clinopyroxene?
Ferric content, yes, sir, but now...
Because instead of oxidation,
Yes.
it's always the potential that you have oxidizing fluid. You can also have some sort of closed system situation where the ferric in clinopyroxene can contribute
Sir,
to the ferric, because you have a correlation here.
Yes, yes.
That your two pyroxenes have different iron, original iron content
Yes,
here.
yes.
So you can have a look here whether your pyroxene also have some ferric here.
Yes, sir, they have.
They have.
They have. It's very less amount, but still they have compared to the normal clinopyroxene over here, which is less ferric and more Fe2 plus. Whatever element is present, it is Fe2 plus. But rather here in this zone, it is Fe3 plus. Small amount is there.
Okay, thank you. One last question.
Momita, this coarse grains, I mean, just have a look of possibility of fluid assisted processes.
Yes.
Because recent studies shows that fluid assistance can actually create very fast coarse grains.
Coarse grains.
So
that's why is actually we believe that this is fluid induced and fluid assisted mineralogy only.
yeah.
Thank you.
Thank you, Dr. Momita, and thank you
you
for
so
all
much.
the lively discussion. So moving on, we have our next talk scheduled is by Dr. Sayandev, but I think he's not around. So we'll move forward to the fifth talk in the schedule. So that's by Dr. Aditya Naik from ISER Mohali. So it's on assessing the linkage between garnet zoning and metabolite Annexis. So I welcome Dr. Aditya to the talk.
Good evening, everyone. So I'll be presenting on the link between Garnet Fractionation and how does it affect the metabolite Annexis. So, and we'll be first exploring the theoretical considerations using average metabolite composition given by Ag et al. And then we'll move on to its application to Sad-Mata complex of metabolite gneiss. So in a magmatite, what happens is metamorphism happens when it reaches up to a certain temperature, say 700 degrees Celsius. The rock undergoes partial melting. It loses its low temperature components, and which causes bulk composition change. So mass balance is not preserved at this point on the rock scale. So if you are using its composition, it's not the original protolith, it's the changed protolith. So for that, we have to basically perform melt reintegration procedure, which was given by White et al. 2004. But what happens is, they did not consider the case of zoned minerals like garnet, which have slow diffusivity of elements, which causes them to form growth zoning. So basically, there are two processes that are happening simultaneously during Annexis. One is garnet growth and fractionation, which is usually not considered, and the Annexis part. So for garnet fractionation, what happens is there is an original system. When the garnet forms, it sequesters some component within itself. But if the diffusivity of outside elements cannot keep up the pace, it forms a zone of depletion which does not allow other garnets to form near this. So after this, then we have second, because matrix composition has changed, second generation of garnet can form, similarly third, and it continues on till all the components are completely exhausted, or the rock has underwent 2PT condition where garnet is not stable anymore. Now, the second portion is melt generation. So melt generation can happen in two ways. One is batch melting, where rock melts, but remains in equilibrium till the annexis is complete or some threshold has been reached. The second is relay melting, which are generally happening in the high strain areas, where each individual parcel of melt that is forming will segregate out of the system instantaneously. It does not equilibrate with the original restite. Now, okay. So a typical melt integration workflow is we have to identify the peak PT condition using isomode intersection. Isomodes are basically volume of anhydrous minerals that are present in a thin section or average of multiple thin sections. Now, so after that, we reduce the H2O to reduce the chance of retrograde minerals or basically contribution of retrograde minerals that have formed during the cooling of rock. Then we find what is the melt composition just at the solidus, and then we increase its proportion, and we keep repeating this till the K feldspar at the lowest subsolidus temperatures disappear or convert into muscovite. So in this case, the first step is the critical portion where we have to identify the peak PT condition. Now, what it is generally assumed that complete garnet is in equilibrium with the matrix when we are performing melt reintegration. But in this presentation, I'll show you that it's not the case. So what happens if garnet core was isolated from the matrix? We'll see. And then what are its effect on annexis and melt composition, both in terms of major and trace components. So we'll be performing two modeling practices. First is phase equilibrium modeling, and the second is trace element modeling. For phase equilibrium modeling, we'll be using Perplexx with Holland and Powell dataset and these mineral models. For trace element, we'll be using batch and relay to basically cover all the possibilities that trace element content of melt can occur due to fractionation. So we'll be modeling on three PT paths, which is normal subduction zone path, normal geotherm or stable continental path, or the orogenic geotherm. Now for each PT path, we'll be performing 4 scenarios. One where no garnet of melt fractionation occurs, which is batch melting, and we'll be using it as a baseline. Then the second is garnet fractionation, only garnet fractionates, but melt does not. Only melt fractionates, but garnet does not. Both fractionates is our final situation. So this is the composition we'll be using. So let's start. So starting with the highest P by T nature of PT path, what we find is as there is no significant change in the mineral assemblage or mineral panagenesis, except for at the very highest grade, which is around 900, when biotype basically disappears from the system, in the case where garnet is not fractionating. But if garnet fractionate, it basically buffers the biotype. Now, this is the modeled garnet profile, core to rim profile, which we see is a low almandine core and high almandine rim, which again goes into high almandine mantle, which goes into low almandine rim. Now, if we consider that garnet was the complete garnet was part of the system, we'll be estimating this PT condition. But the actual case will be that. So we are basically underestimating our PT condition by almost 4 kilobars and 200 degrees Celsius. Now coming to the normal or stable geothermal. In this case, what we see is garnets are growing in two phases. First is subsolidus growth, and the second is suprasolidus growth. But in this case, as we can also see, without garnet fractionation, biotite goes out, which will have implication. We'll discuss further in the presentation. Now we have similar garnet profile. In this case, what is happening is we are getting almost the same pressure, but we are getting underestimating our PT condition by almost 200 degrees Celsius again. Now coming to the orogenic path. Here same thing is happening. We have two growths of garnet. One is subsolidus, one is suprasolidus. But the interesting thing is where garnet fractionation happens, OPX becomes stable at the very highest rate, but not in the case of where garnet does not fractionate. This is little toned down, but the same pattern is there in garnet profile. Now in the peak PT estimation, what is happening is now we have a confusion. This is our true path PT condition, but we are getting two different intersections. One is with garnet with OPX, one is garnet with sillimanite. If we choose, in this scenario, we know this is much nearer to the peak. But if natural sample happens, we have a natural sample, we do not understand or we do not know what the peak should be. In that case, it becomes erroneous. So if we are at true peak condition with true bulk composition, then these three should intersect at one point. One intersection should be there topologically. Now, so with this background, we'll move to geology, the actual sample, which is garnet sillimanite OPX gneiss from San Mata complex, which is in northwest India, northwest Indian Peninsular Shield, almost here. And we picked up a sample from this Hempura village in the Bhim district of Rajasthan. So this is the sample, whole thin section overview of the sample. As we can see, we have two different sub-portions of this lithology. The center is the leucosome, dominated by quartz feldspar vein, which is passing through, cutting across the sample. We have a garnet stuck within, and then we have garnet biotite-rich portion, which almost is relatively very less modal proportion of quartz is there in this portion. And if we zoom in a bit here, what we are seeing is garnet is being decomposed into OPX and sillimanite. So that gives an idea that garnet is not in equilibrium with the OPX and sillimanite or orthopyroxene and sillimanite, and should not be considered for peak PT condition. So we have two mineral paragenesis. Oh, sorry. So, okay, we performed CT scan of the sample to understand what was the distribution of sample. We got, it was 17 volume%, and there were two domains. Larger garnets are basically more isolated and only occur within the leucosomes, while smaller numerous garnets, which are retrogressed, are within the rest type. So from the garnet rim to rim profile, we are seeing there are two stages of garnet growth with almost 50% of core and 50% of rim. Okay, so if we use purely, we do not consider garnet as part of the peak, we get a temperature of almost 950 degrees Celsius and 8 kilobars. But if we do consider garnet, we come down to very low temperatures, almost 110 degrees low and 2 kilobars low pressure, which as I have shown earlier, garnet is not in equilibrium. So what are the effects of this garnet fractionation? Now we are using melt integrated forward modeling on the melt integrated of this lithology. So what it shows is almost 50% of the melt, cumulative melt, is formed at low temperature by muscovite melting. Then we have slower, smaller amounts of growth in biotite melting. Rest, almost everything is same except A by CNK ratio or per aluminous nature of the anatectic melt increases if garnet is fractionating. Now coming to the 25C, what we see is same thing, per aluminous nature of the anatectic melt increases. For 40C, what we are seeing is slight increase in maficity, almost of 12%, in addition to the A by CNK ratio. Now, the trace element variation, what is happening? The dashed line shows the portion where garnet fractionates, and the red line shows where garnet is not fractionating. Where garnet does not fractionate above 850 degree, we see enrichment. So let me back up. We are using a CL by C0 ratio. CL is the trace element composition of the melt, and C0 is the trace element content of the protolith. So if it goes above 1, we have enrichment in the melt. If it goes below 1, we have a depletion in melt. So in all the scenarios, we see a CL by C0 of greater than 1 above 850 degrees Celsius, both in case of Rayleigh and batch melting. But Yttrium shows opposite trend. It goes below 1 when we go above 850. Same scenario is here again. The only thing is Rayleigh is giving us opposite answer compared to batch, which shows it might be a numerical artifact, and this should not be taken into consideration. Now coming into the 40C kilometer orogenic path, we have same thing as we had in the subduction zone path. We have a enrichment in melt above 850 degrees Celsius. So what are the key takeaways? Garnet cores should be removed during peak estimation, otherwise we will be underestimating the peak pressure temperature conditions. Garnet and melt fractionation along orogenic path will induce or OPX plus sillimanite symplectites or growth. Garnet fractionation will promote per aluminous and high mafic melts, and then garnet fractionation will discourage LCT type mineralization.
Thank you, thank you. Yeah, just in time, you have finished. So, any questions?
So what is the advancement of your work that can be taken as what Shah et al. In 2008 has published to understand the metamorphic evolution of the
So, sir, basically what we are trying to say is, if we know the metamorphic evolution of a terrain and we know the kind of lithologies, metasedimentary or metapelites are there in the rocks, we can basically check the potentiality for LCT or NYF type mineralization in the terrain. Yes, basically because we were waiting for the whole rock data and we did not have it, so I am using CL by C0 as a proxy for enrichment or depletion.
I am also not convinced about your assumption that garnet core composition is to be removed for the epithelial model.
So,
because your garnet is composition is not composition is the core part.
So the almandine is almost 76% in concentration, but the rims are in the core, almandine is 76%, in the rims they are almost 80%. So we have
Okay, thank you, thank you. We will have
so that is why I used the theoretical modeling that I did with all right, sir.
When you showed that photograph of your section, so you considered the white portion as wet fraction or?
So white portion.
Because of Hippocrates part, you considered that a wet fraction or?
Glucosome.
Glucosome. So entire part is glucosome. Why? I mean, it can happen. Solid state differentiation cannot be possible.
Solid
Do you
state.
find any textural evidence of melt-induced crystallization due to that?
Yes, sir. So the whole area is actually covered by charnocites, magmatites. Hmm. It is crystallized melt, so we can. So we have textural crystal. So the thin section that I showed to you initially, that was section cut from the after we recreated it, a 3D image of it. So we can find the largest garnet that we can cut through to get the most amount of history out of it.
Okay, so we'll continue this, during the tea time. So moving forward to the last presentation in the session by Dr. Mohammad Raza from ISER Kolkata. So Dr. Raza will be talking on the cryogeny metamorphism from Madurai block.
Good afternoon to everyone. I will be talking about the cryogenic metamorphism from Madurai block of southern granulite terrain, India, a petrochronological appraisal. To start with the introduction, this is the geological map of Indian shield showing the craton and mobile beta of the India. The southern part of the Indian shield lies south of the Dharwar craton, is called the granulite terrain of southern India. And this is the geological map of granulite terrain of southern India. The granulite terrain of southern India lying south of the Dharwar craton till the southern tip of the southern peninsula of the India. The granulite terrain of southern India has rock record from the Paleoarchean to Cambrian. The entire terrain is divided into several crustal blocks with intervening shear or suture zone, that is the Mawar Bhavani shear zone, Palghat Kaveri shear zone, and the Achan-Kovil shear zone. And the granulite terrain of southern India is further divided into NGT and the SGT. The south of the Dharwar craton till the Mawar Bhavani shear zone is called the NGT, where the south of the Mawar Bhavani shear zone is called the SGT. So the SGT further divided into three parts: the Nilgiri Namakkal block, Madurai block, and the Trivandrum block, separated by the Palghat Kaveri shear zone and the Achan-Kovil shear zone. So the Madurai block is the largest crustal unit within the SGT and preserves an extensive history of crustal evolution spanning from the Neoarchean to the Cambrian. The multi-phase metamorphic event reported from the Madurai block is 2.5, 1.0, 0.8, 0.6, and 0.5 GA are reported from the Madurai block. So these are the major magmatic and metamorphic event reported from the granulite terrain of southern India. We will be focused mainly on the Madurai block. The major magmatic event reported from the Madurai block at 2.5 GA, 1.8 to 1.6 GA, 1 GA, 0.8 GA, and 0.6 GA. Whereas the metamorphic event reported from this block is 2.5 GA, 1 GA, 0.8 GA, and 0.6 to 0.5 GA. And here we are mainly focused on the 0.8 GA magmatism and metamorphism. So all the data reported from the magmatic and metamorphic event related to about 800 are plotted here. The blue color showing the magmatic event, whereas the gray color showing the metamorphic event reported from this Madurai block. So these are some metamorphic event, about 800 reported from the Madurai block by Brand et al. 2014. But you can see here all the 800 metamorphic event reported from the meta-igneous rocks using the zircon overgrowth. But there is no cryogenian metamorphism reported from the metapelite from this block. And there is no characterization of this 800 metamorphism. So the question is the characteristic of the 800 metamorphism from the Madurai block and its correlation with the magmatic events. So to answer this question, we are moving to the study area and its field relation. This is the Dindigul is my field area where the most of the rock is the Charnockites and the hornblende biotite gneiss considered as the basement. Overlying the basement is the supracrustal, including the metaphylites, quartzite, and the calc-silicate rock. These are some field photograph of metaphylitic rock from the Dindigul area, where the pegmatite cross-cutting these metaphylites, and these are the larger view of this metaphylitic rock, where you can see the garnet overlapping by the sillimanite and the biotite rich faces. So now moving on petrography and mineral chemistry of this metaphylitic rock. These are the photomicrograph of this metaphylitic rock. We have two types of the garnet present in this metaphylitic rock, the garnet 1 and the garnet 2. The garnet 1 has the inclusion of biotite and quartz, whereas the garnet 2 has the inclusion of small biotite, sillimanite, and quartz. And these two garnet are chemically different based on their XAMG value. The garnet 1 XAMG value is 0.2, whereas the garnet 2 XAMG value is 0.32. And similarly, as per the biotite XMG value is also different. The biotite 1% as an inclusion in garnet 1 has XMG value 0.61, whereas the garnet biotite 2% as an inclusion within the garnet 2 has XMG value of 7.1. And these are biotites 3, that is the matrix biotites, has very lower XMG value, about 0.54. And these are some biotite and the sillimanite rich zone. You can see most of this, some larger grain of this sillimanite sitting over the biotite zone, and these are the highly sheared rock. And X-alvite value of this plagioclase is 0.68. And similarly, in the second sample of metaphilites, again we found two types of the garnet 1 and garnet 2. The garnet 1 has an inclusion of biotite and the quartz, and whereas the garnet 2 has an inclusion of biotite, quartz, and sillimanite. And the garnet 1 XMG value 0.3, whereas the garnet 2 XMG value of 0.39. And the biotite inclusion has XMG value is 0.72, whereas the biotite 3 XMG value of 0.74. Here there are some larger grain of sillimanite are present in this rock. To see further the variation of composition biotite and the garnet, I have plotted the FM diagram and the XMG value of garnet and the X-granular value of this garnet. Here we clearly see the garnet, the variation composition of the garnet 1 showing the red color, whereas the green color showing the garnet 2 value, and these value are cyan color is the biotite 2, this gray color showing the 1, and these are showing biotite 3. And the XMG value of garnet 1 is the lower, whereas the XMG value of garnet 2 is higher. So now coming to their age, we did the texturally controlled monazite geochronology. We have found two types of textural monazite. One is present as an inclusion within the garnet, whereas the second type monazite present in the matrix. So we found the age population of this monazite about 800. Only except one point, it has about 563 million years. We infer these ages are overgrowth during the retrograde metamorphism because these monazite grain at the boundary of the biotite. So when we plotted the XHRE versus XLRE and the contrast normalized RE pattern, here we can see the inclusion core of monazite and the sum of the matrix core have higher XHRE value, whereas the higher in the RE pattern diagram, the higher HRE and the Y value, which indicate these monazite formed during the garnet growth in the prograde metamorphism. And when these ages plot in the probability density plot yield an age of 804 million years. And another sample, we again found two types of monazite. One is a inclusion, whereas the second one present in the matrix, where here again plotted the XHRE versus chondrite normalized RE pattern diagram, but here we cannot see any major changes of XHRE and XHRE value, which indicate these two types of monazite form at the same time of events. And when the age plotted in these monazite give an age of 40 million year. And again, when we move for another sample, here you can see the last two samples, 34 and 52, has plotted here towards the east side of the Dindigul. When we are moving towards the west of the Dindigul, towards along the KKPT's SZ zone, we get disappearing of the 800 ages and found the 600 and 500 million year ages of monazite, because all the ultra high temperature metamorphism reported from along this KKPT SZ zone. So in this sample, we again found two types of the monazite. One is as an inclusion and second one in the matrix. When here you can see the X-ray element map of thorium and the yttrium. The low thorium core overgrowth by the discontinuous high thorium core, and again a very thin low thorium core. And in the Y, the high thorium Y and the low thorium rim. So when plotted in the XHRE value, we can see there are two types of the core. One is the higher XHRE value and another is the lower XHRE value. So this indicates there are three growth of these monazite. First is a higher low thorium core, and again higher thorium core, and again low thorium cores. When these ages plotted, they give the polymodal age. One is the S22 and the second one is the 606. Okay. Yeah. So we conclude this. Conclude this metamorphism of about 800 by using this monazite. So the Madurai block preserve evidences of the extensive granitoid magmatism of about 800 million years. And this magmatism is accompanied by coeval anorthosite, alkaline, and the mafic magmatism. And here we plotted all the magmatic and the metamorphic event about 800 in the map. And the vestigial evidences of 800 MA thermal event is primarily recorded in this meta-igneous rock. And this study presents the first evidence of dominant 800 MA metamorphism in the metapelite, enabling the characterization of this metamorphism. And this is likely indicate the occurrences of a pervasive 800 MA metamorphic event whose evidences has largely been obliterated by more intense Ediacaran Cambrian metamorphism. When these events are correlated with the global tectonic during the Rhodonia supercontinent, the Madagascar, SGT, and the Renner complex are together. So the Rhodonia supercontinent assembled about 1300 to 900 and broke apart during the Cryogenian 830 to 650 million years ago. And during the disintegration of the Rhodonia, the wide spread of continental rifting between 825 and 740 million years. And the Indian continent, including SGT, Madagascar, and Antarctica, experienced the magmatic and metamorphic event related to the Rhodonia breakup. So we infer the 800 MA magmatism has a special link to the heat source for these metamorphic events. I acknowledge my supervisor, Dr. Tapobrata Sarkar, and also thankful HOD Department of Earth Sciences and ISR Kolkata for providing me the research facility and the Institute Postdoctoral Fellowship. And I am deeply grateful to Professor Purak Sengupta for introducing me to the granulite terrain of the India and engaging in insightful discussion during the fieldwork. And also acknowledge Dr. Mahmooda Talukdar for her support during the fieldwork, and acknowledge analytical facility provided by the NCESS. And I thank all the members of Metric Lab for the fruitful discussion with special appreciation Mr. Ashish Kumar Tiwari. Thank you.
Thank you, Dr. Raza. So, any more questions?
So
So you have shown two generations of garnet in metapelite,
Yes.
garnet 1 and garnet 2.
Yes.
What is the basis of this classification? And next question, these two generations of garnet formed continuously or there is a break in metamorphism?
Sir, I think there is a break in metamorphism. We found their XMG value is the garnet 1 is lower and the XMG value of garnet 2 is the higher. And the inclusion of biotite.
It is in the same thin section or
in the same thin section, sir. Sir, and the inclusion of biotite percent in both the garnet has the different value of XMG.
But it can also form in compositionally banded rocks where different layers may have different XMG values. Some garnet with higher XMG have formed in more magnesian domain, whereas relatively ferro-1 garnet has formed in relatively ferro-1 biotite bearing domain. Is it possible?
Yes, sir, but that's why we have very limited data still, and we are trying to get more data to conclude.
So what is the timing of formation of these two generations of garnet, 860 or
No.
at different times?
About the first generation is about 800, sir.
And second generation?
Second generation most probably later, but it's all the 800 monazite found in the garnet 1 gen as the inclusion monazite present in the garnet 1.
Okay, thank you.
Thank you, sir. Any other questions?
In fact, it's a nice presentation. Okay. I don't have a question, actually. I have a suggestion for you.
Okay.
So you were relying on chemical dates from monazites, which is best, I would say. But there is a problem when you rely on chemical dates, that especially on monazites or any kind of accessories, that is the assessment of discordance. So chemical dates basically rely on a single age, which cannot assess the amount of discordance. So in case of your monazites, you find all these like 800, 850, very concrete weighted mean ages, fine, but they not be the real ages, they may be discordant. Why I'm saying is that your ages are slightly biased to the upper side from our experience, what we did here in SGT, on SGT. Your first set of ages on 815, your second set is ages on 600, around 610, 620. That's your two main clusters, right?
Yeah.
But if you look at the igneous emplacements of the first cluster, you say that it's all related to the Rodinia rifting, right?
Yeah.
That's basically, if you look at the rocks on the SGT, 80% of the Rodinia rifting rocks align at 750 to 780. So your ages are slightly over the metamorphism. Why I'm saying is that we have dated more than thousands of monazites from SGT using laser ablation ICP-MS. So what we could find is that the 800 region, the 810, 820 region, these regions have a very good monazite cluster, but they are all discordant. But you have a very prominent cluster of concordant monazites at 750. So what I intend to say is that your ages may be 780 or 770 or 760, but you couldn't recognize that based on due to the problem with the discordance. So when you do that, you should be very clear that whether it is 800 or 750 while assessing the discordance. But the rest of the things is fine, and if you can make like that, you could clearly relate to the Tonian magmatism with the metamorphism, because the Tonian magmatism basically brackets between 750 and 780 prominently. You have some 800, but 750 to 780. So assess the discordance and you could get a good answer for that.
From the real age. This is, if you see the dating technique of monazite, this is the thorium, uranium, total lead. So if you say discordant, so it's lead loss, if you say. Okay, so you can be lead loss. So what kind of discordance? So over discordance means uranium, lead, thorium loss? Okay. Okay.
Thank you. Now we'll wind it up. Appreciation to Dr. Raza for the very lively talk and also for the lively discussion. So over to Sneha now.
So now tea is arranged in outside, and next session again will start from 4 p.m. And 1 minute, sir. And I will request our director to hand over the memento to Shantanu Bhaumi and Dr. J.K. Thompson. So now we are going to start our 10th session that will be chaired by Dr. Lopamudra Shaha and Professor Rajiv Kaur. So please take the charge.
This session we have 4 lectures. The first one, Professor Rajesh, he is not here. So we start with Pritam, Dr. Pritam Nasipuri, and please, Pritam, and yes, your you because Professor Rajesh is not here. Actually, he will talk on geochemistry, PT pseudosection, and monazite geochronology of metasedimentary rocks, PG Valley. Okay, Pritam. And he will have time of 15 minutes. After 12 minutes, we will.
That's on. That's it working. Okay. So, good afternoon to all. And I am Pritam Nasipuri, going to present the work done by one of my PhD, one of my master student. This is on the geochemistry, PT pseudosection and monazite geochronology of metasedimentary rocks from the Pranita Godavari Basin, South India. So I think from the high temperature metamorphism, granulite magmatic phases, now I am giving you a flavor of low temperature metamorphism and how low temperature metamorphism can be useful for some commercial based research that I am going to discuss, and I seek a suggestion from all of you in that. So I presented organized my outline presentation with the introduction of the PG basin and its geological significance, although it has some redundant information. The lithotomic unit, this is a newly described unit, not described before from this area. Then part of the geochemistry which has been published. Then thermometry and PT pseudosection. Monazite geochronology, again we will discuss in some different perspective. And finally, I will seek suggestion from some possible significance of the work that we are going here. So we all know that this is a well-known geological map of India where the Bundelkhand Craton and the Aravalli Craton form the North Indian Cratonic block, and the South Indian block is constituted by Dharwa Craton, Basta Craton and Singhbhum Craton, and all these are sandwiched between the Central Indian tectonic zone. And a lot of research has been done on the amalgamation of the North Indian Cratonic block and the South Indian Cratonic block, when these blocks combine to form a supercontinent. But very less research or a very less information is available from the Pranita Godavari Valley Basin. I will come to the next slide why this is important. And recently, except some research on the Mahanadi Rift, some literature is basically unavailable from these two rift basins. So this is a geological map taken from Henderson et al. And Saha et al. 2015 and others, which shows that this is basically a rift basin situated between two Archean cratons. One is the Dharwa Craton, this is and the granulite belts, and this is the Basta Craton, and this is the another granulite belts, Bhopalpatnam granulite belts. There are a lot of debates whether these two cratons were together or not, and if it is together, when these two cratons got separated, and what supercontinent it represents, and at what time the separation did occur, and what time the valley did form, and how the valley did again amalgamated to form the new supercontinents. In a sedimentological perspective, this is the stratigraphical table taken from Henderson et al. This is our DY, its source of the DY. And there are a lot of groups. Most important is that Pakal supergroup, which goes to Penganga supergroup, Silubhai group, Albaka sandstone, and finally we have the Gondwana rocks. Now if we see, there are some ages based on the sedimentology. If we see there was some limestone which ages 1686 plus minus 6 MA by lead method. Again from conglomerate detrital zircon which is 1622 plus minus 6 MA from detrital zircon. So in this, from the sedimentological perspective, this ages has some meaning on the basin opening, but today I am going to explain why this significance is in terms of metamorphic petrology and tectonics. So we collected the samples from a newly cut road from the Bolapalli formation, which is just occur above the angular unconformity below the just above the peninsular gneiss, which is about 2,500 million years of age. This is the study area. This is a newly cut area. This is called the Kinasarai River, and this was published by one of my PhD students in 2024 in Geosystems and Geoenvironment. Here, in the dam site area, the sedimentary rocks occur, metasedimentary rocks occur like this, extremely highly foliated rocks. And the most important is that the strike of the foliation is parallel to the northwest southeast strike of the Godavari Rift Valley. Now, in most of the cases, sedimentary rocks are flattened and outcrop is of granite. So these two are the situations where we got these rocks. And if we go further, the metasedimentary units, although this picture is not very clear, you can see the metasedimentary units, and there was an angular unconformity before which the Gondwana sediments occur. So this is the roughly stratigraphy of the study area, and we studied these rocks in terms of geochemistry, mineral chemistry, and geochronology to be used in a different in a commercialized So first, if we come to the geochemistry, this is the routine work. This is the all geochemical part, and we see that the rocks are Al2O3, which is the most immobile element, has a positive correlation with Na2O, K2O, and possibly something nearly flat correlation with L2 with SiO2, which indicates that from this fine-grained rock that possibly mica, biotite, and aluminosilicate control the major element abundance of the studied sample. Trace element we cannot say much more, but from the normalized diagram we can see that the rocks are metasediment exhibit low strontium, phosphorus and titanium values, which we suggest to indicate that the parental rocks of these rocks are derived from an active or a subduction zone setting where the phosphorus is incorporated into garnet, and low titanium is an indicator of subduction setting, and low strontium again an indicator of feldspar retention mechanism. And this is the flat pattern mostly of the some past normalized rare earth element pattern, which is mostly common towards the other studied sample. Now we determine the temperature, because this is a very fine grained and the composition of mica varies widely. We use different techniques to find out. First, we use the technique defined by Henry et al., which gives an empirical temperature of 651 plus minus 12 degrees centigrade based on titanium titanium exsolution in biotite. Now, if we use the modified formulation by Hu and others and use the titanium as well as empty number, again we got a nearly similar temperature 650 degrees centigrade. Now, to substantiate this, again we use the PT pseudo section. I think from the beginning lot of presentation is on the PT pseudo section, but what I will say that our assemblage is stable at a very low temperature between 0.4 GPa and 600 to 625 degrees centigrade, which is roughly corresponds to the empirical formulation, and say 600 to 625 degrees centigrade around 0.4 GPa. So this is basically this is an essentially lower upper crustal phenomenon. Now for the geochemical classification, this is again some routine work what we did to find out that what are these rocks, and we found out these are the mostly are the metapelites from the weathering, and these rocks are classified as shell. So we can say that these are the rocks which formed due to weathering of some parental rocks, and parental rocks experienced zircon recycling as formed from the thorium by scandium by zircon by SC ratio, and we from the index of chemical compositional variation we can say that this weathering is of moderate weathering, and the weathering occurs in the arid conditions. For the source rock, the chromium nickel concentration gives us these are the Neoarchean, these are the Neoarchean granites which were developed in the active continental setting, as we found in the log K2O by Na2O and thorium strontium by 10 into zircon ratios. So we can say that these rocks, although these are formed in a rift basin, show an active margin signature and they are formed during sediment recycling and moderate weathering. Now, what is the age of these rocks? There was some age given by the sedimentologist. Now, to find out the metamorphic age, we found monazites. This was done in GSI Kolkata. And you can see monazites are small and is associated with biotite, quartz, muscovite, and somewhat sillimanite. Now, if you see these grains, all this is taken from a paper and the quality is not very good. The interior of the grain shows a low thorium core and a high thorium rim, which is traditionally told as non-normal monazite. Now, there is a big doubt that whether monazite is an igneous mineral, a metamorphic mineral, or a detrital mineral. So, we compared some available data. Monazite nucleates after allanite, which is a sorosilicate, at temperature above 425 degrees centigrade. This is experimentally proven. And next is the dissolution of the small grains. To grow larger grains occur between 500 to 600 degrees centigrade, and the fluid assisted growth due to monazite breakdown occurs at 650 degrees centigrade, possibly due to mica breakdown and liberation of sodium ions. And the most important other point is that hydrothermal monazite, which was widely measured as with thorium less than 1%, whereas igneous and metamorphic monazites have thorium greater than 3 to 4 weight percentage. So based on the size, more than nearly 100 micron, the PT conditions nearly 650 degrees centigrade, which cause that they satisfy the second and the third condition, and the fourth condition that igneous and metamorphic monazites are have more than 3 to 8% of thorium. We concluded that these are the metamorphic monazites, and these monazites represents metamorphic age of the sample. Now, to date the things, we have done some UPB thorium chemical dating, although there are a lot of controversy, but still I say that for monazite, this is the most monazite, this radiogenic lead is very less in the structure, and this age is the most widely used age to identify the metamorphic domains. So we got through ages 130, and 1122 plus minus 41 MA. And the error bar is always 1 sigma. Now we do the KDE plot of the same to find out, we do the KDE plot of the same to find out the two peaks. The first peak is widely correlated with rifting between Eastern Dharwar and the Bosta Craton. Lot of articles are there. So we correlate this. This is the disintegration of the Columbia supercontinent. And finally, this one, the Yonga peak is the amalgamation of the Bosta and the Eastern Dharwar Craton, we can say from the available literature. So if we compare these two, this indicates a meso-neoproterozoic transition from Nuna to Rodinia, and rift basins give us the answer for the transition of one supercontinent to the another. Also, it shows the idea of how a transformation of a passive margin, which was initially a rifting, can form to an active margin. Now, this monazite bearing, as morning SDG sir pointed out, research can have two aspects. One is the applied and one is the knowledge-based aspect. So here we can show that easily that RED bearing minerals can be formed from the allanite, which is a very, very common clay mineral, and mica breakdown. And rare earth minerals are now in the India's national mission. So can we develop a mechanism or a furnace mechanism to heat the clay minerals to form the monazite yield, and would see whether we can commercially viabilize it or not. And for this I seek your suggestion whether this can be utilized or not. So to questions what I want to seek answer from you, that we know that there is a mechanism, that Prakasam alkali complex were entered between the study area, which is below nearly 400 kilometers away from the study area, and that model is still being used to describe the disintegration between the Eastern Dharwar and Bosta Craton. So is it so? Or what are the tectonic events that causes the polarity and reversal of the amalgamation? There is one paper, but there is no definite answer, although there was a lot of good and well-cited work by Professor Dasgupta, Professor Bose, and the others. So with this, I want to acknowledge my PhD student with whom this work was not possible. And thanks for your attention, and I seek your suggestion if we can do this work. Yes, sir.
Thank you.
I was just wondering about the stratigraphy. I mean, I have no questions about your monazite dates and PT and all this, but what is the stratigraphic position?
Yeah, stratigraphic.
I mean, this is a very peculiar sample because you are showing above this is Malampalli and Muluk and Sumanpalli, isn't it?
I am showing you the stratigraphy, sir. Yeah, the stratigraphy is this one.
The Ramagundam sandstone is unmetamorphosed.
So that is the point. That is the thing that this is a very newly cut road cut. We got this.
Because Pandikunda limestone is unmetamorphosed, which has glauconite, Ramagundam sandstone has ferriculite, and then you have the Pakal and the Adilabad Penganga group, you have again glauconite.
Yeah, but once we collected the samples from just the Bolapalli formation and Peninsulanese contact.
That's true. But what I am thinking that this temperature, what you got, the temperature is right. But the question is whether this is, you can call it a Proterozoic thing, or this is a part of the Archean. This is, I have not, because Bolapalli is unmetamorphosed.
Yes, because the.
So how come 650?
But once I get the samples, then we just analyze it. And
that part is okay. But I mean, I'm asking for the ancestry
because I do not have the ancestry.
This part is unmetamorphosed. You have here glauconite all through. We have mapped this area. No? This is
the
Ostri Chaudhry's area, mapping area.
That is a question because that is one of my student, and this we collected from just the Bolapalli.
Yeah, this is new. This is new, no doubt about it. This is a very new information, but because this part is unmetamorphosed, and suddenly you get 650 here. Strange.
I will show you the samples.
Thank you. Pritam, you just think what Professor Dasgupta told. Any other questions? Anybody? Okay. Thank you, Pritam. Thank you thank you very much. Our next speaker, Dr. Shreya Karmakar from GSU ISI Kolkata, and she will speak on evidence for titanium mobility during regional metamorphism from Markohar granulite belt, central India. Okay, Shreya.
Very good morning, very good evening to all of you. So, as I was introduced very generously, so I'll be talking today about evidence of TI mobility during regional metamorphism. With a case study from the Makrohar granulite belt in central India. So I won't be going into much detail about the geological history or the regional geology of the area. So just to show you my study area. So here is the CGGC actually. So this is the northwestern extension of the terrain. This is the Mahakoshal belt, the Vindhyan sediments. So the Makrohar granulite belt is this part, which is the northeastern sort of the end of the central Indian tectonic zone. And the area is seen from the map here. The country rock is mainly a suit of porphyritic granite gneiss. And it contains these calcilicate, not calcilicate, sorry, the dolomitic marbles occurring as meter to kilometer scale rafts which are folded. And the other dominant rock type here is these in grey color, the gabbros and troctolites in this area. So the studied marbles, they are banded in nature. The bands are continuous and parallel in the scale of single outcrops, few centimeter scale thick, and their color varies from grey to brown. The bands are also folded and deformed later. So So if I look at the mineralogy of the rocks, the host rock, these white colored marble part, they are composed of calcite, rhodamite and phosphorite. And the bands, when I look at them, the grey part of the bands, they are spinel rich, and so the grey part of the bands is spinel rich, and these brownish layers, they are almost pure clinohumite rich bands. So the mineralogy is of the bands, the brown bands are clinohumite calcite, whereas the grey bands, they are comprised of clinohumite calcite and spinel. Now the gradation of these bands with the host rocks is quite sharp. The abundance of appearance of clinohumite suddenly stops and it's all calcite dolomite. But within the grey and brown bands, the variation between spinel content and clinohumite content is gradational. So this beautiful golden colored, yellow colored mineral is clinohumite. Okay. So now before I move on, so clinohumite, what is it? So clinohumite basically is a hydrous olivine. So this is the olivine part, and there's another bivalent site, and it contains OH. So this is the MgOH N member, and it contains some amount of titanium fluorine. So all the reported occurrences of clinohumite, the pure N member is not yet been reported. It is all the titanium fluorine bearing occurrences that have been reported. Normally, those which have been reported from skarns, the occurrences have been reported. They are relatively more fluorine rich, whereas the few handful of occurrences reported from ultra high pressure metamorphosed mafic, ultramafic rocks, they are relatively more titanium rich and fluorine poor. So based on the textures that we observed, we deduced two textural reactions. So one is that the clinohumite calcite bearing bands, clinohumite formed from dolomite and phosphorite. None of these two minerals contain either titanium or fluorine, and they are anhydrous minerals. So this necessitates that this reaction formed in an open system through fluid infiltration. Now in the spinel rich bands, we deduced that the precursor of spinel was most likely magnesium chloride, because commonly if we are thinking about the sedimentary protoliths, limestone clay alterations have been commonly reported. So the clay rich bands probably during metamorphism formed magnesium chloride, which later on formed spinel. So we modeled both these reactions using the C-space program, and the relative volume proportions of the product phases that we found from C-space also matched the volume proportion that seen texturally in the rocks. Now moving on to the thermodynamic modeling. So we are familiar with these two diagrams of metamorphism of marbles. Here we see that clinohumite is not present in anywhere in this field. But from the study of Rice 1980, it is shown that clinohumite can form under very hydrous conditions. So we recalculated these TX diagrams after constraining the activity of the phases that were present in our rocks. So what does it mean to constrain the activity of a phase? So here the phases that are present are all pure phases in the C-V system. So now let's say we have a reaction in the C-V system which is of the form A plus B equal to C plus C. So this is the original reaction. Now we add another component into the system through external fluids maybe, in such a way that the additional component Z enters only one of these four phases. So the effect is that the activity of that particular phase is reduced and its stability is enhanced. So if Z preferentially enters only C, as I've exemplified here, so the reaction will shift in such a way that the stability of C plus D is enhanced. So in that case, we see the reaction texture A plus B forming C plus D happening, but that may not necessarily be due to a change in pressure temperature, okay? Because the reaction has now shifted in a PT space. So with this idea in mind, so in this case, our Z is titanium and fluorine in this pure MgOH clinohumite. So with this idea in mind, we calculated the TX diagrams for the clinohumite bearing marbles, where the activity of forsterite, spinel and clinohumite is what we have observed in the studies rocks. So just to simplify this diagram, these are the expected fields that we see here. So this is basically the very low XCO2 end of this axis, so 0 to 0.03 only. So we have tremolite chloride, diopside chloride, forsterite chloride, forsterite spinel, and here we see a field of, in yellow color, clinohumite and spinel appearing at the high temperatures and very almost pure H2O fluids. So because of this limited stability, this pure clinohumite is metastable in crustal conditions. So then, so here in this diagram only the activity of forsterite and spinel are what we have observed in our rocks. So now we have recalculated the diagrams with lower activities of clinohumite. So the effect that we get is this clinohumite forming reaction, it shifts to more XCO2 rich compositions. So in a sense, so this was the brucite forming reaction. So commonly in marbles during hydration, we see the ferromagnesian minerals getting altered to form minerals like brucite, serpentine, antigerite, those kind of minerals, not clinohumite. But because of the lowering of the activity of clinohumite, its formation is favored over the formation of other minerals like brucite, serpentine, antigerite. Now this answers our question that indeed because of the infiltration of aqueous titanium fluorine bearing fluids, clinohumite was able to form in these dolomitic marbles. But this still leaves us with the question about the source of Ti. Now this is important because classically we consider elements like Ti and aluminium as immobile. The Ti is also a high field strength element. So in many mass balance studies, it is considered as a reference frame, the immobility of these elements. So we cannot just say Ti was mobile without offering a possible source of Ti. So experimental studies have indicated that in the presence of halogen bearing aqueous fluids, particularly fluorine bearing aqueous fluids, titanium can be mobile. So do we have any source of such rocks in our study area? So going back to our map, we said that the other abundant rock in our area was these gabbros and troctolites. So these occur as dikes in the country rock and also as such plutons. So the mineralogy of the rocks is that they contain variable proportion of pyroxenes and olivines and plagioclase, and they also contain in some of the unaltered samples that we found, they also contained abundant apatite and ilmenite. Now these rocks have been variably altered. So in the less altered samples, we found a beautiful array of multi-layered corona texture, which is commonly found in such gabbronorite dikes. In the more altered samples, all the ferromagnesian phases have been replaced by amphibole. The igneous texture is still preserved in some of the localities, but more commonly we find such recrystallized amphibole plagioclase rocks. So in these samples, there are only few relics of ilmenite present. So apatite ilmenite has completely been replaced in these samples. So if we take a look at the composition of the minerals, apatite has a significant amount of fluorine, but the altered minerals, amphibole, it does not contain any significant weight amount of fluorine or TiO2. So it was mostly removed out of the system. So keeping in mind the close proximity of the rocks, so there are other marble areas. So these in these marble bands and some in the south, in those we find only serpentine and brucite and antigerite. Only in the localities that are close to the gabbronorites, we find that clinohumite has been formed, because the titanium and fluorine from the gabbronorites was able to mobilize the Ti. Now the idea behind this study was that even though it may not form the principal question of my research, the idea was that it is important to document such even maybe minor mineralogical occurrences, because it helps us to evolve our understanding of element mobility during it helps us to evolve our understanding of element mobility and recycling during crustal processes, particularly when we are talking about such immobile elements. So with that, I'd like to end my talk. Thank you.
One or two quick questions. Anybody?
Share that I was discussing with you,
Yes, sir.
the titanium mobility. If you see your hand specimen or field observation, can you go back to the field observation?
Can you go back to the presentation, please?
So you have a very nicely banded structure, and these bands alternate in the scale of observations
Few
here.
centimeters, yes.
Few centimeters here. So if you have titanium mobility, how it will produce this kind of alternate layers? So what will be the possible pathways of titanium mobility that will produce this banded structure?
So the banded structure, what we said was initially the protolith was a limestone clay alternated unit. Then during metamorphism, the clay-rich layers formed the chlorite-rich layers. So the schistose minerals provided additional pathways for the fluids, and the fluid flow was not pervasive. So only along the bands where the fluid encountered phosphorite, it replaced to form clinohumite. Elsewhere in the host rock, where the fluid could not reach the phosphorite was not altered. It remained as phosphorite. So it was neither altered to brucite nor to clinohumite. So this banding is roughly a pre-existing structure.
Okay.
Any other question?
Purely a fluid rock interaction.
Purely a fluid rock interaction.
Thank you.
Thank you.
Thank you, Shreya,
Thank you.
for the nice presentation. Now, for the rest of the tour, I hand it over to Rupa.
Thank you, sir. Now I'd like to call Dr. K.R. Adisheshan, who is going to present a talk on the title Neoarchean Transient Tectonics from Western Dharwar Craton, Insights from Shimoga Greenstone Belt.
Good evening, everyone. I am Dr. Adisheshan from National Institute of Advanced Studies. I am presenting my postdoctoral research, and this is yet to be published. So the introduction to my research area, this is the Neoarchean tectonic in the Western Dharwar Craton. It's a very much debated subject, and there are several models for the earlier, the older rocks like the Sargur and the associated TTG rocks. But now I am focusing only on the Neoarchean part. So the motivation to select this study area especially, because the older groups are already studied comparatively very well. This is the youngest sedimentary unit in the Dharwar stratigraphy. So this is one of the reasons I chose this particular area. There are few works already done in the Shimoga Greenstone belt, where it is basically done with the help of elemental data. And earlier work, the first work was done by Chadwick et al. During 1988 and 1991. So they did basically the field related aspects, and the Shimoga stratigraphy, they well established with the field data. And my interest to combine the field data along with the geochronological and geochemical data to tell about the Neoarchean tectonics. So this is what I am going to present, and this is the Dharwar geology of the Dharwar craton. So already I am not going much detail into this map because Dr. Ramohan sir and today by Dr. Aliba already all the things are explained. So I straight away go to the Shimoga. So generally this is the study area. It is generally mentioned the Shimoga Dharwar sedimentary basin because this is the youngest one found in the western block of the Dharwar craton, and this is covering the huge area. But now I have done my postdoctoral work from both Shimoga and Dharwar covering, but now I am presenting only from the Shimoga region. So this is the this map I cropped out from the Bocos portal from Geological Survey of India. So here we have the different many rock types. Actually, I simplified to show whatever the rocks I have collected and whatever the rocks I collected and used for the chemical analysis. So this white part is the basically the Bababdan Greenstone belt, but from here the Shimoga actually it starts, and there is a small tongue of the Shimoga Greenstone belts. It come down here. So here this pink are the polymate conglomerate, so which forms, and this is the first the tectonic units. From here onwards the Shimoga Greenstone belt starts actually. So and then the other tectonic units are the basement rocks, and then the arc sequence which have the mafic greenstone and followed by the felsic rocks, and along with some sediments also. So these are the three different tectonic units, and the polymate conglomerate, this is actually associated with the ultramafic rocks. Here in Shimoga region we have ultramafic rocks which are chemically, if we speak, it is the MgO content of these ultramafics are above 18%, and it is going up to 32%. If we compare with Sargur group, they are slightly younger. The Sargur group, which happen to have the MgO content up to 42%. So these are some of the field photographs. The first unit of the polymate conglomerate here. So here we have different type of clast, starting from gneissic clast and granitic clast, and these are some of the mafic clast here. In the field we could see also some of the very tiny BAF also, which could be come from the Babavdan, but I could not make the clear picture of it, so I did not show here. So this contains many different clasts, and this is the longer view of the polymate conglomerate mixing with the ultramafic. So here the ultramafics are highly altered due to this mixing, and this is another ultramafic genus chert, and then these are the argillites, and this photo is not very clear because due to the long shot, and here the small portion, this is the again the mafic rock. So here the mafic rock is also depleted here, and I am trying to figure out the timing of different tectonic units based on our study plus the data from the literature. So here we have collected the basement rocks from the Honali Dome, there are few outcrops, ground level outcrops are there near Tarikere. So we have dated here and the Honali Dome. So already the another work which was done recently and published by Ravindran et al. 2023, they have collected the basement rock along the Tarikere. So the maximum age and the minimum age for the basement rock what we got is 3,342 and few grains which are showing up to 3,400, and the minimum age for the basement it is 3,180 million year. So and the UPB zircon age from the polymite conglomerate, the clast we extracted from the polymite conglomerate which we have dated, and earlier it is dated by Maiba Metal during 2016. He has dated from the Naisi clast, so that has given the age of 3,200 million year with a few grains of 3,400 million year. So what we have collected, the two clasts which are granitic, so the one is giving 2,703 and another one is giving 2,626 million year. And the mafic units, mostly the mafic units are here. In the Medur, it is the mafic units are mostly concentrated, and along the, so here the Shantisagar is here, and along the Shantisagar there is another mafic unit. Here the mostly the sediments are located in the lower unit. In the stratigraphically, it is the Jandimati, Joldal, Medu and Ranebenur. So we consider the Ranebenur is still further north. So here Giri et al. During 2019 they have published a paper, and there they have done SM&D isochrone, whole rock isochrone from the mafic volcanics. So they have dated 2,638 million years, and the felsic volcanics which are earlier dated during 1996 by Natman et al. This is the Daginikate volcanics, felsic volcanic. This is 2,614. So I have done some SM&D isochrone isotope analysis from the ultramafics, but I could not get precise age due to it is highly altered and the isotopic systems are highly disturbed. So I did not present that data here, but I am just using that data for the arguments. And these are some of the geochemical plots where the comatiites, the ultramafics, they are comatiite in nature. It is having the MgO from 17.92 up to 32 from the Shimoga, and there are some comatitic basalts are there. So they are characterized by the MgO content between 16 to 12%. The less than that, we grouped into tholate, the tholeitic basalt, and some of these are the felsic volcanic from the Daginikate and surrounding area. And the basement rock, it is mostly the transmitic in nature. And these are the RAE of the rare earth element plots of the ultramafics. So here the ultramafics are, it is variable, means it is depleted, but their total RAE is around from 1.2 to up to 10 ppm. And here it shows nearly flat, but when I did the SM&D isotope analysis, they are highly disturbed here, and the corresponding multi-element diagram I have shown here. I have excluded the Lyle elements due to high zigzag nature. So here, though it is ultramafic, still it is showing the negative NBTA and less pronounced zirconium and hafnium anomaly with yttrium. And in the mafic also, in the mafic rocks also, it is the signature is the arc signature, but still the zirconium and hafnium here, we cannot expect here, but I can explain that these are derived from the shallow source, so it can take some amount of this zirconium and hafnium. And this is the RE of felsic volcanic and the basement TTG. So these two are sharing the similar geochemical patterns. These geochemical plots I am just using for my tectonic to support my tectonic model. This I have already explained with the RE plots, so I am going to the next one, the conclusion part. So our field observation from the field observation and combined elemental and isotopes, it is suggesting the transient tectonics, because the ultramafics here it is not plume related. If it is plume related, we supposed to have the strong negative zirconium and hafnium anomaly, which is not in this case. And so we are planning we are suggesting the rifting for this area, because the polyimide conglomerate that is giving the explanation for the rifting, and there all the clast of gneisses and granites it is falling and mixing in that area, and then the drifting and eventual subduction that form the continental arc, and collision of this arc with the Western Ghats mobile melt, Western Ghats belt, which actually generated 2.6 billion year granite. So with that, I conclude my presentation. Thank you.
Thank you. And any questions from the audience?
You said that you have rocks which are commotite and commoditic basalt and things like that.
Yes, yes.
And then you said that it has nothing to do with plume. Yeah?
Yes.
So how this rifting occurred and how such high magnesium rocks have come into being?
Yes, sir. This is, I think another kind of idea. This could be the failed plume. It is started, but because to melt such a high MgO rock, we need certainly a high temperature source. So that is possibly the plume. But if it is a plume, we still supposed to have the higher MgO here. In case of Sargur, we have such comatites here, but here we don't see the comatites with either spinifex or other kind of characteristic features in this particular area. If we compare with 3,350 million year old comatite from the Sargur and the younger Shimowa Greenstone, if we compare that one, here the MgO content is still less. So there could be a failed plume activity here, but still we don't see the field evidence to convincingly say that.
It's very difficult to understand, what is failed plume.
Any more questions?
I'm sorry, I missed the part where you were describing the field setting.
Sir.
But you sure it's volcanic?
Yes, sir.
How? I mean, what features do you see? Because you're not seeing any spinifex textures or anything like that.
Yes.
How can you be very sure that it's a volcanic rock that you're looking at, the ultimate?
Sir, in some places in the field we have seen the ultramafics where it is, we have photographed and collected samples. They have the tectonic contact with the the surrounding sediments or whatever the rock types, because we don't see any clear, we see the tectonic emplacement of this particular ultramafics, because these are not widespread. It is the patches of ultramafics around a certain place, not it is the continuous body over the field.
What I'm telling is, what if it is you're looking at a cumulate? I mean, it may not be a liquid at all. I mean, so I think what Talatsa was saying, I think is probably hinting at that. So if it was a cumulate, then maybe you never had a liquid of that composition. That's the only thing. I thought I missed it because the volcanic features, I can't remember seeing you showing anything like that. So I was just wondering if you're actually looking at an ultramafic cumulate and then interpreting it to be a liquid where there never was a liquid of that composition.
Maybe I will look into it, sir, again. But I just want to add one more point here. In the Sargur area, we have the cometiate. There we have separated the cumulate cometiates, which have the MgO content more than 38%. Right. Yes, sir.
Okay, thank you, Dr. Adisheshan, for such a nice presentation. Now I'd like to call Dr. Arnab Dasgupta for presenting a talk on metamorphic characterization of metabasites from Proterozoic Chandel formation and their implication in the tectonothermal evolutionary history of northern margin of North Chingbu mobile belt.
Am I audible? Good evening, everyone. Today I am going to present work that I am just started, and it's in the just in the nascent stage of metamorphic characterization of North Chingmu, some metabasites from North Chingmu mobile belt. First, coming to the just introduction of the North Chingmu mobile belt. As we all know, it's present on the northern part of the Archean Singhung Craton, and it's actually composed of some supracrustal rock, low-grade supracrustal rocks, and this is actually divided. The central part of the North Chingbu mobile belt consists the Dalma volcanic group, which actually separates it into northern domain and a southern domain. So my point of interest is in the northern domain. This is another detailed lithological map developed from modified from Banerjee et al. 2024. Here we can see actually in the northern part of this North Chingbu mobile belt, this actually consists of the low-grade supracrustal, mainly of phyllite, micaceous quartzite, mica schist, and carbonaceous phyllite, all those stuffs. But surprisingly, within this low-grade formation, there are a number of metabasic rocks, which actually consist of some metabasalts, some amphibolites, all these stuffs. And these are actually my point of interest. When I was intrigued while I was doing field work, actually this was my place of work before my present college. I used to work there, and while taking the students in this region, I was a little bit intrigued by seeing these low-grade terrain consists some rocks from high-grade rocks like amphibolite, which is of amphibolite facies. For that reason, I started collecting some samples from this region, and then started the basic thing of geological research, that's petrographic study. And there, after collecting those samples, I actually subdivided them into, after looking into those hand specimen and outcrop pattern, I subdivided into three type of rocks. One is a coarse grain variety, consists of hornblende and plagioclase, which we can call as amphibolite. The second one is another rock type which is mineralogically almost similar, hornblende plagioclase quartz, but it's actually schistose in nature. And the third variety is a very fine grained rock. It's actually a metabasalt. And after looking into the petrographic details of under thin section microscope, I observed that this coarse grain variety actually consists of mainly calcic amphiboles as well as plagioclase and quartz, and also around the boundaries of these calcic amphiboles, large number of titanites develop also, and some ilmenites also develop here. At the same time, while studying those metabasalts, the fine grained one, I observed that they consist both hornblende means actinolite and chlorite. Also quartz, plagioclase, and also ilmenite develop around the boundary of these actinolites, and they have a good preferred orientation. And coming to the hornblende schist, this consists large porphyroblasts of actinolite, and which are getting wrapped by chlorite schist, and also good small crystals, well developed crystals of inclusions of ilmenite present within this actinolite. So after that, after the petrographic study, I went for some mineral chemical analysis and observed that these hornblendes, mainly these coarse grained amphibolites and the fine grained metabasic rocks, which I termed it as metabasalt. These are mainly calcic amphiboles, mainly of Charnockite and magnesian hornblende variety. But the hornblendes from that hornblende schist, they are actually tremolite or actinolite, means less calcic amphibole in nature. And while doing further analysis, I observed that the XMG ratio is high in this case and the CA ratio is less. And from this data, it can be said that as calcic amphiboles, these are more calcic in nature, they may have developed in higher grade of metamorphism. Now coming to some epidote, classification of epidote. Most of the epidotes fall in this category, and the chlorite mainly consists of glynocore variety, and in some cases, especially in case of the hornblende schist, also chamosite variety can be observed. Now coming to the metamorphic evolution of North Shingmu mobile belt, mainly the northern part of North Shingmu mobile belt, number of workers have done their work from those metapelites. And while they have suggested that mainly the metapelites, mainly this staurolite or garnet bearing mica schist or the phyllites, they have suffered a metamorphism of around 470 to 580 degrees centigrade and 4 to 4 kilobar pressure. But while observing the under microscope, when I observe the minerals, suppose the Charnockitic variety of hornblende, those things can't be developed in, generally doesn't develop in this low temperature and pressure regime. For that reason, I have done the conventional thermobarometry and observed that they have done, I don't have number of options. I only managed to do these things, aluminum hornblende barometer and the plagioclase hornblende thermometer, and they give us a data of around 7 to 7.8 kilobar pressure and 500 to 550 degrees centigrade. At the same time, while observing the petrographic under petrological study, while doing the petrological study, I observed that this is actually that amphibolite type of rock. Titanite is getting developed as rim around the ilmenite, as well as the next slide, if you can see, chlorite gets developed around the boundary of this Charnockitic hornblende. So it can be, we can suggest that maybe a peak metamorphism of around 500 to 550 degree and 7 to 7.8 kilobar pressure developed in these rock types. Then again, due to some fluid activity or retrogression, they again move down to suppose that 4.4 kilowatt pressure or 450 degrees centigrade, which has been documented from the metabolites by previous workers. Now, how to address that ambiguity? Suppose metabolites giving a less pressure temperature regime and these rocks giving a high pressure temperature regime. For that reason, we can approach firstly geochronology. Geochronologically, previous workers have suggested these are the data from the previous workers. Suppose this is the emplacement of some felsic volcanics from the North Chingu mobile belt. Suppose it's actually from Chandil formation. Detrital zircon from Chandil formation also give a date of 1627 plus minus 6 million years. At the same time, there are a number of intrusive granitoids which get emplaced along the boundary of North Chingu mobile belt with CGC or Charnockite Petrogenesis complex. Again, if we look into the metabolites of Chandil formation, they gives us an age of 1300 million year to 900 million year. It's a range. So if we can address this, if we can analyze the rock minerals from Chandil formation, these metabasites from Chandil formation, suppose batellite or if zircon is available, then we can actually understand the evolutionary pattern of these metabasites from Chandil formation, at what time they got developed. And then we can suggest whether they have been developed at the same time with these metabolites or they are actually a protolith which got emplaced within these metabolites, because I haven't done any structural field, detail field. So I can't now say anything about the structural arrangement of these metabasic rocks with the metabolites. So detailed fieldwork, structural and lithological fieldwork is the most important thing that I have to do. And after that, geochronological study, and especially isotopic study of SMND can give us some insight about the source of these rocks, the mantle source, what is the age, and everything else. So this is actually my work is in a nascent stage. For that reason, I just like to present the basic observations. For that reason, I have presented this thing. And these are the references. I want to thank people for supporting me.
Thank you. Any questions from the audience, please, or any suggestions?
So this is a medium grade metamorphism.
Amphibolite.
So around that you don't see any such high temperature metamorphism around that. How far is this from Kootenai?
This is a bit far from Kootenai. Actually these metabasic rocks are in a east-west trending line, and they continue from the Mukutmanipur Dam to west till Barabazar. So around 50 kilometers.
So I have seen some dikes there. Are these metamorphosed dikes or what?
Actually, the dike part I have seen as the metabasalt, which I have termed it as metabasalt. I have seen it as I addressed it as metabasalt. Maybe
because there is a major shear zone passing through Bandhawan to Barabazar.
The shear zone is in east-west trending direction.
So your rock is also east-west
trending there. For that reason, I have to do a detailed field work to observe whether that shear zone influenced this high-grade metamorphism or not, because the metabolites
this is very strange. I mean, I worked in that area, Kootenai, Barabazar, and everywhere. The grade is much lower.
The grade is
much lower, not to this amphibolite.
But I have been intrigued by these rocks because they are showing amphibolite species.
This characterization is okay. I mean, this is amphibolite species. If you have a hornblende plagioclase, what can it be? That's simple. But well, I cannot reconcile with the geology. That's the problem.
Okay.
Arnab, do you have plagioclase composition in any of the metabasites that you have?
Yes, they are all.
So what is the composition?
They are
Is it compositionally zoned or compositionally
No, they are
homogeneous?
not actually zoned. Mostly they are albitic. The albitic part is much more. Anorthotic part is less.
So is it oligoclase or is it andesine? That will give oligoclase.
Oligoclase.
So do you have epidote as a mineral which is stable with hornblende and plagioclase?
Epidote is there. Around the boundary, the epidote is getting developed as reaction texture.
But whether that epidote is of retrograde origin
That
or whether
I actually am very much confused that there is some epidote as it's getting emplaced within the hornblende and some are developed around the boundary. For that reason, I don't know whether there are two generations of epidote. One during the prograde metamorphism, it got entrenched within the hornblende, and another one while the retrograde happened.
Why I have asked you this is that you have some idea that metamorphic pressures where hornblende has formed is of the order of around 7.7 kilobar. So your plagioclase composition is oligoclase. So generally oligoclasic plagioclase is a characteristic feature of epidote amphibolite fascist metamorphism. So where you will have hornblende, oligoclase, and you should have epidote. So that's why I would like to know that
the
if
epidote
it
is present.
But if it is epidote amphibolite, that will support your pressure estimates.
Okay.
But if epidote is not stable with your hornblende and plagioclase, so then you have gone directly from green schist to the amphibolite fascist, and in that situation your plagioclase should be more andesinic. So therefore, try to see the origin of your epidote in your rock carefully. If it is stable with hornblende plagioclase, so this is epidote amphibolite.
Okay.
Then you will have a very good understanding the metamorphic pathway through which you have landed in epidote amphibolite fascist.
I have to do a detailed work. This is a very basic work I have done.
Just a very minor comment, just building up on what Shantanu also said. The amphiboles are blue-green amphiboles mostly, the ones that we showed. Usually when you go up into the amphibolite fasces where you eliminate
towards brown.
More titanium I presume will get in, so it will
increase.
So
Actually, in that the actinolite cyst which I got, there some amount of brown hornblende is getting developed.
so it's just starting. You're at the border, maybe epidote amphibolite, but you don't see any epidote, right? That's what you say.
In the the coarse grained amphibolite, there are epidotes.
You do see a few epidotes.
There are epidotes around the boundary of the hornblende. I have shown in that picture. Can you just put that thing on the PPT?
But I think your titanite that is surrounding the ilmenite, or titanite is breaking down to ilmenite?
Sorry, just a second.
Titanite is surrounding the ilmenite. Yes. So that means that you have you're actually going down, I think.
Sorry, not this thing. These are the, sorry, I have mistyped it. It's actually epidote. I have put it as chlorite, not chloride. These are actually epidotes getting developed around the boundary of this hornblende. And there are some reaction textures. Here we can see some sort of reaction textures.
See, titanite corona developing on ilmenites, even on magmatic rocks. I mean
these are very good example of getting developed.
So these are not uncommon textures where an igneous rock is loaded and getting just in the nascent stages of getting metamorphosed. I've seen these features, so it would be interesting. And the other thing is that again your thing of saying it's metavolcanic, is it simply because it is fine grained now? But it's entirely metamorphic, so you don't know what the grain size was originally.
Another thing is that because the adjacent to this place is Dolma volcanics, maybe they are part of the Dolma volcanics, but if I don't do any geochronological, I don't get any geological.
I think.
No, but these things continue till the south. I have shown a very small map. but they have continued south till that Bandwa.
No, that is actually quite an interesting and important thing you're saying, which you will need to prove if you.
I have to do a detailed field work for that.
I'm just saying that I mean it, whether or not it. I mean, just from the metamorphic grain size, I don't think you should make an inference about whether it was volcanic or plutonic.
Actually, my title is bit misguiding.
No, but anyway, I mean, these are things that I think would be interesting to see.
I will have to do some detailed field work and present something more interesting. There are some carbonites around Beldi, but I haven't. But I didn't find one actually for going to the field, and I have searched that location, but there is. Actually, there is a.
Okay, thank you, Arnob. I thank you for the nice talk. And now, with this, I have concluded this session, probably the last session of the day, the oral presentation. Okay, thank you very much. And now.
Okay.
Thank you, sir. Now I will ask our director, sir, to hand over the memento to Dr. Lopamudra Shaha and Professor Rajiv Kaur. Mentioning the name. Now I will request again our director, sir, to hand over the certificates to all the presenter. So please, first, Professor Shomnath Dashgupta. Now, Professor Shantanu Kumar Bhomik. Exactly. Dr. Tapobrata Sarkar. Dr. Aliba Ao. Professor Shankar Bose. Dr. Amal Dev. I think he's not here. Amal is not here. Dr. Shirina Roy Chaudhuri. Yeah. Dr. Ajay Kumar Singh. Dr. Lopamudra Shaha. Dr. K. Naidu. Professor Shoibal Gupta. This time I properly mentioned. Dr. Priyadoshi Chaudhuri. Dr. Momita Talukdar. Dr. Aditya Naik. Dr. Mohammad Raza. Dr. Pritam Nasipuri. Dr. Shreya Kormokar. Dr. K.R. Adisheshan. Dr. Arnab Dashgupta. Shirina Roy Chaudhuri. And for the 2 days poster presenter also, we are giving the certificates now. Yes, because going downstairs and coming upstairs is a bit difficult, that's why. So, V. Deep Chand. Amresh Bharti. Anuj Ghosh. Anmesha Ghosh. MS Parvati. Siddhi Sirodkar. Rituparna Naik. Sanchari Chatterjee. Soumya Ranjan Behra. Tiasha Basu, Bishwaranjan Pradhan, Preeti K, Devashish Bora, Shorab Mitra. And yesterday, 2 people didn't get the certificate. Dr. Ashish Dongre, Professor A.P. Pradeep Kumar. And now we are giving the memento for the poster session chair, Dr. Topobroto Sarkar. You will chair the session later, but you are getting the Dr. Shreya Kormokar. Dr. Momita Talukdar. Also, we will give the memento to the yesterday's poster session chair, Dr. Amia Samal. Dr. Rohit Pandey. Dr. Shimontini Shen Sharma. Dr. S.N. Mahapatra. Thank you, sir. And next, our cultural program will start by 6:45. No, in the downstairs. Before that. Yes, yes. Posters are there. No. Posters are already attached there, so you can visit and you can interact with that presenters. And after that, cultural program will start. Enjoy that program, and after that, by 8, dinner will start. Thank you.